Okay, so welcome everyone. It's 8:50, a little bit behind schedule, but we're going to start our opening ceremony. My name is Cyril Mani, and I'm formerly part of the McGill rocket team, and now a fervent disciple of Launch Canada, our very own
Canadian rocket competition. Congrats for making it across the country for some of these teams, to the beautiful city of Timmins to launch some rockets. And on that note, I'd like to officially welcome you to Launch Canada 2023. There's nothing more Canadian than an aerospace competition in the middle of the boreal forest with a polar bear on the stage in an arena. It's on that note, Launch Canada last year had its inaugural competition in Calgary, Ontario, not too far from here, as you noticed. But we've been very lucky this year. We've been welcomed in Timmins, Ontario, to a new location, and we want to properly lead this new collaboration with the city of Timmins in the utmost respect and vision for future collaboration, because we want to find a place that we can properly call home. And so allow me to make the following 9 acknowledgments. I would like to acknowledge that we are Treaty 9 territory on the land of which we gather. On which we gather is the traditional territory of Oxidizer, Mushkegowuk, Algonquin, and Métis people. Thank you for welcoming us on your land and showing us the ropes of your heritage while we build the future of Canadian aerospace together.
And so talking about the future of Canadian aerospace, I would like to invite up here one of the only reasons we are here today. Please give a warm welcome to Launch Canada's president, our very own Adam Trump.
All right, thanks everybody, and it's awesome to be back here in Northern Ontario for our second ever Launch Canada competition. So last year was our first time doing this, and it was a bit of an experiment. We've never had a Canadian rocket competition like this before. We knew how amazing we were all done at other competitions in the past. And we wanted to see what this would look like if we kind of isolated that incredible camaraderie, teamwork, and skill and let it loose to its own event. And you guys really delivered. It was incredible to see how we all came together and accomplished amazing things. And this year we are back with double the number of teams we had last year. So the fact that we've been able to grow the way we have is really all down to you. So thank you all for your own skill and dedication to this, and it is really going well back here. As Cyril indicated, it takes a lot to make an event like this happen. And first and foremost, I need to thank the reason why we are here, which is the Matagami First Nation and the city of Timmins, who have very, very graciously welcomed us into this beautiful part of the country to share in this journey with us. So tremendous thanks to Matagami and to Timmins for making all of this possible for us. Now, you've all been working for the last year building your rockets, and honestly, putting a competition like this together is not too different from that. It's a complex creation with a lot of moving parts, and it takes an awful lot of teamwork to make it happen. So the first thing that we needed to be able to do this is supporters. And I think everybody knows that building rockets is hard, and getting the resources to build rockets is hard. But I'm very pleased to say that we've got a number of organizations who have seen what you're all doing, who believe in what you're doing and your potential, and who have really stepped up this year to support you and make all of this possible. So first, I want to acknowledge our lead sponsor for this year, Pratt Whitney Canada, who have really come through for us. And we've got Ninad Joshi from Pratt Whitney right there in the front row. big thanks to Pratt Whitney. I also want to thank MDA, who were out here last year and again came back in a big way for us this year. They have been a phenomenal partner with us, so thank you so much, MDA, for being a part of this. And while they couldn't be here today, I also need to thank our sponsor, Maritime Launch Services. So as many of you might know, earlier on this year, they hosted the York University Arbalest rocketry team for the first ever suborbital launch from the new spaceport Nova Scotia. So that was the start of a really great partnership. They obviously see what you're all doing to build the kind of talent that will carry this industry forward. And we're so excited to have them as a part of this whole event as well. So huge thanks to MLS. We've honestly, we've got too many sponsors for me to thank all at once here, but you'll see on our banner we've acknowledged the many organizations who have come together to make this possible. You'll see some of them around here in the next couple days. So if you do, talk with them, thank them for their support, and know that there are a lot of us who are behind you, who see what you're doing, and want to see you run with this as far as you can. So, finally, I need to acknowledge the many volunteers who really stepped up this last year to make this event possible. Like I said, we've doubled in size since last year. We've got a much bigger venue. We've got much more of you here in it. We've got a whole new launch site, and this doesn't just happen. It really does take an amazing team of people to do this, and that's exactly what we've had this year. So you'll see the volunteers around in dark blue shirts, polos for our staff, and t-shirts for the general volunteers. So be sure to say hi to them. I want to acknowledge a couple people in particular who are going to be playing a very important role over this week. First up, we've got Zach Harrison, who is our conference director. So he has been working tirelessly to make all of this happen. So there he is. Boy, was that good timing. We've got Matthew Ho, who has been our logistics lead, trying to coordinate all the many, many moving parts needed to not just put on an event, but carve a launch site out of the forest. And I also want to acknowledge our launch operations team, who are going to be playing a huge role in the launch over the next week. First, we've got our range safety officers, Shane Wetherill and Frank Nobile. So when we are on the launch range, their word is law. Pay attention to them, listen to them, and you will be hearing a lot more from them over the next week. I also want to thank Dave Lefrancois, who is going to be not only our solids lead this year, but he's also been supporting launch operations, so done tremendous work. So a great thanks to all our volunteers and to all of you who came all of this way to be here. We're really excited to see what this week has in store, so have fun, work hard, and let's launch the North.
Now for a little judging blurb. Is Mitchell here? Yes, awesome. Sorry, first row. Welcome, Mitchell, our lead judge.
Hi everyone, so I'm actually here right now. I'm fulfilling, or I'm taking over the role for Robert Bernard, who unfortunately wasn't able to join us this year at the competition, but he, Karina, and I have been working tirelessly, honestly, over the last 2-3 weeks to make sure that all of the judging stuff is standardized and ready for all of you. We've made several improvements last year, but the main focus is you'll be seeing a few judges coming around and judging you. The approach we're taking this year is a bit of a buddy system. You will have 2 judges assigned to each team, and they will be your judges for the entire competition. We're going to be looking at not just over the 2 conference days, we'll be talking to you about the technical aspects of your rocket, how you design things, why you are investigating your engineering process. But for the launch days and over the whole competition, we're going to be evaluating the conduct of your team, how you go about doing things, and then also looking at the performance of your rocket. But that's kind of the easy part. All we need to do is get your altimeter data, so make sure that works. I don't want to have to try and estimate with my finger how high you went. That's not easy. So with that, we look forward to working with you and cooperating with you, and I can't wait to find out all about your different designs.
All right, so since we're trying to make this place our home, allow me a little bit of housekeeping. For the Wi-Fi, there is a public Wi-Fi. There's another one that's locked with a password. You may use it, but please limit your usage because we will use it for live streaming this event. So even more of our rocketry peers can actually attend. And so if too many people use it, unfortunately, it will crash. Also, for the volunteers here in the audience, there will be a volunteer meeting right after this opening ceremony. So please stay around. And then if you are a student team, just arrived and haven't had the time to set up your table or can't find your table, the setup has changed a little bit, so just try to find your category, whether it's basic, advanced, or technology demonstration, and take the table next to it and establish yourself a home for the weekend. Then for talking about live streaming, if you have family at home, friends, significant others that didn't do the drive all the way up to Timmins, there is a way to attend this event. There's a live stream going on now. So if you go on our social media, on LinkedIn, you'll be able to see the link for it, and you can share it on your own social media as well, so that even more people can get to see our work and our sponsored logos. And just last mention, we are running a little bit late, so if you look at the schedule for today, all until lunch will be pushed back a little bit, 20 minutes or so. And so for today, we have an amazing schedule for the conference. We'll be talking about Pratt Whitney, the career opportunities, space engine systems, scramjet engines. We're going to talk about lunar fission power on the moon, rotating detonation engines, space medicine. It's going to be an amazing day. So both will happen, both the conference and the student presentations will happen here. And you'll have, student stands on the other side, which will happen in parallel. Feel free to come in and out for the sessions of your choice. Of course, in this section of the arena, we're going to try to keep it lower so we can hear our speakers. And then finally, we have outreach activities for visitors. I think here it's mostly student teams, but if you see some visitors come, feel free to welcome them and show them that we're a warm family. And there's 2 things that we'll be organizing this weekend. We'll have the rocket passport that the teams might have heard of. So if you are a visitor and you do come, you can go at the registration desk and take a little pamphlet. And on there's all the student teams which you can go visit and get a stamp by completing their outreach activity, which is linked to their rocket design. And so for the teams, please keep 1% at your stand at all times so that if we do get visitors, they can actually get to enjoy your activity. We also have a mini launch event, so if you do see school children or visitors that want to try to put their hands to something more concrete, they can go and build their own rockets. So Ilara is at the back on the outreach table, which is a beige table towards the left back of the arena. She's right there here, so thank you very much for helping us build these mini rockets all day. And that's not even the cool part. The cool part is you get to build your rocket, but launch it. So after every conference day, we'll be launching these mini rockets, and the students will get to keep them and bring them home with their design painted on them. And then finally, tonight, there is an event called, it's Stardust event called Yuri's Night at 8:30. There'll be drinks and food. It's at the Porcupine Dante Club. And if you do want to attend, there are tickets online that are available. And then for the last part to this opening ceremony, I want to personally we'll have one more round of thank yous. Like Adam said, organizing an event like this requires tremendous work. There's dozens of people with thousands of work hours, volunteer work hours behind this event. So like Adam said, very well said, it doesn't just happen. And if it feels like a yearly family reunion for all the volunteers, it's because it really is. It's amazing to see all these people every year dedicating their love and energy for rocketry and being here. So thank you one more time to all the volunteers that put their energy into this day. Yes. Yeah. Okay, so we're going to have a couple more things to talk about. If you come up stage. Thank you.
So everyone that's flying, all the rockets have to go through a safety inspection. We'd like to get that done as soon as we can. Ideally, if we can get everyone who's flying through today, then we don't have to worry about it tomorrow. So if your rockets are ready for their final inspection, the room is just at the bottom of the stairs to the left when you're going down the stairs. We're hoping to be able to run 3 teams simultaneously. Just let us know you're coming. We'll kind of queue up. We want to see the rocket in flight-ready state with no motor and no energetics. But I want to see everything else. I want to see your electronics. I want to see your recovery harness. I want to see the full vehicle. And we're going to just go through and make sure everything's ready to go. So give us probably half an hour after this stops, and then we can start accepting teams. So yeah, just queue up and try to keep it orderly. Thank you.
And one other quick note for everybody. Awards, because this is a competition and we do have awards at the end of this. So I wanted to very quickly give you all a rundown of what we've got this year. So last year we introduced our Launch Canada trophy. UOttawa were the first ever winner of the trophy, and they now will forever have their name inscribed on it. So for this year, that could be yours. So that is going to be the grand prize award chosen from the winners of all the different categories. We're looking to see a high level of excellence for that, and our judges will be determining that over the course of the week. We've also got, of course, our category awards, first, second, and third place for the basic, advanced, and technology development challenges. We've got cash prizes for the advanced and technology development categories. And I also have to thank one of our sponsors, Cesaroni Technologies, this year. Many of you will know CTI as the company that makes the solid rocket motors that you use. And they have added some prizes for the first and second place winners of the basic category. So first place basic category wins a Pro 98 reload of their choice. And second place basic category wins a Pro 75 reload of their choice. CTI is also offered to sweeten the deal a little bit, and the winner of first place basic will also be invited for a private tour of CTI that might even include a firing of a big solid rocket motor. So that can be yours if you're taking part in the basic category. You'll see some folks from CTI out here this week. So again, be sure to say hello to them and thank them for their support for this. We've got some fun awards this year as well. So last year we introduced our Spirit Bear Award. Spirit Bear is back this year, and this is going to be for the team that shows a consistently positive attitude and great support for their fellow competitors and for the organizers of the event, and great all-round team spirit. We also have our Splashdown Awards. because there are various bodies of water and swampy areas around here. We want to make sure that teams who end up with rockets going for a swim don't feel too bad, or at least have the aid of a pool noodle when they go to recover them. So these are the selection of awards that we've got this week. Final note is we are doing this event in partnership with our friends at Stardust. So the Stardust Festival main events are happening just across the street at Boreal College. You are all invited to go check out some of those talks. They've got some great speakers and great programming over there as well. So you can see on the schedule, it shows both the talks and events here at the arena on the Launch Canada side, as well as the Stardust side. So feel free to divide your time as you like, go back and forth as much as you want, and enjoy the event. Thanks so much, everybody, for being here.
All right, so we're going to have a little break, and during that break, we'll have the volunteer meeting here. And then after that break, at around, let's say 9:25, we're going to be continuing with the rest of the conference and go through all the amazing speakers we have today. So good luck, everybody. Have fun, and let's launch the North. experience on patenting and innovation for current and future product and processes. And his interests include propulsion technology, evolution, hybrids and electric, which makes a lot of sense for his presence today, competitor movements, new manufacturing techniques like additive manufacturing, MIM, and ultrasonics. So please, everyone, please welcome our first speaker of the day, Ninad Joshi.
Coming in. We still have wind generation behind of it. All right, thanks for being here, and congratulations to all of you. Isn't it exciting to be here? Doesn't the whole vibe around the place seem so exhilarating? Isn't it very captivating? I guess the enthusiasm and the passion that we put in is so much contagious. The whole vibe is completely different here. I really don't want to use the conventional terms, firing on all cylinders, or thrusting on afterburners and so on. You really need to coin a new term for yourself to describe this vibe. All right? So, as Cyril mentioned, my name is Ninad Joshi. I'm going to talk to you all about a couple of career opportunities at Pratt. So, moving on. Pratt Whitney Canada, we are part of Raytheon Technologies. So, together we are close to an $80 billion company now with net sales of $20 billion coming from the Collins Aerospace. Then close to 23 billion coming from Pratt Whitney, and then lately we have launched the two aspects of Raytheon, which total another 30 billion in sales or a bit more. In terms of Pratt Canada ourselves, we are spread all over the world. It's close to 15,000 operators, more than 1,000 airlines, 2,500 airplanes, 58,000 still in service, and the most proudest milestone is nearly 920 million operating flight hours. This is what in 2021, and we just crossed 1 billion flight hours on the 23rd of April, on 23rd of February this year. Isn't that a great milestone? Now, since you guys are working so close to the aerospace industry, I thought it was prudent to kind of introduce you to the nitty-gritty details of the industry and then walk through it. So primarily, these are the engines that we are working on. So the aerospace industry, the way we see it today, is divided into multiple verticals. So what you see on the very left are turbofans, which go into a series of airplanes. Each model that you see, the JT15E, the PW500, 300s, and so on, each of them further goes into a series of models which go on a series of different airplanes, so we'll walk through that. At column number 2 is the general aviation, which consists of turbofans covering all the way to 2,000 horsepower. And then we have regionals, which are primarily PW127s and PW100s and 150s. You must have seen a lot of them. Then we have the auxiliary power units, which are one of the important aspects. 980, the APS family is again divided into close to 6 or 7 models, which power everything from the Boeing 747, the Airbus 380, the Antonov, and so on. And then we also have the helicopter segments. So overall, we own close to 60-70% market share for the turbofans. General aviation is again 80% plus. Regionals is 95-96%. There's nobody like Pratt Canada out there. APUs and helicopters are still in the high 70s. Okay, so for the size that we have a big market share, and we cherish that. Just introducing you to turbofans. Do you hear the videos? Is the video helping? Can you guys hear the video? Can you hear the video? Stand by for a quick second, guys. Huh? Wasn't that exciting, guys? So basically, the smallest engine that you saw was a 15-inch fan diameter with close to 1,200-pound thrust, and the largest that you saw was a 50-inch fan with 17,000-pound thrust powering the Gulfstream 600. Okay, so this one that you saw landing was the Gulfstream 600. Okay. Now moving on, so this category is a very, very demanding category. You talk about very high net worth individuals who customize their travel needs. It's more like a Lexus in the sky or whatever. And then they really spare no demands in terms of asking for comfort. Once in a while, we do see customers who want a treadmill on their airplane, or they want a jacuzzi on that airplane, and we have to cater to that segment as well. Yep, exactly. Jacuzzi on the airplane. Now, I'm not kidding. We had to provide engine air to heat up that water. So imagine that, okay? Next is turboprops. So this is also a very busy segment, which comes more from a single engine owner operator kind of segment. So let's scroll through that. This is a market segment that's more characterized by single owner operators. PT6 is our legacy product that has clearly established new horizons or new benchmarks for the competitors to follow. PT6 is the only single engine airplane that is certified to cross the Atlantic on its own. So if you have a PT6 powered airplane, you can have a single engine airplane and cross the Atlantic. For anybody else, you need a twin jet, you need a twin engine application. So again, this is a very, very busy segment. It's one of the most profit-making segments for us. Now, regionals is the most money-making segment for us. So this is something that is used for commuters. So we'll walk through that. as I mentioned here, this segment we kind of capitalize. We are well above 95% in this market segment. This market segment is characterized again by commuter jets where dispatch reliability is very, very important. And the nicest thing about Pratt Canada in this segment is we go and power both competitors. So you may be flying on the Bombardier Q8-400, which is now Viking Aerospace product now, or you could be flying on the ATR. Either ways, it's a Pratt Canada engine that's powering you. What the demand for this segment is a bit different. Here we are talking about developments in on-wing, keeping the engine on the wing as long as possible, minimizing the maintenance schedules and so on. Also prognostic monitoring of engines, make sure that you can go fix the engine before the problem comes in, okay? Helicopters, of course, this is an exciting segment for itself. So it's not me touting about industry's most reliable engines. We have several testaments and several third-party auditors who have evaluated that. Now, Pratt Canada touts itself on dependable engines. So let's put some numbers together, okay? So as a consumer, let's just assume we all buy a car and we use it for a regular commute. So we drive 50 kilometers to work one way. We do 4 engine starts a day. Start from home, go to work. During lunch, I again start from work, go to my most favorite takeout place, whatever. Start from there, come back, and in the evening, I start again to go home. I use my car 5 days a week, so let's say no work from home privileges, whatever. And I don't have any vacations as well. So 50 days a week, 50 weeks a year, I end up working. What that statistics gives me, and I have a career span of 40 years. So let's assume that as well, okay? So what that statistics gives me is per quarter, I have 240 engine starts. I do about 6,000 kilometers on my car, and I use the car for 90 hours, okay? So 6,000 kilometers is a typical mission for a PW300 aircraft or a PW800 aircraft. So once you take off, you land typically about 6,000 kilometers. That's a typical flight. Let's build more on that. 1 year, nothing dramatic happens, so just continue going. Let's talk about 10 years. So in 10 years, your car has done 9,600 engine starts. It has done 240,000 kilometers, and we have accumulated 3,600 engine hours on that. So 3,600 engine hours is typically a time between an overhaul for the smaller PT6s, the smaller turbofans, and the helicopters. So the engines just come back, say hello to us, and then go back again. Okay. Now, at 10 years, I basically changed my car, right? 250,000 kilometers. Make sense? If I have a 40-year career, I go to work every single day. I have 38,400 engine starts, 960,000 kilometers on my way to work and back, and 14,400 engine hours, okay? Now, 14,400 engine hours are typically when a large PW300 or a PW800 or PW100s, they come back for their overhauls, okay? So by the time we have lived through 4 different cars, this is when they come back just to say hello to us, okay? Now, there's one more important statistics that makes typical Pratt Canada engines, dependable. So even with after 38,400 engine starts and 14,000 hours on it, it still commands a reasonable, a fair amount of aftermarket value. Okay. Now, it's still a very, very sellable product. It still goes off from the shelf very quick. Now the dotted line is, think of this. I mean, I use my car for 250,000 kilometers, and every second car is allowed one aborted start. So that's what is called dispatch reliability. And this is what industry norms allow. And this is what Pratt Canada has been delivering to its customers. So one failed start in 2 lifetimes of a car, okay? So with that, this is how we've established ourselves as a market leader in multiple segments. And then market dominance is basically attributed to strategic investments and, of course, motivated and dependable employees. Okay. Strategic investments come, we are the biggest R&D investor in Canada, spending well over $500 million. Okay. Then we invest based on environment, the newer manufacturing techniques, and so on. And in terms of motivated employees, we have, employees have ability to grow within the company, cater to different expertise. There's a technical stream where people grow and build along a certain expertise. Then there are managerial streams where people move around different departments and go on. We also have very good initiatives on corporate citizenship. So we do invest a fair bit in terms of STEM education for war veterans, women in leadership, women in engineering, robotics, and so on. So we do cover the whole aspect over here. Depending upon which side of the brain excites you in this talk, if you're interested in internship opportunities, grab this QR code. This will take you to the Spot platform. So it will be updated on the 7th of September with new opportunities. We hire 4 times a year for each term. And then you can look for opportunities for single term co-ops or SOW type projects, or for multiple terms as well. I still see a couple of phones there, so I'll wait. In terms of long-term career opportunities, follow us on social media. We are there on Instagram, Facebook, LinkedIn, and so on. And most career opportunities are listed here. Okay. Again, they advertise careers for beginners, fresh out of university graduates, and then later mid-career professionals and so on. So you're very welcome to follow us and apply to positions as they come in. Okay. And that is all. If you have questions, you're very welcome.
So if you have any questions in the audience, please raise your hand and I'll bring you the mic. Yes.
Hi there. When would be your next hiring sort of time frame?
The next database is updated on the 7th of September, and the next interviews are scheduled for October. And then the hiring would really begin for the winter 2024 term.
Hi, thank you for the talk. I'm just wondering what your customers think of your reliability. Do they like it? Do they agree with it?
I just mentioned that we are at 95–96% market share in the turboprop segment. So the number speaks for itself. Okay. Now, for our newest G500, G600 airplanes, so I mean, rather than saying something, it's more what the customer does that matters, right? So we worked on the the 814 and the 815 engines back in 2010. The products went out 2014, 2015 timeframe. Lo and behold, we have the next product, the 812 engine, coming on the Gulfstream 400. So if the customer is coming back to you with more orders and so on, that conveys everything. If you look at the Textron family, for example, we powered the Cessna Citation Sovereign with the 306C engine. That airplane went into service in 2001, 2002, if my memory serves me right. Later on, the 306C became the 306D. So the Cessna Sovereign became the Sovereign Plus. Before that, the Sovereign got certified for an extended range. Then the extended range became the Sovereign Plus. Then it became the Citation Latitude. And we continue to do all that. So we continue to power all that. So it's more that what the customer does that gives you the confidence about it rather than what the customer says about you. Make sense? A very good point.
So you talk a little bit about co-ops. What about full-time opportunities? I'm graduating soon, so do you take resumes? There you go. I'll give it back to you.
Yes, full-time opportunities are also available. Okay, so the QR code that I shared was specific to co-op interns, or co-op or SOW interns, but permanent opportunities are more advertised on social media, and they directly come through HR. So the Spot platform with the QR code, that's a third-party site, but we use that site for 100% for hiring. So that was the reason of me knowing, that was the reason for me telling you about this. But the permanent opportunities are advertised directly by Pratt. So you find that on social. I think there were a couple of posts on LinkedIn last night as well, you know, hiring for specialist roles and so on.
Are most of your engineering divisions located in Quebec? And if so, like, how does not speaking French impact like day-to-day work and what? Great question.
Yes, the mothership is located in Montreal. Being bilingual is perfectly is an advantage for sure. But I'm based in Toronto. I've been with Pratt for 21 years. It really hasn't limited my career in that sense, you know. So I would not say that. I would not. I mean, I wouldn't say not knowing French will limit your career, but it's good to know French. It's good to communicate. And, you know, you pick up with time. French is an easy language, you know. So
Thank you. What's Pratt working on the research side of things? Like, are there any interesting technical problems that Pratt is trying to tackle right now? Great question.
okay, so I think you've asked me a very big question in a very small sentence, okay? So I'm going to, okay, so let's talk about 15, 20-year forecast, okay? So, or 15, 20-year horizon. So at that, what's actively happening within Pratt is focus on hydrogen as a propulsion unit, then hybrid electrics, pure electrics, and so on. So that's what is kind of the newest terms around. Slightly shorter term. What we see as a demand from customer is, okay, I think let me take a pause. Like not so long ago, companies used to sell a business. So you're allowed 99.995% dispatch reliability. Okay, so now if you don't meet it, fine, I need to go, send me another airplane. So that's the business model, what has happened. So in the nearer term horizon, we are looking at more sustainable materials, more durable materials that can extend time on wing and so on. And within the very short time horizon, a year or 2 years from now, the focus is more on prognostic technologies. So something that can tell you there's a problem that's about to happen and so on. Okay, so that kind of gives dimensions in multiple different ways. So anything that can, I mean, like here the technology is more on on how you can detect a failure, how can you transmit the data from the airplane to your ground server, how can you have algorithms that can keep churning the data without anybody looking at that, and so on. So then again, there are cool areas on cyber security and watchdog technologies and so on that are happening right now. So this is the complete horizon. Did I do justice to your question?
Very good question. So we have time for one or two more questions from the audience, if there's any. Then I might take the occasion to ask one of my questions. So you've talked about, you're taking a position in intellectual property at Pratt Whitney. Can you talk a little bit more about your experience working on patents, on turboprop, on turbojets, on other components of propulsion of planes, and in the airframe in general?
Yeah, so one thing we have to realize is patents are business tools, okay? So we have to derive business value out of it. Why patenting is important is I tell you what I am doing, and then it means that you should not be doing that. So in that sense, it derives market value. I mean, it puts more time on wing. Okay, so if you look at, let's say, for example, if you take a 307 fan blade, it has a typical Marilyn Monroe shape, okay? So initially you start at the fan hub, you get into a big belly, and then you go and turn up again. So there are specific reasons of why that blade was built that way. The same advantage comes on 814, and the customer enjoys that, okay? So 814 fan is again built differently than what the other fans are built. That has increased time on wing. So the customers are deriving that. 814 engines they really don't have any time between overhaul. The maintenance is condition-based. So the sensors tell you when to come back, otherwise just keep flying. So all that technology comes in, and what is at the forefront is going ahead and protecting that technology before anybody else gets access to it. So it's a space to reserve your parking spot, and once you have that, you can derive value out of it, okay?
That makes a lot of sense, thank you. And if you allow me one more question, if there's not another question from the audience. Okay, did you fly here?
No, I didn't.
No. But I'm sure a lot of us came and used some nice Pratt Whitney engines.
Yes, most likely. Typical short haul planes are PT6s, so most likely you flew on a PT6. So.
Well, thank you very much. Can we have a round of applause for Nidad? Thank you.
Thank you so much.
So to continue with these amazing presentations, the next presentation will be from Space Engine Systems, a Canadian company that specializes in developing engines and vehicles that are meant to be single stage orbit systems. So, asking to Zach at the back, do we have oh, there you go, beautiful. Joel, okay. All right, so from Space Engine Systems, we have Joel Gagnon on the screen here. Joel Gagnon grew up in Regina, Saskatchewan, with dreams of becoming an astronaut. His passion for space exploration led him to study aerospace engineering and astrophysics at the University of Minnesota. He then went on to pursue a master's degree in aerospace engineering from McGill University, yay, where he also had the opportunity to work on developing engines at Pratt Whitney, Canada, a great segue from our previous speaker. For the last 3 years, Joel has been working in the propulsion group at Space Engine Systems in Edmonton, Alberta, where he is currently working on the Hilo 1X, a turbo ramjet-powered Mach 5 aircraft. Everybody, please welcome Joel Gagnon.
Good morning, everyone. I hope
yes,
you can
we
all
hear you very well.
Okay. So I'll get started. Thank you for the introduction, Cyril. Said, I'm Joel Gagnon, and I'm with Space Engine Systems. So, out of a company headquartered in Edmonton, Alberta, and definitely want to thank the organizers for inviting us to speak today, present a little bit on what we do at Space Engine Systems, and I hope that the audience will appreciate what we have to show. So we like to call ourselves the lowest cost trucking company to anywhere in space, including the lunar mission. So our president and CTO, Pradeep Das, founded the company with the ultimate goal of going to the moon. And everything that we're doing before then is just really to prepare for that ultimate vision and hopefully create other products, spin off other technologies along the way to bring in revenue and bring value. So quickly, this is the content that I'll try to go over today and hopefully leave a good amount of time for some questions. We'll start with a brief overview of our Hello series space planes that we're developing. Then we'll go into the engine that powers it. So it's the DAS GNX. It's a hypersonic turbo ramjet engine. Then I'll briefly talk about how we're testing that engine, go into some nozzle design, and then briefly talk on joining space engine systems, and then questions after that. So the Hello Spaceplane series, we're starting off with the Hello 1X. This mission is basically to demonstrate our turbo ramjet technology. So the Hello 1X will take off horizontally like a regular plane, use a turbo ramjet all the way to Mach 5 speeds and roughly 32 kilometers. It will then glide, land back, and land horizontally like a plane. The next, so I should say, the goal is to fly this next year pending regulatory approval. The next step is the Hello 1. And so the beginning of the trajectory is the same. It uses, again, the DAS GNX engine to go to Mach 5 and 32 kilometers. But at that point, then a conventional rocket engine kicks in to take the vehicle up to roughly 100 kilometers at the edge of space. That's when a transfer vehicle is deployed with its own engine that can bring a payload to orbit. So its mission really is the delivery of this transfer vehicle to bring payload into space. Oops. The Hello 2 will basically be a scaled up version of the Hello 1. Because it's so much larger, same flight path, but now this transfer vehicle can bring a lot more payload to low Earth orbit, or even then GEO, translunar injection, hopefully payload to the moon. So just to briefly touch on the capabilities of what these space planes will have. So the Hello 1 and Hello 2 also could be used for hypersonic point-to-point transportation. So that's here on Earth, going roughly Mach 5 speeds. You could bring important cargo a lot quicker in case of emergency, or different applications including organ transplant when it's critical to bring something super quickly. Could also be used for simply suborbital return research flights, because we go just to that suborbital point, as well as crewed flights. And then for Hello 1, we can start bringing payload to LEO. Hello 2, now we're looking at more mass to LEO, and then payload to GEO and to the lunar surface. So we think that using an air-breathing engine for that first part of the flight can bring down the cost to bring stuff to space. And that's basically powered by this DAS GNX turbojet, hypersonic turbo ramjet. So it's a pre-cooled air-breathing turbo ramjet. So pre-cooled meaning there's a heat exchanger in front of the conventional turbojet, and we use a coolant like liquid hydrogen, which is a great coolant, and then we can use that as well as the fuel in the engine. And as many of you probably know, hydrogen has a really efficient energy, one of the highest ISPs, so a great way to use it as a coolant and then a fuel. And then a bit more detail on this engine. So it operates like an afterburning turbojet from takeoff to about Mach 3, and then it transitions to a purely ramjet mode. So the air bypasses the turbojet core and gets combusted and then out the same nozzle. So here's a picture, screenshot of one of our ramjet testing that we did. I think this is over a year ago, testing different fuels, different operating conditions on one of our smaller scale testing here in Edmonton. Always fun when the testing is going on in the office, get to see some cool flames. And then this is our much larger scale mobile engine test cell. So on the left, you see another cool kind of screenshot of a full afterburner test that we did. And on the right, you kind of get a little bit better picture of what this test cell kind of looks like. And it's mobile, so it's in a shipping container, so we can bring it to wherever we want to go test. And we built this all in-house. So I touched a little bit on the engine, the planes, the testing. This just a brief look at some of the methodology, some of the simulation, CFD that we do. So one interesting part of our design is we don't have like a traditional cruise condition for our plane, because we're trying to basically accelerate and ascend as quickly as possible and bring something into space. So the question that we ask ourselves is, well, how do we optimize anything, and in this case, a nozzle, for an accelerating and ascending trajectory? So although let's say Hello 1X goes to Mach 5, it's not cruising at Mach 5 for a long period of time. So you might not want to optimize it for Mach 5. You want to find a way to optimize it for that whole trajectory. And so my colleagues and I wrote this paper, and we presented it at the 25th AIAA International Space Planes and Hypersonic System and Technologies Conference earlier this year in India. And what we did is we conducted a CFD sweep on some key nozzle parameters for a single expansion ramp nozzle. So this picture on the right shows sort of a 2D cutout of a ramjet CERN nozzle, single expansion ramp nozzle. And we parameterized the key lengths, angles, curvature, did a large CFD sweep, and then optimized the nozzle using a trajectory optimization software. So for this particular one, we're looking at optimizing it for emission from Mach 3 to Mach 7. And what we found is, using this tool, we were able to reduce our time to climb by about 10% using this approach. So a lot of really interesting optimization problems, trajectory simulation, CFD work going on at Space Engine Systems. A lot of fun. A lot of these problems have not fully been solved yet. They're not super obvious, so you get to really look at novel problems and see how to solve them. So briefly, if any of that was interesting, a little bit more about Space Engine Systems. We are headquartered in Edmonton, Alberta, but we do have operations in Canada, US, and the UK. Just picking, so on our website we have a lot of careers posted. Some highlights about this junior aerospace mechanical engineering one that I think are probably accurate for a lot of the positions too. You really do get to engage in the full breadth of the development program, and it's a very hands-on environment. So as you can see, we do a lot of testing in-house, we build things in-house. A great experience for engineers. You're expected to wear a lot of hats, so design, procurement, inspection, assembly, testing, maintenance, analysis, any of those things you could be expected to do and learn. Having said that, we are a lean team on aggressive testing programs. So it's fast-paced, it's exciting, but it is also a lot of work. So it can be very demanding in terms of time allocation. So may not be for everyone. You have to be quite passionate, dedicated, and really interested in doing this kind of work. And then, of course, we also have internship and co-op positions available. So all of that information is also on our website. We also have a presence on social media, LinkedIn, etc. And then here's a little bit more contact information. You can email us, info@spaceenginesystems.com. And then this QR code should also bring up a few different links. so that you can follow us. So, having said that, I think I'll open it up to any questions.
Mic check. Test 1 2 1 2 test. Test 1 2 1 2 test. Okay. Can you hear me, Joel? Joel, can you hear me? Just making sure that Joel can hear us through the mic. And any questions for the audience for the moment? Okay, perfect. So Joel, you can hear us? Hello, Joel.
I can only hear you, I think.
Okay, perfect. So I'll be passing the mic around. We have a question
Relay
here.
the message.
So say your name and you can ask.
Hello, Joe. Thank you for the talk. My name's Talon from the University of Toronto. And my question is, what market sectors would spaceplanes service better than rockets, for example? Like, how do you guys market yourself as the better alternative?
Sure.
Oh, Joel, did you hear that question?
Not quite, sorry.
Okay, we're going to move to the back and ask the question directly on the computer. Thank you for your patience.
Perfect.
It's a good question, so I want to make sure.
Yes, very well, thanks. Yeah. Great question, Talon. I think, thank you for the question. So, I mean, really, it comes down to money. We do think that our system can reduce the cost to access to space. So, in terms of, you know, competing with a traditional rocket company, we think we can bring down the cost simply because if you look at the rocket equation, for example, you look at the ISP of a rocket compared to our turbo ramjet from this 0 to Mach 5 trajectory, we're 10 times better than a rocket. We think because of our architecture where we are able to glide land, that's basically a free re-entry, whereas companies like SpaceX have to use extra fuel to bring down their reusable rocket. So those two things are just an example of how we think we can bring down the cost. So like we said, trucking company to space, we're just trying to bring down the cost and compete in that way.
Great answer, thank you. Just validating, can you hear my voice? Okay, so if you have any other questions, we'll have them at the back. If you want to ask them directly to Joel, so that we can make sure that the audio actually goes through. In that case, I myself have questions for Joel, so I'm going to run to the back.
Awesome.
Can I do both at the same time? Okay, Joel, can you hear me?
Yes.
Okay, fantastic. So in propulsion, many fields cross, and the powering an engine is at the crossroads of many fields. Which one would you say is the hardest right now in the development of your product? Would you say material science, thermodynamics, heat transfer? What is looking like the biggest challenge right now for space engine systems to break through to achieve your objective?
Thank you, Steven. That's a really good question. I think it's almost like there are solutions that exist to tackle the thermal problems, let's say, of hypersonic flight. So there's, of course, at Mach 5 speeds, you have these shock waves that end up bringing your skin temperatures on your aircraft to really high values. But then how do you still build a lightweight structure? So it's, I sort of see the main problem is the integration of it all. So you kind of know what to do for the thermal, you know what you should do for aerodynamics, you know what you should do for propulsion, but it's not obvious how do you actually find the compromise between all of those problems. So I really do see it as like an optimization problem. That's sort of how you can solve this.
Thank you. Great answer. And in a similar vein, we at Launch Canada is the intersection of a lot of fields as well. We have students from avionics, payload, aerostructures, propulsion. So what could you share? You know, you've presented the progress on the propulsion system, but Space Engine Systems is working on a full vehicle. Could you share a little bit the progress on other components, such as the airframe, avionics, and flight computer?
Yeah, so I can't share too much detail about the actual Hello 1X vehicle. So this is kind of a rendering of it. But we're really focused on this Hello 1X, trying to fly this next year, but it's pending regulatory approval. So unfortunately, we haven't put too much in the public domain on this vehicle yet, but hopefully as we get closer to actually doing these flight tests, there will be more out there. Yeah, it's supposed to go to Mach 5, 32 kilometers, so it gets hot. It's a huge challenge, but we are up for it. So
that is totally understandable. Thank you. And for my last question, if you allow me, you mentioned that Space Engine Systems is open in multiple countries, the UK, USA, Canada. Would you mind sharing what's the strategy in being open internationally, and what's the reason behind this multiple offices across the world?
Yeah, so there's multiple good reasons. For one, we recently made an announcement with Spaceport Cornwall in the UK. And so we've taken over our facility there. Part of it too in the US is we do think that going with the FAA for trying to do an experimental flight of this kind is likely going to be faster than trying to get the regulatory approvals in Canada. But we are kind of trying our best to look at all different regulatory agencies and getting that to work. So on a regulatory standpoint, that's one motivation. And then, of course, there's different expertise in different countries. And, of course, we always want to attract the best talent. So probably those are the two biggest things. I guess at some point, once we're really operating, our system, it's a horizontal takeoff and landing vehicle. We can do it really off of any conventional runway. So we do expect to have many operations around the world, depending on our customers, etc. So,
thank you very much for your answer. And if there are any other questions in the audience? Okay, well, Joel, thank you. Amazing talk, really interesting, and it opens the window on this great company that is Space Engine Systems, and hopefully some of our students will end up working there and contributing to your mission. So thank you very much.
You're welcome. Thank you very much for having us.
Absolutely. And so now for the rest of the conference, we will be on a break for 10 minutes and come back at 10:30 back on scheduled time for Rocket's presentation. Thank you very much.
SRAD Avionics boards. So the top part, like I mentioned before, same thing, Raven 4 featherweight, RFD 900 dual antennas, and then it also has the battery packs. So the square battery pack you see up top is the SRAD battery. So that uses 21700 LiPo cells, and we make our own battery pack. And then at the bottom, you have a COTS 9-volt battery pack, and that's actually dual 9-volt slots that are actually connected in parallel. So that makes it dual redundant, and then you also have just more autonomy. So if both work perfectly, you have double the autonomy of a standard 9-volt. And then obviously if one disconnects or something, you have the second one as like a safety measure. So yeah, so these are the two modules when they're assembled. And then, so this is the SRAD module. So as I mentioned before, modular board rail guides, board retention plates. So the metal plate you see in the front is to make sure that due to vibrations, the board don't come loose or potentially slide or move when we don't want them to. It uses sealed circular cable assemblies. So those are military style connectors that actually come and lock into place for all our charges. It has, so the connectors we use are multi-frequency vibration tested. So there's rigorous validation that goes into those. And then we have 100G shock tested PCIe slots. So every interface with the backplane is done through PCIe slots. So same thing that's in a standard computer. And the ones we used are tested for high acceleration, high vibration applications. So what's really cool about this SRAD system is it allows for like really agile product design. So you can change and modify boards kind of on the go. We even have a folder of all our boards, and on the fly we can swap out boards. And each year we can also redesign one board instead of redesigning a whole avionics. And then in the future upgrades part, I'll talk about also just the scalability of what we're able to do with this. So obviously it has adaptive mounting. So we've used, obviously we used it at Spaceport in an actual CubeSat. So it took up 2 U's. Then we have, all the way on the left, we have the bulkhead that we're using at Launch Canada. And then in the middle is actually a metal 3D printed bulkhead that we've used in the past and at Spaceport. That's just ultra lightweight. But basically the whole avionics mounts with just 4 screws. So it's really easy to put into the rocket, take out, and move places. And it's small form factor lens that it's really easy to place in the rocket. So electronics construction. So the avionics is multiple modules that we have right now. So there's backplane, which is kind of the interface between all the modules. Then you have the actual modules themselves. So they're the 5 that are listed below. So you have acquisition, which is obviously acquisition, data fusion, kind of high quality sensors that give you a lot of information. You have your arming, so it's an independent charge activation. So it's actually 2 separate boards on a single PCB. And so that's done with Bluetooth. So you have a Bluetooth connection to the board where you can actually arm each system independently and each of the charges as well. And so we have our own application that one of our members worked on that I have screenshots of after as well. Communication, so that's used for short and long distance communication. So we have both internal Bluetooth within the rocket. So if we have multiple Avionics systems, we can actually communicate between the 2 within the rocket using Bluetooth. And then we have obviously the radio module that I mentioned before, which is for like super long distance communication. Then we have mission. So mission is flight control, charge activation. Basically that board is independent from everything else, and it's the one that takes all the choices and decisions on when are we going to open our parachute, when are we going to separate the rocket, basically all the important stuff. And then PSU, it's in the name, so it's system power and monitoring. So we have just a bunch of sensors on there as well for our battery monitoring. So this is the backplane. So it has 6 modular positions. It has a STM32, which acts as a CAN bus supervisor. So all our communications are done through CAN bus. So through the backplane, we actually have basically a CAN sniffer. So we read all the packets that are going through, and we store that on both an SD card and a flash memory module. So we basically everything that's going on that's being transmitted between the boards, we're able to save, and then we have an overall view of what happened during the whole flight. Dual redundant battery connectors. So up at the top is the battery connector. So you have 2 connectors just in case there's one that were to wiggle loose or to break. You always have dual. It also has our famous RGB party mode. So it has a bunch of RGBs that we can put on and make a show and rainbow with it. So that's always cool. And then each position is actually encoded. So when you plug a board in, each position actually has a specific ID that it transmits to the board. So each board knows exactly where it is in the backplane as well. So that way you know basically which board, say if there was an issue with a board, you know which board and which position is causing a potential issue. Acquisition, kind of same thing. It's an STM32 with an SD card for saving local data. It has an XSense MTE set, so that's an accelerometer, barometer, magnometer, and GNSS, which is just location finding. And then it has a connection at the front for an SRAD GNSS antenna that I'll show later, and it uses a data fusion algorithm. After arming, so the line you see down the middle of the board is the actual physical separation of the two boards. So it's basically just a flipped mirrored copy. So it has two independent for COTS and SRAD. It has a Bluetooth STM chip. And then it does so charge activation, and then obviously board and power distribution. Communication, same thing. The difference with this one is it has a redundant GNSS, so this has a COTS GNSS connection, but it uses the same chips and the same Bluetooth. And then you have a connection for the 900 megahertz radio module. Mission, so mission is same thing. It has STM, SD card, EMU. So the EMU is actually what, the EMU along with the barometer is what takes care of the actual mission. So it looks for apogees attained, specific altitudes to open parachutes, staging, stuff like that. And yeah, so it'll deploy the charges basically itself. And then it has, for our payload that we use, we have a special version of this board which has a parachute motor control. So that's actually for controlling a motor for a spring-activated parachute. Power supply, so same thing. It has a STM SD card for saving everything locally. It has distribute system power, and then it has current and voltage monitoring. So during the flight, we can see the evolution of our batteries, how the charge is acting, and then how much current we're pulling from all the boards and during different flight states. And then we have a special board, which is we call USB telemetry. So this is used for just testing boards. So it uses a micro SD card, and then on the right and left, it has slots for two boards. So this is for prototyping and testing. You put a USB, and then so it allows for super rapid testing. You have all these jumpers right at the front that are actually all the outputs of every single board. So you're able to read all of those, and then you have a USB plug for just debugging and programming the different boards. Data transmission, so I mentioned super briefly our SRAD GNSS antenna. So it's a helicoidal GNSS antenna. So it's up there in the top right. That's it getting tested at Antenna Lab in the US. So we actually sent it out. And then in the bottom right, you see the results of, so that's actually just the diffusion. So it's almost 360 degrees. I believe it's somewhere in like 358, something like that. There's like a super small dead zone. And then it has super low return loss on the frequency band. So the three lines, the three arrows you see is the three frequency bands that we use for GNSS. And so it works really well for that. Wireless communication, I mentioned it super quickly. So it's actually done with an asynchronous mesh. So we can have multiple modules, and basically each module will receive everything. It's basically just a broadcast to all the modules. And so you have your ground station, which is where we get all our telemetry. And then you can have a payload, you can have an avionics, you can even have two avionics modules and basically get redundant data from both. And then you have short range through Bluetooth. So the main avionics to a secondary avionics, the main avionics to some sort of motor control for hybrid rockets and stuff like that. So you have kind of a lot of flexibility with what you're able to implement. This is the Bluetooth application. So you have your device verification, you have your activation. You can also see the charge status in real time, and then you can activate them all one by one. And then we have an abort mode in case of an emergency. You enter like a two-digit code to shut down the whole system instantaneously, basically. This is Qt Station. So Qt Stations are ground system software. So this is where all our telemetry is sent. So you can see we have graphics. So the whole middle section is our altitude, acceleration, velocity. All that information is plotted over time. In the top right, you have the charge status. So in real time, even from where we are, we can see what if the chargers are still connected. And then after an event, we can actually see if the charge properly popped and if it's no longer connected. And then on the right side, you have GPS tracking. So you have two GPS you have basically two maps that are displayed along with the specific GPS point, the distance relative to you, and then you have one for the rocket and then one for payload, because usually we're flying with a payload. And we've also been working on a new second screen for Qt Station, because we actually have a camera system that we've been working on that actually tracks the rocket using image recognition and processing with a big camera. And so we take that live feed and we're working on getting a real-time overlay of the status of the flight, the velocity, and the altitude all in real time while you see the rocket going up. So it's pretty cool to have everything like in real time. You don't even have to look up, you just look at your screen. So, like most programmers usually do, so yeah. So this is the SRAD battery pack. So you have 4 Li-ion cells, an integrated battery management system, the power usage and basically all the consumption is regulated by PSU. And we've tested the battery life up to 24 hours, and the batteries were still more than half full. So we're like super confident. We said there's no chance it's going to be sitting and waiting more than 24 hours. So we tested up to 24 hours, but it could go for a lot more, you know, if we really had to. So that's a battery pack. So it's basically kind of it's a sandwich. So you have 4 screws. So you can open up the battery pack, change the cells, reclose it, and then close up the screws. So it's not like you know, permanently soldered or anything. It's really something that you can open up, change the cells, and then relaunch. So it helps a lot if you have dead cells, or even if you discharge your battery too much and you need to change battery pack rapidly. This is super quick system diagram. I won't really go through it, but if you guys are curious, I can pull up the slide after and show you guys. There's like all the interconnections and how everything kind of works together and talks to each other. Future upgrades. So we're working on an onboard camera module. So that's a board that will just slot in, that'll have wires that'll go to a camera and save the video locally and maybe even live stream it. So that's a project we're working on for next year. Other scientific payload experiments. So basically any scientific experiment we make, we just have to make a board in our standard format, pop it in the rack, and it has supplied power, it has all the charges it needs, and all its data is transmitted for it. So, you know, it really just needs to focus on the experiment that we want to do. Flash memory storage. So we have flash memory on the backplane currently, and we're working on also having a separate module that kind of comes and slots in, reads all the data, and then saves to a separate flash, basically acting as like a black box. So very similar to like in a plane, you'd have a black box that saves all your data, exact same concept. And then finally, we're working on a hybrid motor. So we've been developing a hybrid motor. We actually just, if you guys come to our booth, we have some nice videos of our last hot fire, which is our lab scale, and it's pretty impressive. So we're working on actually my capstone for the end of the year is working on a hybrid motor control module for a hybrid motor. So, you know, opening valves, pressure sensors, temperature, all of the above. And so, yeah. So now I'll open up the floor, I guess, for questions and comments.
Amazing presentation. Do we have any questions from the audience? All right, I'm going to come right there. Here you go.
All right, hi. I'm just curious about how your data fusion algorithm works.
Yeah, so it actually is from Xsense. So we have a sponsorship with Xsense, which provides the MTE chip, which is the little orange chip you see there. So that has a lot of sensors in it. So it has, well, like I mentioned, accelerometer, barometer, magnetometer, and GNSS. And it has its own data fusion algorithm already built in. So it works with all the sensors and all the data we give it. And then it'll spit out different sorts of data using all of those.
Thank you.
Any other questions from the audience? I do have one, if you don't mind me. So you mentioned you're working on a hybrid program, and I've seen the videos myself, and it's very exciting to see where ETS is going. Would you mind me asking, so looking at this avionics system, how will it translate? You mentioned it briefly at the end of your talk, but how will it translate into controlling that hybrid engine?
Yeah,
what's going to stay and what's going to leave?
Yeah, so the idea would be that basically the important boards are backplane, power supply, and then some sort of communication. So this rack can also be scaled down. So say if we do ever, I think I went too far. My bad. The rack can actually be scaled down. So instead of 6 modules,
Could we maybe have the PowerPoint back on the screen? I think we exited the presentation mode.
But the idea is basically you could reduce from 6 boards to potentially 3 or 4, and then have an even smaller system, or even the same, and then you have identical dual avionics. So the idea would be the board would control everything, you know, temperature sensors, pressure sensors, valves, basically all that kind of, monitoring of the motor.
Amazing. Thank you.
Yeah, thank
Any
you.
questions from the audience? Okay, well, I have another one.
Yeah.
So I saw you were developing your avionics system in kind of a CubeSat format.
Yeah.
Are there any plans from ETS to spin off that format into a satellite division or a satellite project?
We're working on trying to start a kind of a space ETS, because there's also another club that's interested in doing a rover division.
Okay.
So we're working towards making a rover division, a satellite division, and then a rocketry division, and kind of have like a, you know, full package of all of those together. And then obviously the CubeSat just lends itself to being really easy to kind of just provide as a completed system. So if there were to be a satellite division, we could just give the system, and then they could work on like really just the experiment portion of the rocket, and not have to deal with, you know, kind of all the recovery and stuff that's involved in a sounding rocket.
Very interesting. Sounds like a lot of teams are taking that path. And then you mentioned, testing for your avionics system. Your antennas were tested in the US. Seems like you have an extensive testing experience. What do you suggest to other teams that are trying to test their SRAT systems? What advice do you have for testing and finding those opportunities?
Yeah. Well, the system also has been flight proven a lot of times, so that's pretty important too. It's just kind of flying it and testing it out. Even if it's not like your main system, just kind of having it in your rocket and getting as much data as possible is like super important. And then we try to look and work with partners that have test facilities or can provide parts that are already rated as well. So that's always helpful too. You don't have to necessarily do the testing yourself. You can kind of look for stuff that's already certified and tested for aerospace applications. Sometimes it's a bit pricier, but companies are always really excited to work with students and schools. So a lot of the times they're like really interested, like for our PCIe connectors, the company that makes them actually came to visit us and toured our complex and was like really impressed by what we were using them for and stuff. So he thought you can always look for stuff that already exists. You don't need to start from the ground up right away.
That's amazing.
And this is something that was developed since 2019, like Cyril mentioned. So it takes a few years to get to like a fully fledged system. Obviously, if you're trying to make it modular too, is like you can keep adding stuff and not necessarily need to start from the ground up every year. That helps a lot.
That makes a lot of sense. And if I can ask one last cheeky question, you're talking about flight heritage. How many of the components that will be flying this week have been already flight proven?
The flight system we're flying this week is the exact same one that flew at Spaceport. So the whole system hasn't been touched basically since Spaceport. So it either flew in the payload or in the rocket, but all of the parts that are there have already flown at least once. So, yeah.
Beautiful. Thank you.
Cool.
Thank you, Mathieu.
Ready to go for launch?
Okay, so we have an 8-minute break, and then we'll have our next speakers, which will be UOttawa. So please don't hesitate to come back and listen to more amazing work by our student teams. Thank you very much.
A big congratulations on what appears to be a very successful flight. Well done, everyone.
Okay, it is 10:59. We will be starting in 1 minute UOttawa's presentation. So please, if you want to attend, come to the conference area. Reminder to not walk next to the speakers with a microphone in hand. Reminder for me. So I will call on to the stage. I'll just give you, or you can stay. Actually, I'll give you a little presentation, your little bio, and then I'll present you guys and have you come on. Do you want 2 mics? So, reminder. Okay, it is 11 a.m. and so we will start with the next presentation from UOttawa Rocketry presenting their Hydra flight computer. So a quick introduction, the team began in 2016 and they started developing hybrid rockets, but the school asked them to learn from solid rocket engines prior to developing a hybrid engine, so very forward looking. Their initial flight computer was a Raspberry Pi based and they used an altitude targeting, and they focused on altitude targeting and active air brake. The team flew 2 rockets based on this concept, and the second, named Jackalope, placed 8 out of about 150 teams out of the Spaceport America Cup in 2019, and 4th overall in a solid 10K COTS category. Following the success of Jackalope, the team continued pursuing hybrid propulsion and is currently focused on developing avionics capable of controlling a hybrid vehicle. Very in theme. And so I would like to present and bring on stage Noah Springer from Computer Science, who is the Avionics Software Lead, Serban Popovici, Mechanical Engineering, Avionics Hardware Lead, and Fernando Nogueira, Computer Science and Statistics, Ground Station Project Lead. Nice round of applause, thank you.
Okay, so yeah, we're going to talk about Hydra. We named it Hydra to have the acronym Hyperdynamic Rocketry Avionics. And our design philosophy is much like the mythical beast Hydra. You cut one head off, 2 come back. So yeah, this is what we've done over the past year, and hopefully is a good test bed for our hybrid engine. So, quick system overview. We have an SVG, ELEPS 2N, inertial navigation system, generously gave to us by SPG Systems in France. And 4 PCBs with isolated purpose. We have a power board, a sensor board, a communication board, and a recovery board. They share power and data lines, and they can be stacked and combined in any order. We can also have multiple of the same board for redundancy.
In order to be able to actually stack as many of these as you want in whatever order that we want, we first started by standardizing the board shape as well as the mounting holes. And on top of that, each board has a set of identical connectors with identical pinouts in identical locations. So on the left header is where we share all of our power rails and data lines. So currently we have I2C, SPI, UART, and most importantly CAN. This stack uses CAN FD, which Noah will talk about more in the future. And lastly, on the right header, we have a dedicated Pyrotechnics power rail that is completely separate from the Avionics power rail. So even if a Pyrotechnics charge short circuits, it doesn't affect our Avionics. Starting with the hardware, so starting from the bottom of the stack, we have a power board. The purpose of this board is to output regulated 5 volt and 3.3 volts on the left header, as well as a protected battery voltage rail, and provide a separated Pyrotechnics power rail. So this board has a myriad of features, but just to name a few, it has reverse polarity protection, resettable overvoltage and overcurrent protection, and redundant regulators and extensive sensing throughout. Moving up in the stack, we have the sensor board. The main purpose of this board is to interface with the SPG. So the SPG looks something like this. In this little red box, we have an IMU, barometer, compass, and GPS, as well as a dedicated MCU We're running an extended Kalman filter to fuse all those sensors and give us a better approximation of the rocket's state. Since this board directly interfaces with the SPG, it also acts as a navigational black box, and it can log data from that sensor at up to 200 times a second. And then it also forwards that data over the CAN bus at a much slower rate. Another important feature, mostly for hybrid, we've included here a separate CAN network connector, and that allows us to connect a bunch of actuators to our hybrid engine and segregate that CAN network from our flight critical avionics CAN network. Moving up, we have the communication board. The purpose of this board is to provide a telemetry downlink using an RFD900 format radio. And since this data processes all the CAN bus data and forwards it to the ground station, it also acts as a comprehensive black box and saves all that to an onboard SD card. And lastly, this board is designed to sustain a power failure of the regulated power rails. So the Pyrotechnics power rail has a separate protections from the main power rails, and this board has its own internal regulators here, as well as its logic to automatically fail over to Pyrotechnics. And that way we maintain telemetry with the rocket, and we can try to debug the power problem and reset overcurrent protections and whatnot remotely. Lastly, we have a recovery board. The purpose of this board is to provide Pyrotechnics channels, function alone, and house the RSC3, which is our redundant recovery backup. This board functions alone because it single-handedly takes care of all the logic in deploying our parachutes, and up here it has its own barometer and IMU, which it can fall back on if we lose navigational data from the sensor board or other sensors within the rocket. In order to better adhere to the Hydra design rules, we've come up with a better design for the power board, which I'll present to you now, and we will be implementing this next year. So first off, this is our current header pinout. The main thing we're going to be focusing on is the right header, because we left all this empty I/O for future expansion. So we're going to take this and populate it all as a giant Pyrotechnics power bus for the entire avionics. We're maintaining the top and bottom pins, so it's cross-compatible with our old boards. But to complement this change, we're going to refactor our power board to look something like this. We can simplify this diagram, and basically the new power board relies on this three-way MOSFET junction. So we can dynamically choose how the board is wired in flight. So we can choose to wire any combination of the power input to the Pyrotechnics power rail and the board's onboard regulators. Lastly, there's only one regulator on this power board, and it has a load sharing circuit, so we can stack as many power boards as we want, and they'll all share the load on the avionics. One last thing to note is we're adding cell voltage sensing, because with this board we'll be able to charge the batteries, and we want to make sure we don't accidentally overcharge our batteries. So to take an example here, if we want redundant regulators, we can stack two boards and we can forward power through the Pyrotechnics power rail. Now of course we can cascade 3 boards, or we can add redundant batteries. Or a more realistic design would be to have one battery going to all 3 power boards. That way we're not relying on all the MOSFETs to forward power between the boards. And the most important feature is we can now connect ground power to one of the power boards. And because of the MOSFET junctions, we can create a path to our battery, therefore charging the battery, which is why we had the cell voltage sensing feature in the first place. One last thing to talk about on the hardware side is we're going to add overcurrent protection to all boards, because currently if one board short circuits, it takes the whole avionics system with it. So for example here, our sensor board consumes about 0.16 amps, so if you had overcurrent protection at half an amp, unlikely to ever accidentally trigger, and that way if it does short circuit, it just removes itself from the system and the other boards can keep working.
All right, so now we want to talk about the software behind the avionics. So our architecture, we've done it so that code is not dependent on hardware. We can change chips tomorrow, and we should be able to reuse our code. So this goes back to our philosophy of Hydra. And we've also done hardware in the loop unit testing. It's as simple as running the command cargo make test dash device. We've done message and packet tests, SD card tests, and CAN bus tests. The idea is that when we start our system, it can test itself, ensure everything is working, and then continue. We also have implemented arbitrary data testing for ground station because of how we've done our message definitions, which is nice to have that. And separation of concerns, we want to reduce code clutter. And we use Rust for this, which is nice. That actually allows us to make our code not platform dependent because of traits in Rust. So Rust also gives us nice binaries. That's a personal opinion. I think the binaries I get are much faster than C. And easier memory management. So like at the start of the year, I tried to write this in C. and there were gremlins in my computer. The memory just was very hard to debug. With Rust, it's very simple. It has some very strong memory rules that honestly are a lifesaver with memory. So yeah, let's talk about tasks. Since this is a hard real-time system, we need an RTOS that can keep up. So that's why we use RTIC. It's a hardware accelerated RTOS, so it takes control of NVIC, the non-volatile interrupt controller for scheduling. It also has some nice features like stack resource policy, reduces unnecessary context switches, simple implementation with a stack, and yeah, that improved scheduling guarantee is directly a result of NVIC and this being hardware accelerated. So you can't see that, can you? Okay, I'm gonna try my best. So these are our board-specific tasks that are from and on the sensor board. So I'm just gonna go over one really quickly. If you wanna know more, talk to me later. But we have a SPG DMA task that uses the software managers, specifically the SPG manager, the data manager, and the error manager. So the SPG manager takes control of the peripherals DMA and UART. So it's going to be actually talking to my device. And then that data is going to be stored in a data manager so that we can put it throughout the network, put it to our communication board, our recovery board, wherever it needs to go. And error manager, this is nice because we capture errors, and the idea is to be able to capture them and resolve them. So whether that be freeing all the resources for UART and DMA, then reallocating and reassigning it to restart it. But yeah, this is kind of how we've tried to implement and architecture the code. So yeah, something I want to talk about that really helped me with the SPG was direct memory access. So this is transferring data directly from input-output devices to memory. It doesn't have to be input-output to memory. It can be memory to memory, memory to input-output, but we specifically use I/O to memory. So improves system performance by reducing CPU. How it does this is hardware. We didn't implement that, Microchip implemented that, but the only time the CPU runs is when we are processing that data. Not when we are reading that data, only when we need to process it. And it does so in a non-blocking way, which is awesome because, you know, real time, we can't use the CPU like crazy. So yeah, that's something that I really enjoyed using and really helped me. So for sensor integration, yeah, we use the SPG. It's a real-time kinematic inertial navigation system. What this gives us is centimeter position accuracy. Hopefully that helps us recovering our rocket. We'll see. One way to find out, exactly. Yeah, and we wrapped, so SPG, our vendor, they give a C library. So what we do is we create a foreign function interface, and this lets us to talk to the C library. But something we did that was a little, you know, dark arts, we took away the dependency on newlib. So newlib, it's an implementation of the C standard library for embedded systems. We took away that and implemented our own malloc and free to benefit from Rust's memory safety and the ability to debug memory, because memory sucks. I hate memory. And yeah, we use the ARM GCC to compile that C code. Okay, communication. So we use Postcard. Postcard is a library for Rust for Saturday. It's just how do you deserialize and serialize data structures. And resource efficient, very resource efficient. It's a non-standard library crate, so we need to use it because we don't have access to the standard library. And we use Mavlink. I personally want to develop my own packet system, but what we noticed was the RFDs, if you are not sending Mavlink packets and you want to read the RSSI packets that it sends in the Mavlink format, it will malform those packets if you're not giving it Mavlink continuously. So something we want to look into is maybe fixing this and being able to scrap Mavlink and get rid of it. Okay, so yeah, CAN-FD. CAN-FD is awesome compared to classical CAN. We get 64-byte payloads compared to the 8-byte payloads of classical CAN, and the speeds are incredible. It's about 1 megabit a second for classical CAN, but for CAN-FD, it's 10 megabits a second, which is tenfold, much more data. FD stands for Flexible Data Rate Controller, and we use filtering, so we have no reason at the moment for the power board to talk to the sensor board, so we set it up in software to let the hardware not process those messages if it gets the ID that is associated to the power board when receiving data on the sensor board. Another beautiful thing about CAN-FD is the CRC checks, relic redundancy checks, just making sure that your packet has not been messed with on transmission. This is nice, increased reliability, but I want to show the many-to-many relationships because you're going to see a lot of stars in this diagram, and that's how we wanted to do it, because we want to be able to have many communication boards, many recovery boards, just talking and working together. Something that I'm really happy with is how we do our ground station. So we have many communication boards that can talk to many proxies. So we set up our Yagi to the radio, get that proxy data, and then forward it to many routers. And then those routers can talk to any clients. So we can have any number of users looking at our data from just one antenna. Which is a big improvement to last year's and previous ground stations where it was one person and you're all crowding around a laptop. It doesn't really work that well. Yeah, project documentation, quick thing. Documentation is great, awesome. It's super simple in Rust, cargo doc -- open. Here, you can't see that either. Anyways, it's a beautiful web page that Cargo automatically generates from your code. So you add your Cargo docs like you would Java docs, and it generates it for you. It's kind of like Doxygen, but it's built into Rust, no extra dependencies, which is awesome. Yeah, I wish you could see that. I apologize. Fernando.
All right, so let's talk about the ground station now. So when creating the ground station this year, we had to go off making something that was open, reliable, and dynamic. On top of that, we also wanted to have something that was robust, flexible, and that can have a beautiful user interface, of course, and that can be customized to each team member's use case. Our modular design, oops. Yeah, it's split into a few services, if you will. But each service, it plays a big role in the overall functioning of the ground station. These systems are the hardware provider, which basically it deserializes and transmits the data we receive from the antenna through our message broker, 0MQ, throughout the local network. We also have we also have our real-time database, which is built on top of Pocket Base. And what's nice about it is that it manages all of our, it stores all of our telemetry data, and it also gives us some really nice real-time monitoring features that are really convenient and simple to implement. And finally, we also have our web client, which is basically our modular data visualization toolkit, if you want to be fancy. And it basically can monitor from the sensor board to the state machine status to a voltage of every component of the board. And it also has other nice features, such as we have a locally hosted map, which means we can download the map of the competition ahead of time. We don't need to worry about the internet. And that's about it. And if you also play the Kerbal Space Program, you notice on the top right there's an F-ball here. So what we did is that we made a 3D scene with 3JS, and we basically get the sensor data, the quaternion data from the sensor board, and we translate it in the quaternion so that we can have like a visual real-time representation of the orientation and other things about the rocket. And well, the stack provides us with a very robust and reliable logging and real-time monitoring of the rocket. And that's something we're really proud of.
So yeah, for software, we have some future developments. As we mentioned, hybrid. Hybrid or bust next year. It'll get done, we hope. So we need to do kind of what Servan was saying. We need to make another CAN network and then add some more not power boards, but actuator boards, servo boards, whatever needs to happen to support that motor. And I think we've set ourselves up pretty nicely to do that with the modular system. So yeah, remote hardware testing, everyone's working from home now and I'm kind of jealous. So I'm probably gonna get some Raspberry Pis, set them up in the lab, connect some debuggers and then maybe SSH into them so I can work from home and test like that. And then open source hardware abstraction layer contributions. We found a couple bugs. So we definitely have to get those fixed in the how. So yeah, we need to contribute to these open source projects. And then better data for ground station testing. So we have a bunch of SD cards on our rocket and hopefully we get that data back. We're not snapped one in half. And we've certainly got a lot of data getting sent to the ground station. So in future iterations of ground station and even our flight computer, we can use this data to run tests. STM32 system, there's a question mark because I don't know yet. We'll see how the chip shortage goes, if I can even buy them. But yeah, those are some future developments. There's supposed to be a slide that says questions, but I guess it's not there.
Great presentation. Thank you very much. You can stay on stage. Do we have any questions from the audience? Okay, perfect. You have a mic? Perfect. I'll go right down there. Here. So in yellow.
I heard you mention microchip. What microcontroller are you specifically using?
Oh, sorry. When I say microchip, I mean Atmel microchip, like the company.
Okay.
We're using the SAM E51. So this is a Cortex M4 floating point. So it has a floating point unit in it. 48 megahertz is our clock rate and 256 kilobytes of flash memory. So, we're on the lower end of performance, but, we have 4, so you make it work.
Any other questions from the audience? Yes?
Solid, okay.
All right. What was I going to say? Yeah, all looks cool. All things I would like to do on my team. I am unfortunately only like one person, and usually if I was to go to them and say, hey, let's rewrite all of our software in Rust, they would look at me and say, we have a perfectly good avionics system, why would we rewrite it? And so I guess my question is, how many people did it take to do all this? Because it looks pretty involved.
For the flight computer, it was myself and Jonathan Papineau. Mr. Papineau is not here with us today. But it was me and him.
Okay. Let me add that he wasn't particularly happy during this point in time. He was getting a little depressed. It was day and night for a while. They did get done.
I mean, that's student rocketry. I think student rocketry is an oxymoron because student rocketry is just challenge and stretching each other thin.
Yes.
And you guys are a prime example of that.
Yeah. Ça ne prend pas la tête de Papineau.
Exactement, la tête à Papineau. Congratulations. Actually, I do have a question, if you don't mind. You talked about remote debugging, and
Yes.
you briefly touched the topic. I'm very curious about that. So could you give a little bit more detail about how you approach this? You mentioned Arduino boards. How can you do this, and why don't you just bring the hardware home?
So hardware is expensive. I don't really want someone to take it from me on the street. But it's also a hassle. You know, you got to bring the power supply, you got to bring this big stack. But then furthermore, say Serban wanted to work on it, I'm not going to be able to bring it to him, and he wants to work the same night I want to work. So this is the beauty of remote debugging. We haven't ironed out the details perfectly yet, but it's going to be Raspberry Pi based. We're just going to hook it up to the university network. Don't tell them. Don't tell them that. And then...
This is live streamed.
I hope nobody's watching, that's for sure. But yeah, we're just going to connect multiple debuggers and then just SSH in and use it like you would your normal computer.
Beautiful. And if there's not another question, I have another one. So you presented, you know, like you mentioned, almost a complete bottom-up design for, you know, a specific approach, modular, you know, debuggable, redundancy. How much of this is heritage and how much of this is completely new?
Sorry, can you rephrase?
So how much of your flight computer is an iteration of previous work compared to
completely new?
Completely new.
Completely new. We came up with this in, I want to say November, and then I learned Rust in December.
Okay.
Yeah. So it's been, we got here barely. It's speedrun, exactly. Yeah, 100%. Well, 98%.
Amazing. All right. Well, congratulations. Beautiful work, and hopefully we'll see it in the sky soon.
Thank you. Thank you.
So we are right on time, and I have one more announcement to make before lunch. So I know I don't know if the teams here have been through their safety review yet. I'm hearing from the judges that some teams are not yet going for safety review because they don't feel fully ready. The safety review we do today is very general. It's just to see, is this flyable and is this safe? The full extent will be done on site. So please, so that we don't have all the teams come, you know, Sunday, the last 2 hours, go and show your design. It's fair. If it's not completely finished, just show and have the judge give their thumbs up. And then we'll see each other back at 11:30. No, it is 11:30. At 12:30 after the lunch, and we'll continue with more student presentation and speakers from all across Canada. Thank you very much.
What does it take to launch a rocket? It takes vision, countless hours of planning, design, and testing. But most of all, it takes people like us. Engineers, designers, machinists, business people, and inventors. We are University of Ottawa Rocketry. Though we might look like a bunch of nerds, our competitive spirit is tenacious. In 2018, we started competing in the Spaceport America Cup, launching and recovering a 9-pound payload to an altitude of 10,000 feet. Our rocket, Jackalope, placed top 10 out of more than 122 teams internationally. But apart from our shiny medals, our mantra has always been to innovate, to learn and to pursue the interesting. From the development of a hybrid engine, to new parachute concepts, to custom avionics, and so much more, our capacity to create is through the roof. With a vibrant team of students, we foster a culture of hard work and ingenuity. This year, we set our sights for the 2023 Launch Canada competition, to reach an altitude of 23,000 feet with a solid rocket while building experience and laying the groundwork for a future hybrid engine. Our team has grown and transformed in so many ways. With more interest and collaboration than ever before, we are confident that we can lift ourselves up to new heights. We are grateful for the support and guidance of our mentors, faculty advisors, and university for taking a leap and putting their faith in the engineers of tomorrow. So, what does it take to launch a rocket? Well, it takes a team like UO Rocketry.
All right, so it is 12:27. In a few minutes, we're going to be able to continue our round of speakers, and we'll be able to start with UOttawa rocketry. So it's 12:37. In a few minutes, please head to the conference area, and we'll be beginning shortly. Thank you. Test 1 2 1 2. Test 1 2. Okay, so it is 2:32, so we're going to get going with our afternoon session of this first day of the Launch Canada 2023 conference. We are starting with another student presentation by UOttawa Rocketry. So a short introduction, the UOttawa Rocketry division is dedicated to fostering innovation and pushing the technical boundaries of student rocketry. The team's main goal is to educate students about rocketry by providing them with a vibrant hands-on learning environment. Last summer, UOttawa Rocketry made history when they launched the first experimental hybrid in Canada. Congratulations. And in the current year, the team is working towards the launch of their new hybrid, Defiance MK. So hopefully there will be the first and the second hybrid to launch from Canada soil. As well as the design and development of their first liquid bipropellant rocket, Humboldt Jr. The team will also be participating in several smaller scale rocket launches over the course of the year and support their members in getting EEE certified. So today they'll be presenting the development of an Oxidizer main valve for a liquid bipropellant rocket, and we'll be welcoming the liquid propulsion lead and liquid propulsion member Liam Zhu and George Chen. You have two mics? One mic? One mic? Do you have slides? Yeah, it's supposed to be in the clicker there should work. So we're just going to give a second for the slides to appear. No, this is... All right, the floor is yours.
Thank you.
Okay, so we would like to talk a little bit about our liquid project, and specifically we want to talk about the Oxidizer valve actuator. So we've been working on this for quite a while. It is a novel project for us in the sense that we never attempted such project before. It used to be that to allow oxidizers to flow through, which burn through a disk. But now it's more complicated. Okay, so let's get into this. Background. So there are a lot of limitations in terms of designing such actuators. First of all, there's space constraint. So the rocket is only 6.5 inch in diameter, and that's the largest thing that we can fit into the airframe. Also, there's a minimum plumbing size constraint, where if the plumbing goes too small, then nitrous, which is our oxidizer, will be flowing too fast in the plumbing system, which is unsafe. So with that constraint, we decided to use a 1-inch tubing to keep the flow under 5 meters per second, which is considered to be a safe value that we've attempted and we've verified before. There's also actuation speed constraint. So this is the valve that allows nitrous to flow into the engine. And the longer it takes to open the valve, the more transient response there is. So we want to minimize that opening time, and we want to limit that in under half a second. We also have other constraints, such as how we can assemble it. We want to make sure it's easily assemblable in the field and does not require special equipment. I also want to talk a little bit about our design philosophy. So in our team, we value safety, safety first as our main value. We want to make sure nothing explodes, nothing went wrong, and we want to make sure everyone in the team is also safe. So to achieve this goal, to achieve this value, we ask for very high safety margins in all the safety critical parts. And we also want to build on proven existing technology that are known to be functional. Other design requirements, design philosophies includes reliability and repeatability. So we obviously don't want the valve to open just once, or we don't want it to function only once and didn't work the second time, and miraculously work the third time, which would be very bad. So we want a consistent, repeatable setup, which functions every single time. We also want adjustability. So if something doesn't work, we can adjust the design quickly, easily, and again, with the repeatability that we just previously mentioned. So that includes having integrated alignment features for high precision parts. And that also includes adjustment slots for things that we can foresee needing adjustments. We also focus very hard on manufacturability, because a design is not a good design if it cannot be made. It must be manufacturable. So we have a lot of communication between our subsystems, making sure the airframe is manufacturable, this actuator is manufacturable, and they also work together as an integrated product. We are also having a lot of consultation with external manufacturers. So this includes machinists and also sheet metal fabricators to make sure the design is manufacturable. We'll quickly talk about the conceptual design, and then George will be talking about how we landed on the final design. So right off the bat, we have no experience designing such injector valve actuator. And we have a couple options. We can either go with a pyrotechnic valve, which have an explosive inside and opens the valve for us. We could have an electric motor, a servo motor that turns the valve. We could also have a pneumatic system, which turns the valve in a similar manner. and we evaluated the pros and cons of each idea. Having a pyrotechnic valve, it's going to be very easy to use because you literally just, short the circuit and poof, it opens the valve. But typically a pyrotechnic valve is very small in size. It doesn't allow full flow, which is very troublesome in our case because we're running nitrous, which can cavitate and self-decompose very easily. The other con for the pyrotechnic option is it's difficult to reset because we need to swap out the entire plumbing system, the entire pyrotechnic system, just to get a reset and try again. For the electric motor, it's a very common design choice. We've seen established company like Copenhagen Suborbital, they were using an electric motor for the similar valve. So it's very commonly used, but it does have a very high power requirement. We need a lot of electricity, a lot of power to power that motor. It is also less reliable in a sense that usually motors have higher speed but lower torque. So to get the torque required, we need an entire gear set, which is very prone to failure. It is also slow. So if we want to step down the turning speed, then we need the motor to turn very, very fast, extremely fast, in order to open the valve in half a second. So we can also take a look at the pneumatic actuation method, which can be very quick if you supply enough,
For your pyrotechnic option, do you think that having it being cartridge-based, where okay, we don't want it to be used once in the flight, but we know we're not going to have it be used more than 4 times. So if we could put a cartridge system involved, would that be compact enough to be worth it?
Yeah, that's a very good question. So I think there's 2 ways to go about having this pyrotechnic design. One I've seen very common in smaller scale valve is that you pierce through that plumbing system and allow the flow. In that case, we wouldn't only need the cartridge, we also need to change out the plumbing inside. The other option would probably be actuating or turning something using that pyrotechnic, which would be similar in nature with the pneumatic solution, where you're essentially providing a pressure source and you're expanding that pressure to get mechanical action. So I would more likely to just categorize that as a pneumatic solution. We can certainly consider that, but with our current design, it's not that cartridge-based. But thank you for the question. Yeah, sorry, let's keep going with the slide. So for the pneumatic design, first of all, it's very quick to actuate, as long as we provide enough flow rate. It is also comparably simpler design, because we only needed to turn and pretty much nothing else. However, we do need high pressure source. So as previously mentioned, we can potentially have pyrotechnic that produce such gas, high pressure gas, or the other way to do it is to have a pressure source that's already being compressed, the gas is already being compressed, and we store it somewhere and pump that or allow that to flow into a pneumatic cylinder, and that actuates the valve. So based on all of these pros and cons, we've decided that the pneumatic solution is probably the best one to move forward, because it is, again, very simple design. It is proven, a lot of people use pneumatic design to open the valve. And it is not very difficult to work with in terms of power requirement or actuation requirement, because we can potentially have the pressure source already made. It's already stored, and we just need to open a simple solenoid valve and opens this piston. And I'll let George to discuss our final design and how we landed on that.
Okay, yeah. So
I'll be doing a part-by-part walkthrough for the final design of the pneumatic solution we have developed. So, to start with the bracket, basically this is our first design iteration, and basically we need a chassis, I guess, to mount the components onto. And we were looking into sheet metal since it was something more strong structurally, but also easy to get machined. So basically, I have the first two designs we had, and the first one we have cut out parts that are unnecessary, and we did some FEA on that, and it turned out that we needed less material. So what I did there was less material, but as you can see, that does not look very structurally intact. So that is our final design, and you see we have taken out the front portion, that square right there, and that for our FEA shows that it works a lot better. The thing is, second point, aluminum versus steel. So we actually started with trying out with aluminum, and the thing is we had like 20 millimeter deformation, which is like 2 centimeters, and that's a lot more than what we want. So we decided to actually use steel for our bracket design, and it reduced it by like 90%. We were at like 2 millimeter deformation instead. So that's a lot better. So we decided to use steel. And this is our basically FEA we did. And this was the one for the aluminum. So you can see there's a lot more deformation. And at the end over there with the flanges holding the shock absorber, which I will talk about later, it's basically tilted. So we couldn't go with aluminum. Next, we developed the handle, which basically we need something for the valve, something to hold on to the valve, and for the pneumatic cylinder to hold on to the valve. So what we have is a handle that we designed. It basically allows a lever arm for actuation, making it easier to pull. So basically what we did was we thought about using either a wire or no wire at all for the pneumatic actuation. And we decided that without a wire, we wouldn't be able to fit our size constraints, as talked before, the 6.5. So we decided to go with a wire, and I'll show you how we did it. So basically, we thread a wire through, and then we make a spelter socket, which basically you open the thread, you put in epoxy, and you pull it through. And basically, we have this wire inside of the handle, which will then allow the pneumatic cylinder to pull onto the handle and open the valve. Next is the shock absorber. So that basically protects the pneumatic cylinder and is at the end of the handle. I'll show you guys a full picture at the end so you guys will understand this a lot better. But basically it also prevents overturning and breakage, absorbing the shock of the pneumatic cylinder. Additionally, as seen previously for the bracket, we have the flanges. It might be a bit dark, but basically it comes out from the sheet metal, and we decided that wasn't actually a good design structurally, so instead we made a separate attachment for the shock absorber, so it will be mounted on top of our bracket. The limit switch is something at the side of the handle. It basically detects if the valve is fully open. So when this is inside of our rocket, we wouldn't actually know if the valve is open or not. The limit switch is what detects that. So once the valve turns 90 degrees, the limit switch gets clicked and an electrical signal is sent, and we'll be able to know that it's open. Additionally, as Liam said previously, we made a slot hole on the bracket for adjustment that allows for our adjustability constraint we were talking about previously. And yeah, this lets us fine-tune the limit switch for when it's fully open. So, lastly, the pneumatic cylinder. So those two pictures look exactly the same, but slightly different. So pneumatic cylinder, we want remote actuation. We're basically using pneumatics to allow actuation remotely inside of the rocket. So we were looking at larger versus smaller cylinders. The first one is fatter while the second one is skinnier. They look the same, but they are very different inside the rocket because we actually we started with the larger one and we needed a lot bigger bracket and we weren't able to fit it inside of the airframe. So we decided to go with a smaller one. But the issue is if we go too small, then we don't have enough force to be able to open the 1-inch valve that we have, which is a massive valve. So we decided with a Goldilocks zone of decently sized pneumatic cylinder. Additionally, flange designs, we were structural, the bracket, basically we have the flanges and we had to redesign the flanges because the hole in the center was too big and another structural issue. And we also added holes, if you see, for the bolt attachment, which I will now show you. This is the full picture, and you guys will probably get this a lot more now, but it shows you all the components. At the bottom there is the ball valve, and that is the 1-inch valve I was talking about, which takes a lot of force to turn. So we have the bracket, which holds all the components. The limit switch is on the top left, and the handle is right beside that. Then we have the shock absorber, which will absorb the shock of the handle with the pneumatic cylinder up on the top right. Basically, when the pneumatic cylinder pulls the handle, it will get detected by the limit switch and also hit the shock absorber. And let's see if this works. So this is the video of us actually testing it with 3D print. So basically, this is when the pneumatic cylinder pulls it down, and then basically we have to manually reset it at the end. So we don't have the shock absorber and the limit switch in, but you guys understand the motion. Basically, the pneumatic cylinder pulls down, it pulls the handle, opens the valve, and then we manually reset it since we don't actually have to close the valve during flight. Okay, so on to our last portion, which is the next steps. So our current stage is what we have here. We finished the design process with all the things I was talking about, the 5 parts. And we did multiple spelter sockets as tests with our final one currently on the yellow 3D print we have. We made the top 3D print prototype, and then we also have the machined bracket at the bottom. So basically, what we are waiting for up next is machining the handle. Once we have the handle machined, we'll be able to test the actual valve and run a couple tests. First, the zero back pressure dry run. Basically, we're gonna have the handle fully secured, so it wouldn't be that easy to turn. As you saw in the video before, the handle wasn't actually like fully secured since it was a 3D print. But once it's fully on, it's gonna be very hard, so we're gonna need to test that with a dry run. And then after that, we will fully pressurize it and test it with the pneumatic cylinder, and we'll be able to see if our design actually worked. Does that have any questions?
Great work, brilliant. Fantastic presentation too.
Thank you.
Do we have any questions from the audience? Yes, we have many. All right, on my way.
Did I go over time?
Here you go.
56, I think I went.
Okay, how is your pneumatic cylinder pressurized? Do you have an external pressurization system, or do you pre-pressurize it beforehand and then depressurize it to actuate the valve? How does that work exactly?
Yeah, so basically we have a pressurized tank inside for pressurizing multiple things inside our rocket. And just so happens we decide to choose a pneumatic cylinder. So we have actually a tank for pressurization to pressurize the cylinder during our flight, basically.
Do you have a separate like pressurizer, or do you just use like what do you use for your pressure?
So the pressurant is nitrogen. We store it at a very high pressure inside the rocket. And basically, part of the pressurant is used to pressurize both fuel and oxidizer. And the other small proportion is used to turn this valve, basically.
Okay, makes sense. Thanks so much.
So with any system being able to abort is super important. So in the future, there's good reason to want to be able to close the valve after. Do you have interest in adding a second pneumatic cylinder with another, you call them splitter valves, or splinter sockets, to be able to turn it back, like a wire on either side?
Yeah, that's definitely something we can look into. But as of now, so this is our first liquid engine that we're ever attempting. And our main goal is just to make it, safe and then functional. So we want to make sure nothing bad really happens. And as you mentioned, having the ability to, abort is definitely important. But we also want to recognize the danger of just shutting off the valve without doing anything else. So that could also cause danger. Seems like you have a question.
Could you expand on those dangers?
Yeah, absolutely. So there's a couple parts to it. First of all, just shutting off the valve doesn't mean that the energy inside the tank is leaving. Right? There might be another pressure buildup in the tank, and that would be automatic. And we definitely don't want to have oxide and tank rupture during the flight as tested. And the other thing is, if we open it, close it, then we might have an unequal proportion of oxidizer and fuel flowing into the engine, and then that might cause an explosion inside the engine.
And then at the end, we'll come and I'll give you questions. Amazing. Do we have any other questions? Okay, I do have one. So you showed your manual reset. Is there any future plans for an automatic reset or a spring reloaded reset, so that if there's a misfire on the test stand, it's possible to fire again without opening the rocket?
Right, that's definitely something interesting we can look into as well. So I guess that also links into the previous question of having the ability to both open and close. But as of now, our approach is to just do it as safe as possible, and we're just progressively move forward. As we are confident with this design, maybe in the future we'll add on more capabilities and more features.
Absolutely. It's good to have a very first prototype and move forward. It's a fail fast, fail forward. I'm not wishing failure on you guys, but it's good. It's a good approach. And then, if you allow me another question, if UOttawa's plan is to increase, for example, the power of your engine, do you anticipate this design to be easily scalable to increase the propellant flow rate to your engine?
Right. So I think there's two ways that we can potentially expand the capability of the rocket in the future. One being just make the tank bigger, but with the same flow rate, which would make the engine run longer. In that case, the valve wouldn't change much. The other potential way to do it is to just feed more fuel, feed more oxidizer to the engine. In that case, we just need a bigger valve, and this design is easily scalable as long as the rocket is also getting larger. Because right now we're very space constrained inside the airframe, but as the airframe also grows, we can potentially fit bigger valves and bigger actuators. I guess the other path that we can move forward in the future is to have the capability of throttling. Then in that case, we're talking about potentially a different valve design, and that would be a separate topic that we can look into in the future.
Absolutely. Thank you very much. Oh, one more question. Yes, we have time.
You did mention about packaging constraints and structural, and more of stress constraints and so on. What kind of dynamic constraints did you run into? Natural frequencies coinciding with each other and so on? Did you look at those aspects?
Yeah, that's a very good question. So we do have we have considered the dynamic response in terms of frequency coupling between, say, the tank and the engine. But our idea for this valve, entire valve project design is that we just have a ball valve which only opens, and we'll lock it in the open position, so nothing else really affect how this specific part functions. And similarly, like for the actuator, we really just use it for like the first half of a second or maybe less just to open the valve. And when we're opening the valve at that time, the entire rocket will be on the ground and nothing is moving except for the valve. And after that, the entire valve would be locked open, and we just won't touch it during the flight.
We unfortunately ran out of time, but we know it's an open conference, so you can go to their stand and ask your questions directly to UOttawa. Congratulations and a beautiful presentation.
Thank you.
Thank you. Congrats. Congrats. Oh, thank you. Congrats. All right, so it is now 3 p.m. and we'll be able to pass to the second part of these presentations, and we should be joining Dr. Budo, Richard Budo. It's 1 p.m. That is a very good point. Thank you. I saw 13 on my watch and. So Dr. Budo will be joining us via Zoom. He was supposed to come, but unfortunately he had a situation at home he had to attend to.
I will try not to catch a bug at NASA Glen. So, but interestingly enough, by doing things in space, one doesn't become extremely rich. But one of the things that you can see on the dollar signs is not because it pays a lot, but these are all the projects that I've created and set up. So we have the RMS and the Dexter, special purpose dexterous manipulator. The radar Sat-1, which I did the first study in the 70s, and transforming the Amundsen into a lab, into a polar lab. And so you may not become extremely rich by doing some space stuff, but they put your projects on money. So it's a bit of a reconnaissance of the activities and the stuff that one has made. This is the team that works with us. Mark Donato and I are the elders. Mark Donato has 45 years of experience. I've hit 50 years of experience. I've worked on all projects that Canada has put in space, except for Alouette 1 and Alouette 2. Mark has been working as COO of MDA, SPAR, MDA, and all sorts of name EMS that it had in the past. He worked on the Canadarm and RadarSat as well. And you see me, you've already heard a little bit about me, but I'm involved in nuclear, metallurgy, quantum physics, big data analysis, AI, and everything. So we have a founder and CEO. He's a young man, lots of energy, and he is from the sector of real estate and found a passion for space and decided to start a company. We have Adam Grice, COO, and we have just had a new acquirement. I'm a failed astronaut candidate, but Andrew Fostel was the chief astronaut for NASA and has joined us, and that comes and helps in all sorts of ways. He's a geophysicist as I am, and he has a background in oil and exploration at Exxon, but that works really well. Then we have also on the other side, we hired two new PhDs, Matthew Canvell, which is a UBC person, and Leonardo Fortaleza, which is a Brazilian, graduated from Yale, and Gustavo Lino, who is an ISRU engineer. He works with me as a geophysicist and a metallurgist as well. So to build a company that is successful, You need in space. If you start with a lot of money, you end up with very little money. So, but if you have different values, you may be able to keep your focus and your challenges in front of you, so that you can live with your purpose. But I have to admit, it is very interesting to have been awarded 4 contracts by the Space Agency and other agencies in the last 12 months, and it's probably based on our deep experience and deep activities we've held in space. So corporate value, want us to be pragmatic. We are transparent, and it takes a village. So we find a lot of other people who have passion for space and work with us. We have very low impact on the nature and even on the moon. We are making sure that we maintain sustainability fairly high in our decision tree. And we are quick and fast of execution, very much so, because we have a combined experience in the group of nearing 200 years of space stuff. So that helps a bit. All right, so Lunar is our device, is a device that we have created. It is a micro-reactor. It is a micro-reactor that has worked for decades and has been installed and operated by people who are not the operator of a reactor, that is students, without an incident in 50 years. So these reactors are very stable. There's been a lot of them. They're Canadian-based, and they're micro-reactor in the 20 kilowatts to 50 kilowatts range, which is quite interesting, because on the moon, one needs a lot of heat to fuel or heat to warm up the resource utilization process. The furnaces needs heat, and so on. And so if you bring the heat to the ISRU furnaces, or the equipment furnaces, then you can have a fairly low need for extreme amount of solar cell arrays. But we're also considering having those reactors being on mobiles, and the activity would then allow us to move the mobile on the surface of the moon, use the heat to impinge the heat into the regolith between 22 centimeters and 2 meters. We have calculated that most of the water will be collected or will be concentrated in the regolith soil on the lunar poles. We call this permafrost, as many people believe that only ice could be the ice can only be formed in craters, in deep craters where the sun doesn't shine. Our view of the world is that it can, just like it is in Canada, produce permafrost underground that can stay for billions of years. And once it is underground as water, it is very probable to have also some CO2 attached to it. So giving us quite a bit of different types of tools to produce volatiles, oxygen, which is great to breathe, hydrogen, which is great fuel, methane, which can be also a great fuel, and different types of other material and volatiles. Certainly water is the first thing that one wants to extract. So we have done a very large study for the CSA, and one of them was about what Canada can do as a leader in mining around the world. 50% of all the money that transacts into mining are transacted through the Toronto Stock Exchange. And so we are very well blessed in terms of mining expertise and operations of mines. So we've done a big study for CSA, and that meant checking from womb to tomb, what is the efficiency of all these processes, and select the ones that are more likely to be interesting. And we selected different places on the moon. First, regolith in the mare does not have much water. It has a bit of hydrogen that is being deposited by the sun, but it doesn't have any water. However, we found different ways in order to extract that water from the moon and recirculate and reuse the hydrogen in order to continue producing the volatiles. So that study is now done. We are pursuing on the second step that, and we are working with a technology that can operate anywhere on it. So it is squeezing water out of rocks. And that technique involves reducing chemically the material that you have in order to extract the oxygen that is everywhere in the soil, as most metal on the moon are oxidized. They're rust. We also work on the project with CSA, and we still are working a project to create nuclear energy on the moon. Again, the nuclear energy has a lot of applications, and most of them will be to keep the variety of rovers fueled at night and warm at night. And so the capacity of having a nuclear reactor locally on mobiles or radiating will be able to keep the flurry of robots on the moon. Every country wants a robot on the moon. The Russian failed 2 weeks ago. The Indian made it to the lunar pole last week. And so it's the onset of a large amount of different types of rovers that will be going to the moon and finding, refinding what I was involved finding is water at the poles with the Clementine mission, which is very, very much before the birth of all of you guys. So, and we also have an healthcare facility. We've been able to work on a system to provide health support for people, and that is one of the way we're doing things on the moon. So I'll show you a little bit of, hopefully I can get this thing to work. Yes.
Technology designed for space has a long history of benefiting life on Earth. From the GPS that you use to find your way around, to the Velcro on your kids' shoes, space technology has enriched the fabric of our everyday lives. But technology for space shouldn't just be for the future. It should help solve today's problems, like healthcare in the most remote parts of our country. With the financial support of the Canadian Space Agency, CSMC has developed a purpose-built, medically customized capsule that will deliver care to the most remote corners of Canada and beyond. As humans extend our reach into the stars, Canada wants to become the global leader in space healthcare. The Connected Care Capsule is a prototype that will be used here on Earth as a capability-building exercise towards the creation of a hospital that can function on the Moon or Mars. CSMC is an infrastructure company focused on solving big challenges in space by first solving problems here on Earth. And when we can deliver care in places where resources are scarce, we are paving the path to deliver care beyond our borders and inspire the next generation of Canadians.
And I hope you see my slides. Well, that's the problem with these things. You never know when they're going to start working. Probably my computer is like me, quite old. So hopefully I'll have the image in a second or two. And I started my career in very much in earth physics, geology, and so on. I am still involved. I'm a professor in civil engineering, mining, and geology at École Polytechnique. I teach also at UOttawa in sustainability and environment. and I am on the board of 3 other universities. But some of the experience I've had is to be involved in the nuclear program in Canada. This is a photo of a CANDU. It is, well, there's effectively 2 CANDUs on this one, but it is meant to produce, and produces about 40% of the power in Ontario and that is very probably the best capacity in furnishing energy that Ontario can have. So the fission power on the moon would be like the systems in Ontario, like the CANDU we have installed a bit everywhere when I was at the ECL. They provide a timeless approach. It's an holistic way of creating energy, and we already are working with something that has been regulatory approved to operate, and has been something that students have been working with for a few decades. One of the things we are trying to reduce is this. In the Arctic, there are enormous amount of very large 1 to 2 megawatts diesel generators. These diesel generators emit some CO2, but that's far from being the issue. CO2 is really bad in terms of climate, but the soot that is produced by these diesel device puts black carbon that is deposited on snow and ice, and that accelerates the melting of snow and ice. And incredible as it may seem, this soot is the foremost factor dragging us into a 1.5 that we essentially are at already, and possibly going to 3 or 4 degrees Celsius before 2050. So replacing those is very important. Finding a way to get nuclear energy at a size that could be replacing those at a cost that is acceptable, it is a very large factor. And so dual use is important for us in our vision. We see the devices helping us with the new NORAD, for example, in the north, providing a way to reduce energy and decarbonize the industry, and certainly on the moon provides a lot of access to energy and without having to unfurl square kilometers of solar cells, which is quite difficult to do. And that is more or less it. The technology we are devising is great, but it has a vision, and vision is important. Purpose is important, and vision and purpose is what's driving the Canadian space program. And I hope it will drive you in the future. And I'll leave you with this statement from Mr. Burhan. He said, "Make no little plans. They have no magic to stir men's blood." We could say human's blood. In order to avoid the sexism, but that is it for me. I thank you very much for taking some time to listen to me.
So just for your reference, I'm sitting in the back so I can talk to you through the computer and you can hear me properly. But does anyone in the audience have a question for Dr. Budo? I do have a couple ones that I thought of during the talk, and if you don't mind, Dr. Boudreau, I would like to ask you some of them. You present the integration of nuclear systems into space endeavors, which is an incredible opportunity and a unique challenge. Could you delve into the complexity you encountered, the various challenges you've encountered while leading this project, and how your strategic leadership helped overcome these hurdles and ultimately led to its success?
A very good question. The major issue that we have with nuclear is that it is nuclear. And there's been a scare in the 70s and the 90s about nuclear. There's been a few accidents. And I have to admit, there's never been an accident with the CANDU technology. And to a large extent, that left some sequels in people's minds. So first, nuclear is a problem. But NASA has realized, and NASA and the Aerospace Agency have realized, that within the ISEC-G, which is the architecture of doing things on the moon and far beyond the moon, we would need a large access or significant access to energy. Some of it could come from photovoltaics, some would come from concentrated solar, but that is not enough. And we should not deface the moon with extremely large solar panels. That is not going to be what people will appreciate on a summer night's viewing. So, so one of the problems is it's nuclear. The second one, well, the counter argument is that it was accepted. It is what people are interested in doing. NASA has let 6 contracts for SMRs, small modular reactors, to American companies. And Canada has one with us, and there's none in Europe. The reason why it's not in Europe is mainly the issues related to the nuclear itself, and the fact that it could be environmentally unsound if somebody places a big bomb under it. So the reactors themselves need to fight an uphill fight, which is providing a nuclear reactor on the moon. And if you build a new nuclear reactor, it takes 20 years to get certification. It takes 20 years to get it operational to a point where people feel it's safe. So we're talking about 30, 40 years to the next stop of putting a reactor on the moon. While the one that we're proposing is an older device that is well-defined, that is well understood in behavior, that is operated fairly easily, and can operate on its own for long periods of time, and is already approved. So that shaves a lot of time off bringing the reactor to the moon. And that's what's bringing us forward, because NASA is thinking that the 6th reactor in the States is going to be too expensive because they're new reactors and it's going to take a lot of time. So we seem to have the solution handy for that, and being able to position a reactor in the 2040s.
Amazing. And thank you for positioning not only your company, but Canada also on the map and on the moon. Well, Dr. Budo, this is the end of our allocated time, but thank you so much for presenting and taking the time to share your work with us today. And hopefully, amazing. We're signing back to you. We'll get the chance to talk again about fission power on the moon. Thank you very much.
Live long and perspire.
Absolutely. Thank you. Can you hear me well?
Hi.
Hi, Craig. Can you hear me well?
Yes, I can.
Okay, fantastic. So I'm at the back of the room just so you can hear my voice, but just for your information, you are projected in front of our audience and the student stands. So
okay, I'll behave.
We have here with us Craig Nordin, who's representing New Cycle Engineering LLC. He is a mechanical engineer with 30 years of experience in advanced design of jet engines and engine components at United Technologies, which is now Raytheon Technologies. After leaving UT, he pursued a PhD in mechanical engineering from the University of Connecticut and graduated in 2013. His dissertation is thermodynamics of a rotating detonation engine. He currently pursues research as a consultant under the name of New Cycle Engineering LLC. I'm very personally looking forward to this talk, as I've worked on RDEs before, and I'm looking forward to hearing what, Craig, you have to share on the subject. So the floor is yours, Craig, and thank you for coming today.
Thank you. Okay, can everybody hear me? Okay, can you see my slide, first slide? Oh, okay. Let me see, where do I do that?
So there's you should see a green button saying share screen at the bottom of your screen.
I got it, okay.
And then you'll have an option of different screens, and you can select the one you prefer.
Okay, let's try that. How's that?
We still can't see it. Can you maybe confirm? I think there might be a blue button saying OK to confirm.
Let me try. Don't see the blue button. Let me push this share button again. And it says host disabled participant screen sharing.
Okay, maybe
I think
give
that's
me
you.
a second. Okay, you should try again.
Okay. How's that?
1 second. We still cannot see it, unfortunately. Okay, Zach is coming. Oh, he can't share his screen.
Oh, I got a different screen here.
So what options? Oh, perfect. Okay, we are seeing your screen. We're seeing Zoom.
Okay, let me. All right, I'm bringing up.
Beautiful.
How's
There
that?
you go. With a beautiful video. Fantastic. The floor is yours.
Okay, good. I was a little bit concerned that the rate of internet linkage might chop it up a little bit, but
No, it's great.
if it looks smooth to you, we're good.
Very smooth.
Okay, these are two animations of rotating detonation. As you can see, the one on the left is actually rotating. And I just clarify that it's the wave that is rotating, not the particles. The particles follow a slightly different path. The blue animation is an unwrapped RDE, so it repeats just like an old-fashioned video game, going off the right and coming in the left. The high red colored areas is the actual detonation, in that it actually occupies a very small portion of this grid. The blue unrolled animation is a pressure gradient, and the one on the left is temperature. And what you don't hear is the sound. There is no sound on these because that's mathematics. And that's what it sounds like. Did you hear that? Oh.
So there should be an option to share your sound as well.
Okay.
So when you share your screen,
Oops,
you can click a check mark. So if you go back into share screen,
I lost the share screen box here. Let's see where to go.
It should be at the last fourth of your screen, towards the bottom, the middle. It should appear as you hover your mouse towards the bottom.
Oh, okay. Wait a minute. I got. I'm not sure I want to. Maybe I don't want to take the time to find it here, because it's giving me a different screen.
So if you allow me, I can stop your screen sharing.
Okay.
And I will stop my own screen sharing. So now you should be able to share screen again. If you look at the bottom of your screen, the green button.
Yep. Okay.
And
Screen
then
share.
there should be an option to share your sound as well.
Okay.
At the bottom left, you can click the check mark.
Okay, I see it.
Beautiful.
Good. Zoom. Enter your password to allow this. Oh, is that my personal password, or is that the code password? Let me try my.
But if it's too complicated, unfortunately, maybe for the sake of time, we can go to the next slide, and because now I think we just lost your microphone. Can you maybe say something for us, Craig? Yeah, unfortunately, Craig, I think we've lost your microphone. So if you still hear us, can you revert back to the previous setting, and we'll just continue the presentation for where we left off.
All right, we're going to have to forego the sound.
Okay, that's perfect. So if you can just share your screen again, and we'll be able to... okay, fantastic. So, oh, we can hear it.
Okay, did you hear anything there?
Yes, a very loud screech.
Ah, yes, okay, that's what it sounds like. They're very noisy. So this was a 3-inch RDE that's operating at AFRL in Dayton. The RDE is it's a pressure gain combustion. It is a complete thermodynamic cycle. It can operate on its own without any help from any precompressor. There's no moving parts. The compression, combustion, expansion, all packaged in the detonation, and we have confined it to a racetrack, which is evident from this high-speed photograph looking down the exhaust of this this detonation machine. So, next one. A little background. This is a clip from a movie of the testing of the Saturn F1 rocket engine early on, undergoing a rapid unplanned disassembly. And every big rocket manufacturer goes through this. They blow up rockets all the time. And nobody's really figured out a way to not do that. So I would look at this as trying to tame the dragon. And if you know about the Saturn F1, you know that what happened was that there was an acoustic instability in the combustion chamber that they eventually tamed by adding a series of baffles inside the combustion chamber, which damped out the oscillations. So there are reports and opinions that this acoustic instability was actually a rotating detonation. And I've seen some pressure traces that suggest very highly that that's exactly what happened. But this is what we're trying to do. We're trying to tame the dragon, and we're trying to gently wake him up again. We don't want to damp this oscillation because the detonation is a natural outcome of this acoustic instability if you let it go long enough and it doesn't blow up your machine. So the whole exercise of doing this is to get a lot more efficiency than we would otherwise. Why is it important? Because every time we've come up with a new heat cycle, it seems to define an era of civilization, starting with horses, going through sail, steam, and the Industrial Revolution. Every time we came up with a new cycle, we could travel farther in a shorter period of time or farther in one day going. Steam engines could, the best in class was the Flying Dutchman going 400 miles a day. And by ship, 725 miles a day. When we got to piston engines, we could fly this 5,000 miles in a day was the best in class of the Lockheed Constellation in 1953. Today, we can go 11,000 miles on the Airbus A350 if you want to sit in an airplane for 19 hours, that is. So, and the Brayton rocket got us to the moon, so that's 52,000 miles in a day. So the rotating engine is going to add to this, and we're talking potentially anywhere 1 to 20% increase of efficiency is the general estimate for what that is going to provide. And this is actually a curve that shows where it comes from. It's a seminal curve that is used in a lot of papers by Heiser and Pratt, plotting thermal efficiency and temperature ratio on the bottom x-axis, which can be interpreted as compression ratio. So these are ideal cycles up at the top. They are asymptotic to 100% efficiency, which we never get to because we can't go up that high in temperature. And if we add component inefficiencies, like a 90% compressor, 90% burner, 90% expansion or turbine, we get these, and we lose half of that energy. And the curves change and they shift, and at the high temperature ratios, the crossing of the PDE or RDE curves and the Brayton cycle curves suggest that the Brayton cycle is more efficient by a little bit at those high numbers. So this can be divided into small engines and large engines, roughly speaking. And the small engines, in this area, we have like a 2-to-1 compression ratio on the left. That's like a turbocharger. Microturbines can operate with 4-to-1 overall pressure ratios. And at that point, you can get a 50% increase in thermal efficiency. You go up a little higher and these curves start to close in on each other. And a lot of small engines have a 10-to-1 compression ratio, and you might be able to squeeze out 20%. That's still a huge number. But as you get up to the large engines, the big commercial engines and the big rockets are up on the right-hand side of the curve, you're going to have to squeeze out a small percentage, but that small percentage can still be worth it, especially in ground power gas turbines, where they're running 24/7, so any efficiency increase is going to mean a lot. And when I worked at Pratt, they said if you could show that we could get 0.1% of increase in efficiency, we'll give you a promotion. So it's still worth it to go after these small numbers. It's interesting, on the left, the Brayton cycle has a 0% efficiency at a temperature ratio of 1 or a pressure ratio of 1. So there's no pre-compression, and it still can operate. This is the theoretical line that says this can operate without a pre-compression. So that's a self-aspirating, and it's been done by the Russians, by the way. So there are, in the cycle business, it's a very risky business. As historically, out of this list of 16 cycles, only 4 are world beaters. The Rankine steam cycle, which is also used in nuclear power, the Brayton, the diesel, and the Otto. The diesel and the Otto are technically pressure gain combustion, but it's taken a long time to get to these cycles. The Brayton gas turbine cycle, the first modern configuration as a patent came out in 1872. The first to power was an 11 horsepower gas turbine by Elling in Norway, 1903. So the first to flight was von Hohen in 1939. So it's 67 years from the concept. For the RDEs, the first RDEs to fire were by Wojciechowski in the Landtrev Institute in Russia, in Siberia, and Nichols at the University of Michigan. So we're 62 years later, and I figure we're kind of right on schedule. My gold standard is what Arthur Clarke said about the space elevator will be built about 50 years after everyone stops laughing. So it takes a while to get these things up to speed. So be patient. Which brings up this question. What do you want to work on? You're a young engineer. You're trying to make a way in the world. Do you want to work on something that is solvable and doable, or do you want to work on something interesting? After I left Pratt, I had the opportunity and the flexibility to work on something interesting. So this is a question for you, because our world is burning and we need you guys. So there's a number of detonation engine types. These are the ones we know of so far. The AFRL designed a 6-inch RDE and it's shown here both with an aerospike and a convergent divergent nozzle. You can notice the Mach discs that are up there. And if you see Mach discs, you know that this is putting out some serious energy. This has been copied by a number of labs, and it's operating in a number of universities. So this is pretty much our gold standard right now as it stands. One interesting configuration is a radial or disc RDE, where the flow is actually inward or outward. And the hope is that they can make a very compact RDE and integrate this with a turbine. There's also a hollow or centerless RDE that's got a lot of attention, because the center body that is up here as a plug is actually a big pain in the ass. It has to be cooled, It's going to see a lot of heat. It's something that we would just as soon do without. But that, whether we can do that or not, is up for grabs at this point. There's a pulse detonation, and this was actually flown. Yeah, I'll show you a clip of this by the FRL that they designed and built this airplane. And there's a thing called a wave rotor, which is a little bit different than a detonation. Rolls-Royce has put a lot of research into this machine. And there's an oblique shockwave detonation where the detonation sits as a standing wave in the engine bay. And there's some talk about making a hypersonic RDE, but I don't think anything has quite seen the light of day on that yet. So this is the airfoil that was shown at Oshkosh in 2003. I don't know if you could have heard that, but I certainly did, so I didn't try to talk over it. You can see that it works. We can develop thrust. It makes a fair amount of noise, but not enough to bother the pilot too much. So how does this work? The RDE is fed from the bottom, and the exhaust comes out the top. The wave is moving from the right to the left. There's a number of features in here which are basically parts of the RDE. There's a blue area down there which is unburned gas. We call that the fill zone. The detonation is the short side of this triangle right here. And this fish scale pattern are the transverse waves, which are the beating heart of the Dragon. I'll show you something about those in a minute. And up here is the triple point, which emanates an oblique shock and a shear layer, which creates a shedding vortex shear from the new combustion. The products of combustion come out here. They are new and they are expanding and they're interacting with the old products that have circled around back and run into this oblique shock. So this is pumping up and energizing the gas, and it expands out the back. These two arrows in the exhaust indicate that there is what we call a swirl. There's a rotating pattern of azimuthal swirl that goes with this exhaust, and is actually a loss in a certain amount of loss in performance to have that swirl, and we're wrestling with that as a factor. So this is what the cycle looks like. I won't go into a lot of detail, but I can show you a little bit of it. This yellow area you might recognize if you've studied the cycles as a Brayton cycle. You get a little bit of compression here. You have constant pressure coming up here to a point where you start the expansion, and then you get ideally isentropic expansion here. This is an ideal situation. So this is actually the useful work you can get on the Brayton cycle. The detonation starts with a little bit of pre-compression in this case. There's a shock that compresses the flow. We add heat. We come up to this point and we expand. This expansion here is not recoverable. This expansion, just like a turbine, is going to power the shock. There's also an expansion, believe it or not, along the combustion. This is actually a drop in pressure along this line, so this contributes to the expansion plus this, and that expansion work goes to power the shock. So we get an energy balance at the same enthalpy or temperature approximately as the Brayton cycle. So what happens is we get more energy, more useful work out of that because we're farther to the left on the entropy curve. So making this work is all about the entropy. This is the transverse wave to show you how that works in a little bit more detail. It's set up just to study the transverse wave. And you can see there's a beating heart in this Dragon, and it's very organized and rather complicated. If you put what's called a smoke foil in a detonation tube and let this rip down a tube, you get this fish scale pattern, which you also saw in the previous one of the previous slides. And it leaves this trace where the high pressure point moves the soot around on the foil. This is actually a digital smoke foil. But this cell size is a measure that we need to know what the cell size is, because that has to be compatible with the geometry. So you can see there's a lot going on in this detonation. It's quite complex, but it's very organized, and that's important because that means less entropy. One of the things that we can do for analysis is look at average properties, and we can put streamlines through there and see how the average particle will move through the wave relative to the wave, and we use this vector transformation to do this. So this shows that there is a pattern of fill, and this black line is a representative, comes through the detonation, gets energized, and then starts to expand and move up the line, comes around the other side, and then exits. Some of these lines, particularly the ones below here, come around the other side and get swallowed up by this oblique shock wave, which re-energizes the flow, but also adds a little bit more entropy because shocks will do that. So using those streamlines, we could then extract what the cycle is actually doing and compare it to the theoretical cycle. This is a PV diagram on the left. The gray line is a theoretical cycle of the shock coming up here, and then the expansion. This is the expansion during combustion, and then the rest of the expansion goes down through here. So the streamlines are roughly approximating this shape. It's a little bit different because there's some things that happen in trying to digitize a shock, which have a thickness of only a few mean-free paths, molecular paths thick, which makes it pretty impossible to drop a grid, computational grid on the shock. So there's a lot of tricks that have to be done to model the shock. You can't use the grid to do that. That has to be done mathematically in each cell. TS diagram on the right, and you can see the gray line is the theoretical, and we match pretty good the theoretical line, except we get these other lines in here. This is the oblique shock. There's some deflagration that happens along the fill zone and more complications like that. So it's not exactly the theoretical curve. Mixing is a problem. If you look at this as a rocket, the way you get the reactants into the chamber mathematically on our simulations is the upper one is called an ideal simulation. So we do this little cheat where the injection system is actually a boundary condition along the lower line. So the injection holes are really just mathematical, and we are injecting 100% premix of hydrogen and air, or in this case it's air, or whatever fuels and oxidizers are using. So it comes out ready to go and ready to detonate, and it produces a very well-behaved detonation. This dragon is caged and he is behaving. But what really happens is something like this, is that if you have an injection like happens in a rocket where you have separate injectors for oxidizer and fuel, that has to mix in the chamber. So there's a little mixing zone down at the bottom before anything happens. And it elevates the detonation and actually lifts it off of the injection plane. And as you can see, it creates a much more complicated and very different wave structure than is in the ideal system. So this dragon is kind of on the edge of existing. If we tweak our mixing parameters just a little bit more than this simulation, the simulation will fail. So this is on the edge of doability. So this dragon is about to become a real drag if we do the mixing wrong. If we have a better mixing, what can happen is that you can get a deflagration attach itself to the injection, and we don't want that either. We want it to detonate. We don't want to waste a lot of energy actually just doing normal deflagration. Yeah, I'm almost done. This is the last slide. I'm going to leave you with this, and this is courtesy of Nagoya University and the professor there, Hiro Kasahara. July 2021, they launched an RDE off a suborbital rocket over the Pacific. You can see the Earth in the background, and you can see an operating RDE doing its thing. So this is a historic first for RDEs, and I'll leave it right there.
Amazing presentation, Craig. Thank you very much. I think your presentation resonated with a lot of people in the audience here, and some are already lining up for questions. So we have time for one question, but we are thinking of maybe inviting you tomorrow over lunchtime to continue this presentation and talking some more RDE, because a lot of people here relate to your experience.
Okay, you can do that. You could email the details.
Perfect. Okay, so we do have a question for you if you want to just ask it in front of the computer.
You mentioned that we put the detonation into a racetrack, that being the annulus. Does the racetrack have to be angular, or can it be reshaped? And follow up, how would that affect things like cooling? And follow up to that, with it being a pressure gain cycle and there being less energy lost to cooling, or less energy lost to heat, does that make the cooling of the walls more efficient compared to a regular combustion chamber?
Good question. Yeah, thermal management is a big problem because this thing runs hot. And the heat fluxes are barely manageable. It can be done with a water jacket, but for a flying machine, you probably don't want to do that. So there's a lot of thermal work to be done. Your first question, does it have to be circular? No, it does not. I've seen some work, Koreans did some work with oval tracks and some other tracks that were not at all circular, like a star shape. And what they found out is that the detonation has a little bit of difficulty turning the corners. So it did slow down the detonation. So I think it might create hotspots in the corners is possible. There has been other work. If you look in the literature, I'm sure you'll find some racetrack work. One possibility is that there was one configuration that I didn't get into my slide because I was running out of space. There is a linear detonation configuration where you can create basically just one part of the racetrack and make it linear. And what will happen is that the detonation gets to the end of the racetrack and it reflects off the wall and comes back again. There's work on that and some mysteries exactly as to how it works, because what happened was not a detonation coming off the back wall, but certainly a wave, but it actually restarted the detonation back in its originating end. So that's a very interesting way to look at it, and it got a lot of attention when it was first demonstrated. I think the University of Florida was working on that.
Craig, I'm very sorry, but unfortunately we have our next speaker in the waiting room. But like I mentioned, I think a lot of other people have questions and more follow-ups from the last person asking questions.
Send me the details on lunch, and I'd be happy to be there.
Fantastic. We'll be happy to have you over. Have a nice evening, and thank you a lot again, Craig, for your beautiful presentation.
Thank you very much.
Looking forward to hearing you speak again. All right. Virtual, but coming from McGill University, we'll have Matthias Nesset, and we will be introducing him shortly.
Yes, I can.
Beautiful. Can you say something for us?
Hello, everyone. I'm
Okay,
Matthias,
awesome.
and I'll be
The sound is great.
Perfect.
Beautiful. So we're a few minutes late, and so I'll jump right into it. So for your information, you are currently being projected in front of the student exhibit as well as our conference room. So I'll shortly introduce you. Matthias Nesset, coming from McGill University, is a current PhD student in the Faculty of Dental Medicine and Oral Health Sciences, focusing on cardiovascular health in humans and rodents in space. He completed his undergraduate degree in biomedical engineering at the University of Alberta and spent the last 6 years doing various kinds of research, from improving medical devices for babies to studying health outcomes in astronauts. He plans to eventually go to space and conduct his own experiments there. So welcome, Matthias Nesset, and please, the stage is yours.
Thank you, everyone. If you don't mind, I just need this ability to share my screen.
Yes, here you go.
Perfect.
And if you have a video, make sure to maybe share your sound, your computer sound.
Okay,
but we can see your
good.
slides. It's perfect.
Okay, perfect.
All right.
Let me just get my pointer ready. And perfect. All right. So, hello everyone. Thank you for the introduction, and thank you for coming to my presentation today about space physiology and its relevance to future space travel. I was going to start today by going over what I will be talking about. First, I'll give you a bit of an introduction into the background, mainly talking about my training and experience both with space studies and in medicine. Then I will dive into what exactly space physiology is, which will both include concepts that will hopefully help you build the definition for this term. Next, I will talk about some basics of scientific experiments, which may be more of a review for some of you, but a refresher never hurts. Then I'll move over into more of the spaceflight models and how experiments can be done in other ways than just actually in space. After that, I'll look at some of the types of studies that can be done and how important each one is and how they're relevant to different areas. And then finally, I will go into some examples of the studies, what they found and how they actually have future implications and how they're affecting current life out in space. So to start, a bit about myself. I'm an engineer by training, as was mentioned. I completed my undergraduate degree at the University of Alberta in the mechanical engineering stream with a focus on biomedical engineering. During this time, I had many experiences, including over 4 years at a research lab in a neonatal or premature baby lab. This research mainly helped me focus on two main things. One, medical device development, which came in the form of modeling resuscitation masks and integrating real-time force and pressure sensors to help improve medical devices. And additionally, I got to work on some studies that improved chest compression techniques and oxygen and airway flow delivery systems, which helped introduce me to the area of research and getting my feet on the ground in this section. While this mainly focuses on my medical background and where I got my medical training I also had plenty of experiences during my undergraduate time with several space clubs. This was including the undergraduate astronomy club, where we would do weekly or monthly events looking at stars, going out stargazing, so on and so forth. But more specifically, I was actually also a part of a group called AlbertaSat. This is a group based out of the University of Alberta, where they had previously developed a satellite or a CubeSat, which is a small satellite, and sent it up to space. We were a part of the second version of that team, so I got to help work on a CubeSat, which was actually recently sent up to space a couple months ago, and it's up there to help monitor forest fires. So yeah, I got to participate in a lot of the conceptualization, the designing, and building this functional CubeSat. Now, looking at me currently, I'm currently in my third year of studies in the PhD at McGill University, like I said. Though this is technically through the Faculty of Dental Medicine and Oral Health Sciences, it's a bit different than engineering, but there's a long story to it. Mainly, all that I really want to get at is that I am still doing biomedical engineering work through this program. But now, if you want to look more specifically at my project itself, my project that I am working on focuses on cardiovascular health during microgravity. To do this, we used a method which is known as a citizen science approach, where I am currently managing around 25 young professionals from around the world, from various backgrounds and various levels of education, who are helping to analyze literature data to perform high-level reviews. And you might be wondering what a high-level review is, and I'll get to that in a little bit. But this project is actually recognized through NASA's Ames Life Science Data Archive, or NASA ALSDA, and their analysis working groups as the Solstice program, as you can see here. So now you might be asking, after all that introduction, we want to get into the actual stuff. Okay, so what is space physiology? So while the two terms are quite recognizable on their own, space and physiology, when joined together, it can be a bit more confusing. But in short, space physiology describes how the body adapts and changes to the stressful space environment. And I'll talk more about these specific stresses in future slides. In a way, the space physiology is a type of preventative medicine, as a lot of the studies that are being done are studying on the effects of the body in this new environment, in order to prevent any significant changes that can disturb regular human function. This is particularly important when we start looking at longer and further manned missions, as humans are constantly curious and we want to keep exploring, and so we really want to understand what goes on in the body long term if we want to move further. Alright, so although there are many aspects to space physiology, I want to look at just some of the levels that are there. So here you can see biology, and it's divided into three main systems that I found to be most reported in my work. First, we have the multicellular systems here. These effectively describe the various interrelating systems of the body, such as, the cardiovascular system, so all the blood flow and all that. The lymphatic system, so this is more of your immunity, and there's various ways that this immediately ties into the cardiovascular system and other systems as well. And finally, one that you might be more familiar with is the nervous system, so spinal cord, nerves, brain, all that. Now, another one of the main subdivisions that I see quite often is cellular interactions. So quite often you'll see, cell cultures or cells sent up into space to see how they interact with microgravity and so on, and just the spaceflight environments there. My work particularly is more focused on larger systems and whole bodies, so I won't be talking as much about this, but I just wanted to make note that it is there and it is something that is being done. And finally, the other big thing that I find most reported is reports on multicellular organs. So here I've just listed two, muscle and bone, mainly because these are the two prevalent thought of and mainly reported ones that appear in spaceflight studies. As some people might notice that, or might have heard, years atrophy. So what this means is when you go to space, you lose kind of the gravitational force, and this actually prevents your muscle from growing and does the opposite, and you actually lose quite a bit of muscle mass, and same thing goes for bone. So now now that we looked at kind of the background for space physiology, I want to kind of shift a little bit over to how space experiments are done, mainly because I'm not sure how many people are familiar with this. Like I said, this might be a refresher for some people, but I just wanted to kind of touch on this topic. So any research question should be able to fit within this framework here. This is called the PICO framework, and it stands for P is population, I intervention, C comparison, O outcome, and T is time. So these words, or this abbreviation, effectively helps frame a question into being as clear as possible, and it allows you to conduct an experiment in a thorough manner. So as an example, just to kind of reinforce this descriptive method for the research and conducting experiments, I went ahead and put together some terms to kind of fill this out, just to give you an idea of what this might look like. For the population, you could say humans. Another way you could put this is astronauts or space goers, something along the lines, but have a defined category of population. The intervention, in most cases, you could say spaceflight, but usually you'd want to go a little more specific, such as microgravity, because as I'll get to later also, you'll see there's many different factors going on in spaceflight. Usually a comparison group, you'll almost always have a ground control or a group that doesn't receive whatever spaceflight treatment you're giving. So it's called ground control because usually they don't end up receiving the microgravity. Otherwise, you give them all the same treatment, all the same diet, whatever, depending on what you're studying, and you will try and directly observe the effects that are just due to whatever your intervention may be. Next, we have the outcomes. Here, because my work is being done in cardiovascular outcomes, I just put cardiovascular effects. One thing you can put here is blood pressure, so that's just one example of one thing you could look at. Another, muscle mass, bone density. The list is extensively long. And then time. Again, I just put a 14-day flight just to be simple, but this can range from anything from like 10-day flights to months to, any period of time for a flight that you want to study. But it is quite nice to have because it helps you quantify and normalize values against each other. Because clearly, if you have a 10-day flight versus like a 2-month flight, you're probably going to get different values, so you're going to want to have to control that in some way. So now, with all this information here, we can start to build a research question, which would look something like this down here. So something along the lines of, does 14-day spaceflight affect cardiovascular outcomes in humans when compared to ground control? This is a very preliminary research question. Again, it was put together with some of the terms that I threw together. Obviously, you could refine it, make it more specific and all this, but this is kind of what you'd want to be aiming for when you're looking to do this experiment. And then you could start to actually design your research and then submit it and do the experiment itself. So now, with the basics of the research done, I want to quickly mention some of the main spaceflight risks that I've been alluding to as noted by NASA. So the first one on the screen here that you can see is one that I've already talked quite a bit about, and I find it's usually one of the most common when discussing the topic of spaceflight is microgravity. Because when you go to space, as most of you probably know, I'm assuming, there is no gravity, and so that drastically alters the way that things are being done. So next, another common spaceflight risk is radiation. There are many different forms of this, and its effects on the body, both short and long term, are being extensively studied. I'm actually part of another group where we're starting to look at the effects of radiation on cardiovascular health, but this is a very difficult topic because it's hard to isolate specifically for spaceflight radiation in these environments, which is why this area is still being worked on so much. Finally, the three other risks are a bit less intuitive, but still very important, and I've actually just been coming to learn these more over the past 2 years through my research, but it's very clear to me now why they are relevant to spaceflight physiology and spaceflight research. So here you have hostile enclosed environments. As any sort of space travel is very stressful because, if anything goes wrong, it kind of has to be fixed then and there. You can't really delay with it too much, and it's very kind of life or death scenarios quite often. Also, with the closed environments, astronauts are typically forced to kind of stay within bounds of their spacecraft, so they can't really go too far. And the way that I kind of think about it too is it's almost like the quarantine from the pandemic, but turned up 1,000 because you really don't have the option to even go outside in most cases. And then next, there's the isolation and confinement, as communication with other people beyond the spacecraft isn't always easy, and this only accentuates the longer the flights or the further the flights go. Because people are only really able to communicate directly with, that small subset of people that they're on the spacecraft with. And finally, this is one that I never really thought about, but it's become more and more prevalent, is the distance from Earth. What this means is that, the longer the mission, or the further rather, the harder it is to resupply or even just obtain necessary items that would be needed. So this really accentuates the need for appropriate planning, looking ahead of time, having all the research done so you know what you're going to need, what changes, you can anticipate what might happen, and a sort of self-sustainment of the spacecraft. So now, as I'm sure you know, spaceflight experiments themselves aren't exactly easy. They're quite costly, difficult, because if something goes wrong, there's not really an easy quick fix to it. You can't go change the batteries maybe, or change part of your system. You might have to ask one of the astronauts on board to do it, or if it's on its own self-sustaining, say like the satellite, it's kind of that's it, that's all. So this also makes them quite rare. Just to put this into a little more context, NASA reported a couple years ago that it takes approximately $10,000 per pound of payload to be sent into space. So as you can see, that can really start to add up quickly, because just even with all the basic electronic equipment, monitoring devices, and everything, you might something even as small as say 5 pounds can start to be like $50,000, and that's just not even considering what the actual work going into it does. That's just to get it up there. So the actual work in doing all that and preparing is going to cost more. And so this kind of begs the need: are there alternative solutions that can be used? So for this, I will say yes. So there's many different models that can be used to simulate space travel, space flight experiments, so on and so forth. There's like lots and lots, but the main ones I want to focus on today will be these 5, as I find these are kind of the most prevalent, especially like I said in my work. There's human models. So what this means is obviously there's the actual spaceflight model, but there's simulated methods, which I'll get to in a bit. Same thing with animals. There's animal models that you can use, because typically getting a human study done is a little difficult, so you have to go through processes to get it done up to human level. There's computer models. These are more mathematical and theoretical, so these will build off previous data and try and make predictions about what's happening. There's isolation. This has to do with being isolated in that area for a while. And then cellular models, which I'll acknowledge but won't talk too much about. So talking about the human models here, we have 5 main ones. Bed rest, which you can see up here. This is mainly, you just lie down in a bed for up to weeks at a time. This helps remove the forces from your body, which helps somewhat simulate the microgravity effects. To add on to this, what they do is they also add head down tilt. So as you can see, his head is tilted downwards a little bit here. This will come to various degrees. This also helps to simulate a fluid shift that goes on in space, which I'll talk more about. There's parabolic flights. So these are where you have an airplane which climbs and drops very drastically several times during flight. And what this does is at the apex of the parabola that it performs, it effectively gives the people inside very short-term actual microgravity, so 20 to 30 seconds of microgravity, where you can start to look at some short-term experiments. One that I know was done looked at the blood flow in the jugular, and they found that it actually, in some cases, the flow actually reversed and started going back towards the brain, which is not good, but studies are still being done. Finally, there's immersion and dry immersion. These are kind of just imagine just putting yourself in a pool and you're floating. This helps remove the forces from your body, and dry immersion is the same idea, but it's kind of covered, so more of a waterbed type thing. Animal models. Here you have 3 main methods. One is hind limb suspension. So this is where you lift up the animal by their tail to remove all the forces. This kind of promotes the idea of like disuse and again, less forces being put on the legs. Immobilization is the same kind of thing. This can be done in several ways. For example, here, using a cast to prevent the animal from using that leg, or there's other ways that are being explored now, including Botox to help immobilize the muscles. And then doing this, you can load and unload to see how various loading schemes can affect muscle growth or prevent muscle loss and bone. Next, there's the isolation model. So these have to do with confined environments. Typically, this will be, a lot of studies will send people to remote areas, such as Antarctica. This picture here is actually a recent study in NASA, where they sent 4 or 5 various professionals. They have them in a Mars-like container, where they will be working together. They will be spending just over a year to simulate the isolation conditions of Mars. And funny enough, you can actually even do studies on cardiovascular health. My work is not related to this because I'm more microgravity. See, this is where it's actually important to specify in the intervention methods that mine would be microgravity as opposed to just spaceflight. Because even in isolation models, you can get changes in blood pressure and stuff like that, which can also start to add to the effects of space travel. Now, looking at some types of studies, I've been primarily talking about the primary and experimental, so I'm sure this is what most people are kind of familiar with. It's these direct studies where you look right away. But a lot of my work actually has to do with literature review and data mining. So what this is we look at the sum of all these primary and experimental experiments, and we kind of compile them all into one to make one large experiment with a more generalizable result. So just a quick overview on literature reviews themselves. So here, as you can see, you have kind of the primary experiments themselves being done with cohort studies, case reports, randomized control trials, just methods being done to obtain the data. Now the systematic review and meta-analyses are kind of deemed as the top level of publications, as they not only do they summarize the most amount of data, but they help reduce the bias in all these studies by, you know, comparing them across each other, normalizing these values, and helping you to get out the most generalizable result, as I was previously saying. In a quick way and short, an analogy that I like to have for this, that I actually learned from some people that I was teaching this to, is kind of a crime scene. So a literature or systematic review and meta-analyses allows you to compile information from many studies. So what this does is kind of each experiment would be, you know, each point of evidence here. And then what you do is you compile all these evidence points together to, you know, get more information about what's going on. This allows you to increase your population, and then you can make, you know, once you have all the evidence together, you can then figure out who did the crime or whatever it may be. And so in the same way, you can look at all the data, find all your different data points, and then put them all together and figure out your generalizable conclusion from the results. Here we just have a quick showing of just the different types of reviews. Again, systematic review and meta-analysis, as it's the highest one, it's obviously the slowest, it has the most explicit methods, low risk of bias, which makes it, you know, that much more important for drawing these conclusions. And then I'm going to end with a few examples here. So for example, some studies here, like I had previously mentioned, bone and muscle were quite commonly studied. Bone, you get a lot of disuse in space, so the resorption of bone exceeds the growth. One study, or one meta-analysis showed that there was about 25% decrease in trabecular and 6% decrease in cortical bone here. In case you didn't know what those are, these are the two various parts of the bone that I'm talking about. Cortical is the hard outside, and trabecular is the spongy inside part. They also found that there is usually more bone loss in lower extremities, so you typically tend to have more of a bone loss in your legs than you would your upper body. And generally, you don't, even after astronauts return, they never fully return to their pre-flight levels of bone mass. Even though they can start to rebuild them upon return, it never gets, you know, back to that exact level. There's still always residual loss. Same kind of idea with muscle, you know, disuse, same thing, you decrease muscle mass. Even in just a flight of, you know, 5 to 11 days, some studies found that your muscle mass would decrease by about 20%. So this is quite concerning and something that really needs to be considered, you know, moving forward and looking into these long-term space flights. Looking at cardiovascular health, so this is again what I'm more fluent with. So you have this fluid shift. So here, you know, this is the regular pressures in your body. But when you go to space, you lose the gravitational effects, so fluids start to shift more upwards to your head. And this is where you get something called puffy face syndrome or facial puffiness. A lot of astronauts get this, and it's just swelling in their face from more fluid being there. Additionally, upon return to Earth, you get what is known as pre-syncope or fainting in astronauts because of the drastic change in blood pressure after when you're resubjected to the gravitational forces. However, something that's quite interesting, and it's still not understood why, but almost pretty much 100% of females that have gone to space will experience this pre-syncope and fainting when they come back, but only 20% of males do. So females are 5 times more likely to faint than males, and no one really knows why yet. And then finally, another thing that can happen is cardiac mass can decrease by about 10%. I believe this was in a longer-term spaceflight study. And not only that, but the actual shape of your heart changes, because generally your heart's a bit of an oval shape, but because of the lack of gravity, it starts to shape more into just a round ball. So as you can see, there's pretty significant changes that are going on within the body, even in very short-term flights. So study implications. So these studies have help show that, you know, astronauts need to exercise up there to prevent any muscle loss, to prevent bone loss and all that. So right now it's recommended they do about 2 hours a day. This is quite a lot, because even if you think about it, 2 hours a day for an astronaut can be a lot, given all the other work that they have to do. a lot of their work is mainly treadmill running and stuff like that, but they do also incorporate a little bit of resistance training. Again, this is very different because they can't really just use weights because there's no gravitational force. So the resistive machines really have to be developed for these guys. Additionally, one of the main things, the cool things that I think about spaceflight research is that it does actually impact life here on Earth. For example, one of the big topics was the distance from Earth and, you know, making sure how to get them access to resources when they're not able to get access to them because of how far away they are from the Earth. But this idea can actually be applied to remote communities. So for example, say somewhere up very north in Nunavut, you have a remote community that needs medical supplies or something. The spaceflight research that goes into looking at the distance from Earth can be applied there as well, as in a very similar method. They're, you know, hundreds of miles, hundreds of thousands of miles away from, you know, the big city where all the resources are. So even spaceflight research extends beyond just the space and can be used practically on Earth. So just to conclude, we talked a bit about space physiology, how the body adapts and changes in the environments. We went over the 5 big NASA spaceflight risks, which might not be intuitive, but they're always good to keep in mind. We looked at the different experiment types, you know, simulated actual, the different models, human, animal, computational, the types of studies, experimental, and then there's also literature-based, and we did some of the findings. Finally, I'd like to acknowledge some of the members of my lab who helped me do all the research I do and helped me get into this position, and some of my collaborators at various institutions. And finally, I'd like to ask if there's any questions.
Congratulations and beautiful talk. Thank you for sharing your work today and all your experience in space physiology. So, do we have any questions from the audience? If you want to ask a question, I recommend coming to the back so we can talk directly into the computer and the sound quality will be the best. Otherwise, I do have some questions for you, Matthias. I think we have time for maybe one question considering it's 2:29.
For sure.
So, oh, okay, no questions? Okay, perfect. Right, sorry for that. You talked about space physiology and your work within literature reviews and condensing all that information to understand the greater impact of microgravity on cardiovascular health. For a visual audience, would you provide some examples of some concrete examples of the work and research you've done and the impact of this research on the lives of our astronauts?
Okay, very good question, because that's one thing that happens a lot in research is you'll do some work, but it's hard to get actual results because you can always publish something and then you're not going to see where it goes or something. But like I was saying, so one thing that I've been working on and that I've been doing on the side as part of my research is, as I was mentioning, there's a lot of this fluid shift going on. And so one thing that's directly kind of resulted from that is astronauts now will, when they're up in space, they start to incorporate, they're called thigh pressure cuffs, or I don't know the exact name, but effectively what they are is they're a small cuff that you can put on various parts of your body, typically, like I said, the legs, because you want to keep the pressures down there. And what they do is they help regulate and compensate for this lack of gravitational force by directly changing the pressure on your legs through squeezing. And so this has, studies are still getting quite early on this, but it has been shown to reduce these pressures and actually seems somewhat to be helpful with all this facial swelling and all the puffiness that I was talking about.
Matthias, thank you a lot for this beautiful presentation and this answer. We unfortunately ran out of time, but hopefully we'll be able to have you on another time and talk some more about space physiology. So once again, thank you a lot, and hopefully we'll be able to talk soon.
Thank you for having me.
Have a nice evening. All right, so it is now 2:30, which gives us a 50-minute break before our next presenters, which will be UVic Rocketry and the Queen's Rocket Engineering Team. And then we will be concluding this first day of the Launch Canada Conference 2023 with Jeff Thornburg of CDL Space Stream, as well as our main sponsor, Dave Mann from MDA. Thank you very much, and looking forward to the rest of the day. Sorry, I forgot to mention, the break is 15 minutes, bringing us to 2:45 for when we come back. Thank you very much. Okay, so welcome to this last part of today's presentations and this part of Launch Canada's conference. So for this last part, we will be starting with a presentation by a university team here, University of Victoria rocketry team. As a short introduction, UVic rocketry was founded in 2016 and has been made several appearances at Space World America Cup, placing third in the basic category in June 2016 and placing first in the payload challenge in 2017. Last year, the club placed second in the basic category at Launch Canada. So today we'll be presenting the ground support live data visualization by Chris Lemieux. Chris is a fourth-year computer engineering student at UVic and leads the development of their ground support application. Everybody, please welcome Chris. And just speak in the mic because you're being live streamed.
All right. Alrighty. Hello, everybody. Good to see a couple people here. As we said before, my name's Chris, fourth-year computer engineer at the University of Rocketry, University of Victoria. I have been working on this project, ground support, for the last 8 months. I've been working closely with our software team to develop it. Yeah. I think I forgot the mouse, so I guess next slide. Oh, it's right here? Oh, yeah. Push on it. All right. So currently, UVic Rocketry, we store all of our post-flight data in CSV files in GitHub repositories, and now that isn't very useful information. So in the future, we are trying to get it into a database system of a custom software that we can use post-flight analysis tools on, so we can actually use this CSV data in a useful way. Because right now it's just kind of sitting there, not very available to everybody. Only people that know about it use it. So that's one of the main motivations for this project. Yeah. All right, so just a little bit of summary here. Our first main motivation for this tool is because it was our last ground station was very out of date system, and it wasn't even used at our last competition, even though we had it there, because we had battery overdraw, which led to it not being used. So what we did is we used a computer with a RTL SCR USB stick. It attaches directly to our antenna with a coax cable. And then from there, we learned our ground station was just a glorified laptop. So that's not really useful. We don't actually need any SRAD hardware. So we just went to an all software solution instead. And also another big goal was to make sure that it was easier to install, because last year it was all pretty used on a Unix system, and we had to figure out, only one person actually knew how to install it. So this being an application, in the future we hope to just run it as like a normal application on any computer, or just deploy it and use it on any website. So just a quick overview of what it actually is. It's a telemetry visualization tool. So as I said before, you have a software-defined radio connected to your computer, and then you'll get all the live data and view it in the live time. It's a post-flight analysis tool, and it is modular and dynamic. So it supports any sounding rocket, depending on how you configure it, and it can accommodate any variety of payloads. Yes. All right. So a couple of design considerations when we went into designing this. It was to make sure it was offline, because obviously the launch facilities don't really give you any Wi-Fi or anything unless we can get Starlink, but hopefully in the future, that'd be nice. We try to keep it very portable, use on any OS, because right now, originally it was only running on a Unix system, and then we moved it over to a Windows system for this one. And we also have it so the portable system. It uses a web dev stack, so that's MERN that can run on any operating system, and then it has cross-compiled executables that you can run to decode the information and all the waves coming in from the RTL-CR. So how we solved the real time, we used WebSockets, so that connects directly from our Python backend, which is our telemetry system, directly to our server, and that will store the data in the database. It will also send data to the client directly for real-time visualization. And the last design consideration is making sure it's a dynamic UI. Very important thing I want to hammer in here is making sure that this software was as dynamic as possible, so we could use it with future rockets without much hard code. Okay. All right, so just a quick overview of our microservice backend. So we have two main microservices. We got our telemetry one, which right now is running in Python. So right now this will decode and send our telemetry to our server, which handles all the data and puts them into entities and stores them in our database. This goes over our socket gateway. There are no arrows on my diagram, but if they were there, they would show you that it goes to the socket gateway directly to the client and directly to the server from the telemetry backend after it's been decoded. So we have two separate backends doing two separate things. So it's not all in one place. All right. So a big thing, as I said before, was the dynamic UI. This is to make sure that the program itself has a lot of longevity and adaptability, so you can use it for any sounding rocket in the future, so the team can continue to use it, because we have a tendency of not using things and abandoning software, so I'm trying to make that not happen. So as we know, rockets have different hardware and components, and sometimes you would have to hard code data in order to get it to show what you want to show. But obviously, hard coding creates unnecessary work, increases errors, and lessens the incentive to actually use the application. So for this, we used a standardized data configuration system that uses this data config file, and then after everything you upload, will show all the values. You can't really see it on there, unfortunately, but it shows all the values that are then shown on the side here. So it'll configure all of the UI based on what you put into your data configuration file. Okay, so for the real-time operation of the system, we're using a socket-based design. Pretty standard stuff. After, in the telemetry side, you go in, we have two telemetry systems right now. We have the APRS, and then we have LoRa. LoRa sends us custom data so that we can configure from our sensors and send that live time data, and then APRS is just our big red B sensor that sends, or a GPS unit that sends us GPS location and altitude. So for both of those, they have different decoding methods, and they go through that, and then they'll go into the socket gateway, send it over through the sockets, so whenever the socket emits something on the client side, it will receive it, and then it will update the display to show it. So that's what happens in the socket side, or on the client side. All right, so I'm just going to walk through some of our workflows here. So on this side here, we have our configuration panels. I'm assuming most of you can't see that, so what I'm going to do is I'm going to show the light mode version. I don't know if that's better, but in here you can see on the top left that is our rocket details. So in there you can put in your dry mass of your rocket, you can put in the height of it, all the generic details that you would normally have on your poster. And then to the bottom left, we have all the components on your rocket. For this year, I put in our flight computer and our big red B sensor, our big red B GPS unit. You can also configure other payloads and other data configs. And then in the top right corner, you have a visualization of the data config file that you upload. So in there, you can edit it in the future. It'll show you all the values that you uploaded in there. So for the top one in the top right there is showing our flight computer. It has temperature, humidity, what else do I got up there, and pressure. That's for one of our sensors, and then you can go in and edit those later. Yeah, so in the future ones, you'll also see these changes from the data config in the rest of the the active views that I'll be showing you later. And then right below that is our missions panel. This shows all of the missions that you have completed or are planning on completing. So we have Launch Canada 2023 there. And then we're going to have other ones for our recovery testing. And then you can just archive all your, have all your data right inside of one place, so you don't have to have it all in all other places. All right, next up we have the active mission. So this is when we're actually in mission. The first view in the top left there is the startup view. And then on the bottom we have the recovery view, and then on the right side we have the flight report. So what that'll do is it'll generate a report right after you got all your data from your telemetry, and you got a recovery location. It'll go directly there, and you'll get graphs of all of your data right off the bat. So you can send it right to the judges right away. So they'll have hard evidence that you actually got to the right apogee right away, and you don't have to wait to go get your telemetry unit from your actual rocket. There's also an option to upload your data and have it downloadable into this form afterward, because it'll generate another flight report. I'll just go into it a little bit more. So the startup view on the left side there just has a log of all the telemetry units you're getting. It's just like a command line interface for now. In the future, we'll also have a graph of the altitude to the side of it. This is just for startup, so when you're first trying to get a GPS lock, you're just kind of pointing your telemetry unit and trying to get a lock. This will tell you if you got a lock or not. Next would be the flight view. I don't have that up right now, but that will have graphs of the live data coming in, and you'll see the updated graphs coming up as you go. So as the rocket goes up and you get more packets, you'll see the graphs update. And the next is the recovery view. This is an interactable map using Google Maps. You can download them offline maps and use them to find your location. It doesn't really plot a trajectory toward it, so you just kind of got to find it. But on there you can kind of, I don't know if you can kind of see the middle pointer, but that's the launch location. And then finally, at the top there we have the flight report view. So this will give you a summary of all of your flight data in a table form and a graph form, and it'll give for each single field you configured from your data config. And then if you didn't actually have live data sending in, you can also upload it, as I said before, and it'll parse it. Yeah. And then for telemetry, it's very simple. Pretty much all we use is an RTL SDR. This will work with pretty much any custom telemetry source. You can connect it to any antenna, and it'll pick up the signal, and then it'll give you a waveform outputted. And then it is your job to change that waveform into actually useful data. And depending on the protocol you're using, it'll give you that software to use it. So you can either connect it that way, or you can write your own. And right now we have two. We have our Big Red B, which uses which is on the APRS band, or it uses APRS, and we decode that with Direwolf, and that'll give us actual useful information. The other one is LoRa. Currently, we couldn't use that this year, but LoRa sends custom packets, and you also define how your packets are received. So in the back end, you can show how the LoRa is, how to decode the LoRa. Yes. All right, so for some future work, we plan to actually work on more of the post-flight analysis part. We want to actually be able to replay the mission in live time, or so you can watch kind of what happened at what events and isolate the events. So right here, this would just show kind of like a little replay button, so you could view all the things that happened on your flight. Another thing we're working on is database syncing. So right now, everything is in your local database, but we want to be able to push it up to the remote database and show it to the world. That is something we're working on. And then we'll have to work on deployment after that. And yeah, that is all. Pretty quick.
Thank you for the wonderful presentation. So would we have any questions in the audience to start on live telemetry data and live data visualization for Chris here? If not, I do have a couple. So my background is in propulsion, so I'm maybe not the best to understand all the quirks here of your project. But in rocketry, we are used to Murphy's law. Everything every bad thing that could happen will happen. So what redundancies have you included in the system to make sure that if you lose part of telemetry, you're still able to display it? Or what's the backup plan if something fails?
When you're talking about fails, are you talking about the packets that are coming in or the front-end visualization side of it? Any of it. Okay, so on our end, when we get the data in, it'll be stored in two places, so we can check it in both ways. And you can also upload the data that you got from Blackbox later, and you can compare them, see if there's any inconsistencies. Because we know that sometimes the packages don't all come out, and some of them we get CRC errors on it. For the most part, there isn't too much error checking because it just comes in as packets, and you get the coded data from Direwolf, and Direwolf does most of the error checking for us. So that is a software used in the industry quite a lot. So we trust that quite a bit. But once that data comes in, we parse it and we use it for the most part.
Yes, if you want to just come here.
Hi, are you guys, so this seems very interesting, and I was wondering if your team is willing to make this so that other teams could use this with their own flight computers, because it's really cool. Okay.
Yeah, that would be the goal in the future, is to open source it so people can fork the code and use it on their own. Because as I said, it's configurable with any sounding rocket as long as you use our standard for how all the modules are configured. But in the future, I'll be releasing it out to the world. I just don't love the idea of maintaining it for everybody. So it'll be I'll give it to you and then you use the base version and add on to it, sort of thing. But once that's live, I'll send a message in the Launch Canada chat, say, here you go, guys. Here's a ready software. It's pretty close right now, but in the future it'll be. I just want to get it into a more of a deployable state before that happens. I would say maybe mid-October is when I would say it'd be pretty good. Yeah.
Fantastic. We'll be waiting for that. And if you allow me, one last question. So you mentioned live data visualization. Have you been able to quantify this delay in telemetry, and are there any plans to further reduce that delay if necessary?
Unfortunately, the delay is more on the hardware side of things because the SDR gets all the data and we get it right as it gets it. So it's not really a software problem. It's more of if our SDR is working well. Sometimes they overheat. Sometimes you need a limiter or you need something to attach onto it for it to work better without it slowing down. So we can't really control that as much. That's more the telemetry side of things. Any data that we get right away, it'll be displayed right away. So for the real-time validation, when you see it on, actually when I was testing it, I had one terminal open and then I had the UI open, it would update right away. So once it got the data, it would pipe it in right away. So for that part, it's not, it works pretty well. It's just the main problem is the SCR itself and overheating. So getting a reliable one is very important. Yeah.
Awesome. Well, thank you very much. A nice round of applause for our friend here, and looking forward to seeing your rocket in the sky. So it is 3:05. At 3:15, we'll have Queen's rocket team presenting their fin failure analysis at IREC. And then we'll be going to our two last speakers of the day from CDL, from Creative Destruction Lab, John Thornburg, and Dave Mann from MDA. Thank you very much, and see you in 10 minutes.
It takes a second.
Okay, so it is 3:14. In a few minutes, we'll be starting with the next talk from Queen's Rocket Team. So please, if you want to attend, coming to the conference area, and we will start shortly. Okay, so it's 3:15. We will start with our next presenter, so Queen's Rocket Team, more specifically QRET, which I think is said curate, or am I wrong? Curate? I like the Curie part of it. It's a nice reference to some nice physicists.
So the Queen's Rocket Engineering Team, which has been around since 2016, and has attended every hybrid and launch Canada since. The team has not only built rockets for competition, but also participates in the LC Tech development competition. They are developing a hybrid rocket motor for future years, and also assist the Queen's First Nations launch rocket team, which is amazing. I'm very looking forward to this presentation personally. I reviewed the report, and I saw that whole part of the failure analysis of spin, so I'll be very much looking forward to additional comments. And so I'd like to welcome to the stage Noah Gaffran and Alex Matheson, with Noah being just graduated mechanical engineering and the team CTO, and about to start a master's in aeronautical engineering at RMC. And we have Alex here entering 5th year applied math, incoming aerostructures lead.
Just make sure to speak in the mic.
On this table for some notes, yeah.
Speak in the mic because we're like.
And where can I go to the next slide? Right here. Okay. Okay, hey everybody. So Noah, Alex over here. We're going to be presenting on the failure analysis of our fins at IREC 2023. So you can see from the screen there, Timmins super well. So we're going to go into a little bit of the why and a little bit on what we can do better in the future for that. So we had a rocket, it was called Calamari. We took that down to Spaceport earlier this June. And we lost the rocket. We were approaching Mach 1.8 and fin fell off and the whole rocket fell apart from there. So we're going to talk about a couple things today. We're going to talk about the initial fin design. We're going to talk about the sequence of events in the flight itself. We're going to look at the probable causes of failure. We're also going to look at the engineering process failures that led to those technical failures. And then we're going to go over some technical changes that we can improve our fins and our rocket construction in the future, as well as our organizational changes that we can implement and we are already implementing in the team to prevent similar failures in the future. So I'm going to hand it over to Alex to talk sort of for the first half of the presentation about the fin design and the actual failure of the fins.
Thanks, Noah. So looking at the design of the fins, we had a 4-fin rocket with a 9.5-inch base chord and a short tip chord. Our design was meant to keep stability above 1.5 for the whole flight, and they were optimized for the transonic and the supersonic regions. The trailing edge of the fin is swept forward just to avoid potential damage on touching down, just keeping the tips of the fins off the ground. To manufacture the fins, we did a layup of a carbon fiber plate. We had 4 layers of plane weave carbon and 2 layers of unidirectional with the fibers running in the direction from root to tip just to resist bending. And the fins were mounted through the outer tube, but not connected to any tube on the inside. After we made the fins and got them, we cut them out using a water jet. We attached them to the outer tube by first cutting slits, and we made some small internal fillets that were just meant to sort of hold the fins in place while we made the more structural external fillets. The fillets were all structural epoxy, and the external fillets ended up at about 3/8 of an inch. We made the circular profiles by kind of scraping down with just a wooden craft stick. So after our fillets were all done and set, we did a tip-to-tip layup with a couple of layers of carbon fiber. First we had one layer of carbon fiber, unidirectional, only covering the fillets, and then a larger layer of unidirectional that went about halfway up each fin, and then finally a layer of spread toe that covered the entire fins. After we finished the tip-to-tips, we noticed a couple of flaws. Mainly, there was some delamination of the final spread toe layer. You can see in these pictures there were some fibers sticking out, and to deal with this, we ended up having to either cut some fibers off or do some spot repairs with extra epoxy. We suspect that we just undersaturated that final layer, and we think we had some problems with the surface preparation of the fins before we did the bonding, which Noah will touch more on later. So during flight, we could make a decent assessment of what happened through video footage. So our initial ascent was looking good, very vertical, straight boost. So we know the fins were well designed from a stability standpoint. But after a few seconds at t equals 4.6, so just before our motor burnout, when we were at about Mach 1.75 to 8, we noticed a turn in the smoke trail and some small oscillations. There were very abrupt oscillations, and we expect that this is probably when the fin failed and fell off. And immediately after this, about 0.3 seconds later, we could see visible debris exiting the rocket. There's a parachute out and several parts that came unattached while the motor continued to burn. So we expect right before this, the entire airframe, or at least parts of it, failed completely. The aftermath of the flight, none of the rocket came down on parachute, but the aft section of the rocket did land very close to a prep area, and we saw that we were missing one fin completely, and another fin had some significant structural damage where parts were peeling off, and some other fins had a minor amount of similar damage. Looking more closely, there's significant delamination of the tip-to-tip layers on the fillets and the fins themselves. Looking at the fibers, the fibers were mostly intact themselves, so we see that the failure occurred at the bond interface rather than the bulk of the carbon itself. So we suspect what happened was fin flutter based on how the fins kind of bent apart from the tip-to-tip layup. Now Noah will dive a little deeper into the reasons of the failure and how we improved our processes in our new rocket Calamini and into the future.
Okay, I'll just stay on this slide for just a brief little moment because these pictures offer a pretty good insight into what happened. So you can see the fin that's missing. There's some of the tip-to-tip remaining on the outside, but the full bulk of the main fin, the main plate, is fully, completely gone. And if you can see into the middle, which you can't see very well in this picture, the fillets are actually mostly intact, and it's mostly just on the bond surface. The fin just ripped completely right out. And then if you look on that second fin, you can see where it was starting to fail, and you can see the kind of delamination in that picture on the left of some of the tip-to-tip layers. That happened on both sides of the fin because the fin was most likely oscillating from one side to the other side, which is very consistent with the fin flutter failure mode. We'll go into the primary technical reasons for why the fins failed. So the first reason is the surface preparation of the epoxy bonds. So after basically looking into why this happened, we talked with everybody who was involved in the building process, and we were able to gather that the surface preparation was not done thoroughly. It was either done in a haphazard way or even not at all on some of the surfaces. A little bit of maybe go fever in terms of the construction, perhaps. But there was no formal procedure for doing surface preparation or bond preparation. And then in addition to the surface preparation, we believe the fillet size may just have been a little bit too small. because like we think maybe a little bit of additional area on those bonds might have been able to increase the strength as well. The second main reason, and this is the biggest rookie mistake that our team did, is we basically had a disconnect between the design specs and what actually ended up getting built. So we did fin sim and flutter calculations, spec for a fin thickness of 6 millimeters, and that's before any layers of tip to tip. But after the failure, we went back and measured the fins, which I guess we had not done until sometime in between the construction and the failure, and the fin stock was actually not as thick as it was spec to be. So they were measuring only about 4.5 to 5 millimeters. So obviously that is not ideal. So going into the organizational reasons for the failure, this is where we can like dig deep and realize why did we actually make the mistakes, and these are the things that we can actually fix and improve that will help us in the long run. Because it's easy to say, you know, yeah, we made the fins too thin, but why do you make the fins too thin? That's like, you know, pretty dumb. So the first one is lack of formal procedures for bond preparation and the tip to tip. So that's pretty basic. We didn't really have anything set in stone or anything written down for that. The second one is a big disconnect between the construction and the design. So basically, once we started building, there wasn't really a lot of going back to the design documents. We sort of, you know, we knew what we were going to make. Let's just go make it. So again, as I said, kind of go fever. You just got to go. Building sort of by the seat of your pants rather than exactly by the numbers that were worked on. You know, and some of that is in the case of the person who's designed it is not necessarily involved actually building it. Or, you know, if that is the case, there's not as much communication going on. And then the third reason, which is not as big of a reason as the first two, a lack of practice or just testing with parts that aren't the actual flight rocket. You don't want to be trying something new or, you know, trying some procedure that you haven't done in a while if that's like the crucial part. So it can be good to do some practice or just do a test, something to figure out your procedures before you actually do it. So what have we done for a rocket that we brought here? So we have a new rocket. It's not called Calamari. It's called Calamini because it's Calamari's little brother. It's one of the smallest rockets out there. You can find it out in the corner. So one of the steps we've done, one, we've ensured that the fin sim calculations actually line up with the actual design fin and the actual constructed fin. Seems obvious, right? We also increased the fillet size just to increase the bond area. This rocket, Calamini, is nowhere near as high performance as Calamari, which was going over 30,000 feet and close to Mach 2, Mach 1.8, Mach 1.9. Calamini is only going to about 12,000 feet at Mach 1.1. But we've used a bigger fillet anyways just because you want to have that nice bond area. One of the things we've done to reduce the problems with that delamination of the tip-to-tip layer, even during the construction, is added a layer of fiberglass on top of the carbon spread toe. The spread toe is a very thin weave that's a little bit fragile in a way. So the fiberglass can act as a sacrificial sanding layer to make sure when we're sanding the fins to get them nice and smooth, we're not cutting any of those really strong carbon fibers. The fiberglass just kind of lets us smooth it out and prevent some of that delamination. Of course, we're ensuring all surfaces were properly prepared for bonding. And we also did a practice run. We took some extra body tube, we cut a little fin-shaped piece of fiberglass, and went through the whole procedure, and we were able to find some things that worked and some things that didn't work, and it made the actual process of bonding the fins quite a lot more successful. So the fin design for Calamini, we have a 4.5 millimeter thick carbon fiber plate. There's 14 layers of carbon fiber in that of various weaves. There's surface mount because this rocket is minimum diameter, so they get tacked on with a jig first and then filleted after that. There's 3/4 inch radius fillet. It's applied with a spherical tool, so they're going to be really consistent. You don't have to worry about holding the wooden stick at the same angle throughout the whole thing to get the right radius. Doesn't matter because it's a sphere. And then 4 layers of tip to tip, so there's 3 layers of carbon fiber and then the sacrificial layer of fiberglass on top of that. So it's a pretty standard design, but it seems to work. So for the bond preparation, this is what we've kind of implemented into some checklists. So the first thing is always to be wearing clean gloves. Even the grease from your hands can affect the strength of a bonded joint. After that, after the part gets manufactured or delivered from commercial suppliers, if so, you clean them all from any dust or residue or mold release remaining on the part, just with soap and water and let it dry. Then any area that's going to be bonded gets cleaned with isopropyl alcohol, dried. Then any area that's going to get sanded gets sanded lightly but thoroughly in all directions and very evenly with 240 grit sandpaper, just to get correct water break. And this happens to happen directly before the bond, because if you do that, this is to give the proper chemical activation of the bond as opposed to just a mechanical activation of the bond. And then after that, to get all the sanding dust out of there, of course, clean it again with isopropyl alcohol. Isopropyl alcohol is just a solvent in this case. Acetone is also frequently used, but there are a few scientific papers out there that suggest acetone can slightly weaken epoxy bonds, so we prefer to use isopropyl alcohol in this case. So this is an improvement that we've made from mostly using acetone all the time. So the construction process, this is surely familiar to many other teams who would probably do your fins in a very similar way, or any hobbyist rocketeers out there as well. We have a fin alignment jig. We tack those on. Once those are fully cured, we do the fillets, and there you can see the surfaces are already being prepared and sanded for one of the tip-to-tip layers. So of course the fillets and the tacking, those areas get bond prepped as well before this. Here you can see the bond preparation underway. Someone's doing some cleaning with a gloved hand and some isopropyl alcohol. That's only blue towel. One improvement that could be made from that process there, from the picture, would be to use a lint-free towel instead. You have to be a little careful with the blue towels not to leave any lint residue on there. But we didn't have time to have any of those. And then you can see a couple pictures of the different tip-to-tip layers being applied. So there's a unidirectional layer, a couple of layers of spread toe, and the picture on the right there is the fiberglass layer. And then after that, that gets all thrown into a vacuum bag with all the other applicable layers that you would commonly use in composites. What are some of the tech organizational changes that we've made? We've just gone over some of the technical changes that we've implemented in our new fins. So the first one is a bond checklist. So we now have a document, a spreadsheet. I don't have a picture of it in here. I probably should have done that. But we have a checklist for every epoxy bond, not just anything for the fins, but any bonded joint in anywhere in the rocket. So if you're bonding a coupler, if you're bonding a nose cone shoulder, a bulkhead or a fin or anything, or doing a layup on top of something such as a tip-to-tip. There's a specific checklist to follow that includes lots of the steps that we showed in one of those previous slides where we go over the bond preparation procedures. So that really been helping us with our bonded joints, making sure those are as good quality as they can possibly be. In addition to that, we're having some procedures being developed for matching design parts to built parts. So it's basically an inspection of every part after you make it to make sure that the part is actually to spec. After every composite layup that we're doing, we have a layup report sheet now. So it records the weave stack-ups, how many layers of unidirectional or twill weave and the weights of the fabric, etc. Their directions, looks at the wall thickness, both of the raw fabric, but then also after the part's cured to see if the vacuum bagging has reduced the thickness, which we think is probably what may have caught us out with making the fins too thin for calamari. We also look at the resin and fiber volume fractions and make sure these are all within our targets that we're looking for. One of the things we want to push to our team in the future is if you get a bad part, don't be afraid to throw it away and do it again. Obviously, it takes a little bit of, courage in a way to throw away your work and say, hey, I did a bad job, it's time to do it again. But it feels a lot worse to put that bad part in your rocket and have to dig it out of the desert. That's another one of the things that we've done. So what are the big impacts of this? So nobody likes to lose their rocket, obviously. It's easy to have a failure like this and focus really, really hard on that failure. So it's really easy for us to lose a fin and focus really, really hard on making the fins perfect. And then when we're making the fins perfect, it's really easy then to maybe overlook some other areas. So that's why when we've been looking at our epoxy bonds, we're not just looking at the fins. We're looking at all of our bonds throughout the entire rocket. And when we're looking at, parts matching their actual spec, we're looking at those parts all throughout the entire rocket, not just on the fin. We've already caught a couple errors and reduced a couple of machining time just this summer. So what are some of the challenges that we think we might be running into in these situations? So it's difficult to pass these sort of lessons on in a student team where, you have someone like myself who's just graduating, about to leave the team. We have lots of new members coming in every year. People going away on internships, people coming back from internships. And a lot of people don't love spending a lot of time digging through documentation on some OneDrive. So it's a big challenge to, pass on this knowledge that is fairly, common rocketry knowledge for some people, like, make sure you do good bond prep on your epoxy. Like, that should be pretty obvious. But it's really easy to make these mistakes if there's not a procedure set in stone and there's not, like, a kind of culture around the team for knowing these certain aspects and being able to follow those procedures. So these technical failures are available, are avoidable, but we're still making the mistakes. So the challenge is to really make that knowledge like passed down throughout the team. So we're coming close to the end here. So what are the main engineering lessons we've learned from this fin failure? So the technical failures, yeah, we can tell you exactly what happened. The fins were too thin, the bond prep was not good enough, and the fin fluttered off. But that's not the real failure. The real failure is that we didn't catch these mistakes before it flew. So these technical failures do have their roots in team organization and like team behavior. And even if we know how to do something right, as I mentioned in the last slide, it's easy to make a mistake. So the last 3 bullet points there are just some nice axioms, I guess, that we can all follow in all of our engineering processes. Double check everything, take your time, and write everything down. And there's a picture of our new rocket Calamini, and hopefully we get it back in one piece when we launch it in a couple days. But that brings us to the end here, so thanks everybody for your time and for listening, and best of luck with your own launches, and if you have any questions, we're here.
Great presentation. Thank you very much. Do we have any questions in the audience? Yes.
Have you been using any non-destructive techniques?
So checking bond spans and bond qualities and so on? Or any thoughts on doing so?
Non-destructive techniques, we haven't been able to do that yet. We don't really have the capabilities to do any of the more advanced non-destructive testing. I've been looking to do some destructive testing, just like tensile tests with various types of bond preparation. In the past month or so, I haven't been able to get access to that equipment yet, but that's something that I think we're going to encourage the team just to, get a little bit more data on epoxy bonding. But non-destructive something would be something that I would encourage the team to look into. I am graduating, I'm about to leave the team, but those of my teammates who are out there, they're still going to be here. Maybe you guys can spend some of your budget on that.
Take notes.
Yes. So, were your fins sort of non-tapered, leading and trailing edges?
Yeah, the edges were tapered.
So, when you sand in the taper, doesn't that introduce additional places where it could start to take away from the layers, so it could start to debond there?
Yeah, Are you checking on the ones that failed? So the bevel is only done into like the plate stock initially, which we didn't see any delamination in that. That was the fin that fully fell off. The tip-to-tip layers don't reach the very edges of the fin. So those areas that we saw the delamination were not connected to the beveled trailing edge of the fin. I guess you could potentially see some areas for delamination there, potentially if some delamination had occurred on the water jet or something, but we didn't really see much of that. It could be a concern, but it's not something that we've experienced reliably.
I do have a question. So in the words of our dear Oppenheimer, theory only brings you so far. And you clearly know that with Calamini, planning for Calamari, if I got the names right. What do you expect are the limits in how scalable those results are, both in rocket size and rocket speed?
These techniques for attaching fins and using tip-to-tip have been applied by our team in previous years and by other teams and other hobbyists in the rocketry community, up to effectively as big as these sorts of teams and hobbyists ever like to do rockets. So diameters up to 6 and 8 inches and fins at appropriate spans for that, as well as speeds above, approaching sort of Mach 3. Usually if you have if you see any crazy projects that are going even faster than that, often they switch to aluminum machine fin cans rather than opposite
plotted fin fans, but our team probably doesn't expect to be approaching anywhere close to like past Mach 2 like Calamari was supposed to do in the future, where these techniques have been proven by many other teams and hobbyists several times before, many times before.
Right, thank you. Any other questions? I do have another one. And so you mentioned knowledge transfer, writing procedures and training your team to essentially acknowledge that when they make a bad part and be able to throw it away. Do you have any perspective on training or practicing those layups in a way that wouldn't sacrifice large parts of what you'd expect to be a rocket part and have to throw it away? What do you expect in terms of training in addition to all the documentation you do?
Yeah, so in terms of training, we're trying to kind of accelerate timelines a little bit next year and have more time to make parts that we don't expect to fly on the rocket. And those parts could also be parts that we're doing testing on. But yeah, we want to have time to make parts that we don't fly, we just practice to like get the process fully down. Does that answer what you're
Absolutely. Yeah. In addition to that, like some of these techniques can be applied to smaller rockets or smaller parts. We've had members on our team get high power rocket certifications. So some people have been doing like tip-to-tip fiberglass layups on a smaller scale for much lower performance rockets. But it just helps you, learn and see how it's done before you have to do it for the one with high stakes.
Thank you. Any other questions? All right, thank you very much.
Great presentation.
Great, thank you.
Thank you. Okay, so it is 3:40, which gives us a small 5-minute break before our next speaker. Next speaker is going to be quite interesting as well. We have Jeff Thornburg from Creative Destruction Lab, the Space Stream, essentially the venture capital firm that is funding most of the rocketry startups in Canada and around the world. So this is in 5 minutes. If you want to come back for it, strongly recommend. Okay, so it is 3:45. And I'll invite everyone that wants to attend the next talk to come to the conference section. As I mentioned, we have Jeff Thornburg from Creative Destruction Lab, Space Stream, presenting with us. Let's give a few more minutes. All right, Jeff, can you hear us?
I think I can hear you.
Beautiful, and we hear you very loud and clear. Okay, so just for your information, you're now projected in front of our audience as well as the student exhibits. And so for everybody that just joined, I would like to introduce Jeff Thornburg from Creative Destruction Lab, the Space Stream. And if you allow me, I'll have a short introduction. Jeff Thornburg is a career space engineer and leader who brings a wealth of valuable experience to the CDL Space Stream. Jeff is the founder of 2 space companies, Portal Space Systems and Interstellar Technologies. Prior work has seen Jeff lead the growth of Amazon's Kuiper satellite mechanical engineering and manufacturing teams as the director of engineering, with other notable roles as the vice president for propulsion engineering at Stratolaunch, working with the late Paul Allen, and becoming the senior director of propulsion engineering at SpaceX in Hawthorne, California, serving as the principal engineer and architect of the Raptor engine development program for the Starship and Starship booster that we're hearing so much about. Jeff also served as the second vice president of the propulsion engineering at SpaceX, overseeing flight, test, development, and research operations, while also supporting customer interactions, including those with NASA and the U.S. Air Force. Jeff oversaw 6 successful Falcon 9 launches during his time as the VP of Propulsion and coordinated qualification and certification activities with the U.S. Air Force and NASA. He was also a lead propulsion engineer and turbo machinery technical project manager for the J2X engine development program at the NASA Marshall Space Flight Center. And Jeff spent 4 years working for Airjet as an engineering director for the liquid engine turbo machinery group, and served as the site manager for the Aerojet Woodland Hills engineering office in Woodland Hills, California. Jeff started his career in the USS Fort as a flight commander and aircraft maintenance officer on KC-135R tanker aircraft at MacDill Air Force Base, Florida. He was selected to attend the Air Force Institute of Technology and earned his master's degree in aeronautical engineering. Jeff was stationed at Edwards Air Force Base, where he joined the liquid rocket engine branch at the Air Force Research Laboratory, where he worked on several component and engine technology programs, including leadership of the Joint Air Force-NASA Integrated Powerhead Demonstration Engine. This program performed the world's first hydrogen full-flow stage combustion cycle engine demonstration. Jeff has received numerous Air Force and NASA awards, including a NASA Spaceflight Awareness Award, the NASA Made It Award, the NASA Stennis Spaceflight Center Propulsion Test Director Leadership Award, and was an Air Force Research Laboratory Technical Project Manager of the Year. In addition to his master's degree, he has a Bachelor's of Science in Aerospace Engineering from the Missouri University of Science and Technology. It's an absolute honor to have you today with us, Jeff, and such a long bio exemplifies your amazing work and impact on the space sector. Thank you for being with us today, and looking very much forward to your talk.
Yeah, thank you. Thank you, Cyril, and I'd like to thank Adam and Launch Canada for the opportunity to come chat with you a little bit today. Apologies I couldn't be there in person this time. Hopefully in the future, I'm looking forward to making that happen. And man, when you read through my bio, I start to feel old, so you know, I might have to cut that back a little bit in the future, but joking aside, it's a pleasure to be with so many talented folks, and what you guys are working on, and I'm looking forward to chatting a little bit with you on my experience and having some time to maybe answer some questions that you may have that I might be able to share. So I'm going to kind of walk through a few charts for the discussion, and I promise I won't bore you too much. I've got more pictures than I do text because that's how I roll, because that's a little more interesting. So let me pull those up.
Yes, we see your slides. Beautiful. Thank you.
Great. So I titled this talk Front Row Seat from Legacy Space to New Space. And the reason I did that is, well, I'll get into that in a second, but you kind of heard my bio, but there's a few things that might be interesting as we kind of walk into my talk today. I think probably what I'm most known for is things that were mentioned earlier. Built the Raptor team at SpaceX, led propulsion in 6 Falcon 9 missions while I was the head of propulsion. Got to work with the late Paul Allen, who co-founded Microsoft, on his space program, and got to work on what is still the highest performing hydrogen engine, liquid engine ever built, with the IPD program. Some other things that people might not know as much about me. I did lead the Falcon Heavy team for almost a year at SpaceX, which was a lot of fun, especially when I see those boosters land regularly these days. Had the opportunity to testify before the U.S. House of Representatives and the Armed Services Committee. That's the center picture there. I did a lot of development for SpaceX and IP development, same for Paul Allen. And then, got to do some interesting things like work with Al Gore on the climate project, which is not something a lot of people probably know. Bottom picture there is me with the first Raptor engine ever made. So it's real. I was there. Glad I got the picture. I'll have to put it on a t-shirt, I guess. But I'm really passionate about pushing humanity farther into the solar system. Working with Paul Allen really kind of changed my outlook on technology for humanity, which has been a real focus of mine in the second kind of half of my career. Always thinking about what we can do to work against climate issues, even with a space career. I don't think the two are exclusive. Passionate about, obviously, propulsion and spacecraft development programs and developing the space economy. So the thing I think that makes me maybe a little unique is that my career so far is about 28 years, and it's been bookended by the end of what is called legacy space or old space, and then this quote-unquote new space era. And I've kind of got to have a front row seat to watching the whole space industry in the U.S. transform. And oftentimes when I talk to a lot of students, both high school and college, and this tends to be, one of the more interesting things I think for folks is how the opportunities, how the industry is transformed. And I'm going to share some of what I've seen, and then, hopefully be able to answer some questions that you may have about what the future looks like. But the neat thing is when I started my career at the Air Force Research Lab, I was able to participate in technology development that was spearheaded by the U.S. government because there was no business case for space. There was no commercial space companies. The picture of the shuttle there on the right, that was the only thing really flying. I mean, you had Atlas and Delta flying, missions for the U.S. Department of Defense, but a lot of people forget that the space shuttle looks like it does because the NASA and the DoD tried to combine design requirements into one vehicle, and the shuttle looks like it does because they tried to build one thing to serve a lot of different use cases, and it really didn't do what it was intended to do. It made everybody equally unhappy, I think, in the end. But once the shuttle was flying, I think later the DoD saw that they needed Atlas and Delta to help with their national security needs. But when I started my career, there was no appetite for hardcore technology development improvements in the U.S. space industry. Because once you had the shuttle and Atlas and Delta flying, they didn't want to change anything. Because if they changed something and it broke something or it invalidated qualification, that means you weren't launching. And so we were doing a lot of tech development in the late 90s and early 2000s in the U.S., but it really wasn't going anywhere. And if you've ever seen Raiders of the Lost Ark, at the end of the movie where the Ark goes in a crate into a warehouse with all this other government stuff, that's where a lot of this technology development went in the 90s and early 2000s. So the cool part is I was able to work with a lot of talented people after I left the government, and then end up at a place like SpaceX where working with a talented group of people, we could actually realize the goal of affordable and rapid access to space. The shuttle program was an engineering marvel, but it wasn't affordable or rapid as originally intended. And so when I started my career almost 30 years ago, the problem was still on the table of how do you get rapid and affordable access to space? And so being able to work through that and see that problem solved and now where we're taking it is kind of one of the themes of what I wanted to chat about today. And I'm really excited to see what we're going to do with this new access to space, affordable and rapid access to space now, which is where, I'm kind of focusing my professional attention. So it's kind of cool to look back and see the shuttle photo. The crewed Falcon 9 just had a launch, just recently with astronauts to the station this morning, I believe. And then, that iconic photo at the bottom is nobody ever believed that we could land boosters. And we got laughed at so many times. And, and now people just kind of take it as commonplace that, these rocket boosters go up and they come back and land in Florida, which or Vandenberg, which is pretty cool. So I'm not going to read through my bio. I mean, I think you got that at the beginning of the talk. A few things I'd point out though that may be interesting is, I've been very fortunate. I am still a relatively young man, I'd like to think, and I have lots of years left to work. But one of the things that I did in my career that's often a question I get from folks is I was always open to opportunity. And what I mean there is I have a lot of colleagues and friends that aren't paying attention to opportunities that could be coming right in front of them because they're so busy or they're so worried about other things or they're focused in any areas. And so, I mean, I think one of the things that both my wife, who was a big part in allowing this to happen, working with me, is giving me that flexibility to be open to opportunities and being able to do some really cool work across the last 3 decades. One of the things I wanted to show is the photos on the right. So on the bottom photo is what's called the U.S. Air Force NASA Integrated Powerhead Demonstration Engine. It was the world's first full-flow stage combustion cycle engine that was reusable. The Russians had a program where they were looking at some toxic storables, but by all accounts in what little information is written out there, they never could get the engine to survive a single test. And so they kind of abandoned their program. And one of the things that made the U.S. successful is things that actually happened at the end of World War II. So I'm a little bit of a student of history, and the interesting thing about the end of World War II is how the U.S. acquired their rocket team and how the Soviet Union acquired their rocket scientists from Germany. And with von Braun and the group that was come over to the U.S. and ended up in Huntsville, Alabama, there was a very strong focus on analytical and design innovation and things that kind of are a little more future forward looking, where I feel like the Russian programs ended up being a little more practical, a little bit more manufacturing and cost focused, and less performance focused. And I guess where I'm going with this is an engine like a full flow stage combustion cycle requires a high level of analytical complexity and avionic complexity to control that engine cycle, because you're fractions of a second away from melting that engine down every time you start and shut it down. And so if you can't figure that out and you can't model that as a part of your design process, you're probably not going to be very successful. So one of the cool things that happened to me along the way is one of my first assignments at the Air Force Research Lab was to take over this engine program. And the bottom photo is full up engine test in 2005. Now, if you fast forward 10 years later, we had the first Raptor engine, development engine on the stand in McGregor, Texas. Just the angles and the horizontal testing always struck me as something cool. And so, I never knew if we'd pull the technology out of the warehouse with the Ark of the Covenant on IPD. And I actually had a chance to work with the Air Force at SpaceX and bring that technology into the commercial sector as a part of this new space movement, which turned out to be a great partnership, and it's great to see those 33 Raptor engines static firing and working out the bugs and getting ready for the first successful flight of Starship. As you can probably see from my bio and background, I spent a lot of time focused on boost propulsion and launch vehicle technology for the first, more than half of my career. And then I'll kind of talk through this a little bit. And then I really, after Paul Allen passed away, I really wanted to focus, my time on the future, which I feel like is in space, spacecraft capability and development, and the propulsion systems that are going to unlock, the LEO to GEO, commercial commerce, DoD needs, and eventually the cislunar market that I think is, not too far away, in the next 5 to 10 years. One of the things that was mentioned is my time at Creative Destruction Lab. So I became an entrepreneur for the first time back in 2015, and then later turned that company into a C Corp in about 2019, and did a little fundraising, and I took Interstellar Technologies through the Creative Destruction Lab. And for those that may not know, that's based out, the space stream's based out of the University of Toronto at the Rotman School of Business, and I got a chance to meet Chris Hadfield for the first time and spend time working with him on that first venture. And then that kind of led to the last 3 years now, I've been invited to be a mentor for Creative Destruction Lab, and I can't stress the value of that program enough. So I'll put my shameless plug in now is for all the folks that maybe think about starting a business in the future, or maybe that's on your doorstep or a thought down the road. What an amazing program. Would happy to be talk to anybody about that at any time. But I'd say, I spend a lot of free time with that program because it's so highly valuable to mentor the next generation of startups. Because I really want to see this new space movement continue and help ventures find the right business case with their technology ideas that are going to proliferate the space economy. So I do spend a lot of time there, and I know that was mentioned. So I'm going to jump in now to a little bit of the history that I kind of mentioned, that I just will talk to a few of these photos, and we can kind of move forward. But this was the IPD engine, and you can see it was a design for flight. A lot of big ducts. It's sitting in a big, heavy metal cradle. But again, this was the first time anybody in the U.S. had ever tried a full flow stage combustion cycle engine, and so this was a joint program with the Air Force and NASA that included Aerojet and Rocketdyne when they were two separate companies, and a lot of work by my friends and colleagues at the NASA Marshall Space Flight Center in Huntsville, Alabama, and the NASA Stennis Space Center in Bay St. Louis, Mississippi. And so what an amazing thing to be able to kind of start your career with, is the first of a kind engine ever in the world. And that still hasn't been, repeated and or exceeded. So that really whetted my appetite for rocket engine hardware. And one of the reasons I left the Air Force and went to the private sector is because I wanted to be closer to propulsion hardware and spacecraft hardware and drive the innovation there. So after my time at Aerojet, I had the opportunity and was asked by NASA to come support the J2X engine development. These are a couple of photos of the first J2X engine development engine that was built and tested at Stardust. And for those that may not know, the old J2 was the upper stage hydrogen engine for the Saturn V. And so I had an opportunity to get to meet and work with some of the old Apollo propulsion engineers and stage engineers, and really understand the original J2 design, working with Rocketdyne. And as a student of history and a propulsion person, what an amazing project to be able to kind of understand all of the historical work that had happened, and then make improvements for a modern high thrust hydrogen gas generator engine. So a really cool program, very successful. There's one of these sitting in the museum and at the Space and Rocket Center in Huntsville if you're ever interested in seeing it. Too bad it didn't fly to space, but maybe there'll be opportunities in the future. Then I went to SpaceX after my time at NASA, and as was mentioned, and my first job was and the job I had for 5 years always was getting the first Raptor engine on the stand and getting that development program moving forward at the engine system level. And so the flight engine today is a little different than when I left the company in early 2016, but the technology is all the same. We had to develop new alloys that could stand the ox-rich combustion on the ox side of this engine cycle. Heavy use of additive manufacturing and innovations in additive that didn't exist, that people take for granted now, that we were pioneering there in the 2010s. And methane. You know, everybody thought I was crazy and SpaceX was crazy for developing methane propulsion. And now in 2023, if you look across the landscape, you've got Relativity with methane propulsion. You've got Rocket Lab's Neutron chasing methane propulsion. SpaceX, obviously, with Raptor. And others. So it's been quite a shift, and it was really cool to be on the front of that paradigm shift and really focusing on a lower cost alternative to both kerosene and hydrogen. But I think that is the first test that was publicly shown in the top left photo there. So while I was running propulsion at SpaceX, obviously, you know, I was heavily involved in the evolution of the Merlin boost and upper stage engines. These were Tom Mueller's babies, and he and I sat next to each other, and I focused a lot of time and attention for development on Raptor, and he was focusing a lot on the evolution of Merlin as the thrust and performance upgrades continued to be enacted for Falcon 9 and Falcon Heavy. And he and I worked together, and it was a really cool time. And so some of these photos are some of the you know, milestones from almost a decade ago now. I think the top right is the 100th Merlin engine, and the bottom photo is the first time we mounted the engines in the octaweb, as we call it, which is the thrust structure at the bottom of the Falcon 9. And so the real cool part is, you know, you see all these launches now from SpaceX, and I think the public kind of takes it for granted now. But that time between 2010 and 2015 was really an inflection point for that business and commercial launch in general. And it was all encompassing. And when I say that, I mean, my wife and daughter came to SpaceX to see me, you know, and so a lot of meals at SpaceX or the restaurant next door, a lot of yogurt to be had in the SpaceX yogurt bar with my young daughter at the time. But what a cool time to be alive in the space industry and participating. We had more propulsion development happening at SpaceX in that time than the history of the number of engine systems in the U.S., and it's pretty incredible. Some other cool things I got to do there. Got to work on Super Draco development. That's the launch abort engine with storable propellants for the Crew Dragon system, and these are photos from that first pad abort test that was done. And so it was really awesome to have a small part of you know, bringing U.S. astronauts and international astronauts back to the station on a U.S. vehicle, and that was a huge deal and still is. And then after SpaceX, I went back to Huntsville. My daughter was young. My wife and I went back to raise her there, and I took a break for 2 or 3 months and just took my daughter to school and picked her up to kind of decompress from the SpaceX era. And then I started doing some consultant and contractor work, and then I had the opportunity to meet Paul Allen, where Paul actually called me one night and he said, can he come chat with me in Seattle? And so a 10-minute conversation turned into 2 hours of chatting about space and space history, and a few days later Paul asked if I'd come join his team at Vulcan Aerospace and Stratolaunch, and that started that relationship there where we built an internal team to build a hydrogen propulsion system that we called the PGA engine that would support both a medium launch vehicle that you see in the photo at the top middle photo, and then we also were working on a reusable spaceplane concept, and all of that's kind of in the public domain, so I'm not sharing anything there I shouldn't. One of the coolest parts about this development, though, that I think all of you rocket scientists out there will appreciate is that I think a lot of people had the impression, and still do in the industry, that the only way you can move quick is if you operate like SpaceX. And I think what people interpret that as being is 100-hour work weeks, and you're in the salt mine and you're in the thick of it, and your life is nothing but going to work. And so one of the objectives I had when I started working with Paul Allen is to do the same rapid development work, but do it smarter. And I think the thing about SpaceX, which is fantastic, is they're always working to outwork their competition. I think one of the reasons you see things happen so quickly is they're working twice as many hours a week as any of their competitors, and certainly their legacy aerospace competitors. But I don't necessarily subscribe to the just work harder. I like the work smarter piece. And so one of the things we were able to do on this program is, in 10 months, we designed from scratch a full-scale hydrogen preburner for the PGA engine, and we're testing it from clean sheet to full power in less than 10 months. And that was the pace of development that hadn't been seen since the Apollo era. Some of that was enabled by additive manufacturing, other things were enabled by experience, but that was a really rewarding program for that team and myself. And I share that story because I don't want people new to the industry or starting their careers thinking, if I don't work every day for the rest of my life, I'm not going to be successful in this industry. Because one, that's not true, and two, there's examples out there to show you where you can, under the right circumstances, develop very quickly. And I still hand it to SpaceX because they do work harder than anybody else in the industry. And you can debate the sustainability of that, but you have to hand it to them. And having been there for 5 years, I wouldn't trade it for the world. I gained probably 20 years of experience in a span of 5 years just because of what we were doing. And there's myths out there that it's not a people are doing this consciously because they love the work. It's not that it's a salt mine that people are working in and feel like they can't leave. It's the work is so encompassing that you actually have to work to get your team to take time off because it's so exciting for them. So following the Paul Allen era, I had an interest in really pivoting towards more in-space and less launch-focused technology development. And so a couple of things that I played around with in the last few years is I spent time with Amazon's Project Kuiper as their head of mechanical engineering, because I really wanted to dive into low-cost spacecraft solutions and kind of apply some things I'd learned in my career. And they were, obviously they're working to compete with Starlink in terms of proliferated LEO constellations for data sales, which was great. But ultimately, I wanted to move more into in-space spacecraft solutions for other things that weren't just data. And I also wanted to understand the latest state-of-the-art with robotics. So I had two really cool opportunities in the last few years. One is working with Kuiper. The other was being the Senior Vice President of Engineering for Agility Robotics, focusing on a humanoid robotics solution. It might seem odd to some on the surface, but, basically where I was thinking ahead was, these in-space mobility and services, both commercial and for defense, are all going to require advanced robotics and AI, and I wanted more experience in that area and helping to drive the engineering behind a humanoid robotic system was something that I couldn't pass up. And this was all before Elon was talking about Optimus and all of that stuff, and so it was kind of cool to see this whole humanoid robotics thing take off here in the last couple of years. But I was really doing it in service to kind of what I saw as the future of in-space mobility. And so this kind of culminates into where I focus a lot of my attention now, which is space mobility for both defense and commercial applications. My second entrepreneurial venture is called Portal Space Systems, and we're developing technology and a spacecraft solution to really enhance mobility for all commercial use cases in LEO and beyond, and needs of the defense community. And so, that's kind of what the top left is kind of alluding to in picture form. I think Starship's going to change the game for in-space mobility in terms of refueling and the size of spacecraft at the right price point. So you're going to see spacecraft get bigger. I think when Starship is fully realized, companies like OrbitFab in the bottom left developing gas stations in the sky, reusability and refuelability are going to be keys to really opening up the space economy in LEO and beyond. So as you can kind of see, I'm really interested in how we take this affordable and rapid access to space through launch that I spent 20 years working on, and now taking that and spending the rest of my career on developing solutions for various customers. And I think that's the challenge, right? I think everybody has a cool space idea, but one of the reasons I'm so passionate and involved with programs like the Creative Destruction Lab is you've got to be able to learn how to build businesses and business cases that are solving customer problems with your cool technology. It can't just be cool technology for technology's sake. It can't just be a cool rocket engine because it's cool or beats a performance criteria. You have to be solving a customer need to really blow the doors off this future space economy that everybody often talks about. So before we get into some time for questions here in the last 10 or 15 minutes, I thought I'd offer an answer to a question I get a lot, which is, where is this all headed based on what you think? So I'd say take this with a grain of salt, because the older I get, the more I realize I have no business trying to predict the future. But with that said, I will make an offering of areas that I think are going to be serious focus areas of things that may be interesting to you in the audience of starting your career and being at the front end of things. What would be good things to look into that may hold interest that I think are really going to be huge multipliers for technology for humanity. Obviously, LEO constellations and data sales are the best business case that's ever happened to space in the history of space development. I mean, programs like Starlink and Kuiper, you basically have remote communities and countries all around the world that are just opening their wallets saying, here's my money, give me my internet, I want my connectivity. And so that is going to continue, obviously, and like I said, it's the best business case for space that's yet existed, which is why you have now thousands of Starlink satellites, and you've got Amazon poised to launch their first Kuiper test satellites here soon. As we proliferate into LEO, orbital debris, sustainability, refueling, observation, logistics in general are going to really become huge, which is why I am personally working in that area. It's going to be the thing that really enables both commercial and defense customer needs. And then you start getting into a little bit farther out, energy. Energy is a problem around the world. I think most people acknowledge that. That's why you see, the chase for fusion or some alternate energy sources and trying to drive the cost of these exotic energy solutions down to compete with coal and natural gas. But I think space-based power generation, that's just on its very beginning journey, but I think it's going to be really key in our future. We're obviously going back to the moon. I'm excited about that, as I know you all are. But it can't just all be SpaceX Starship, right? And it won't be. And so there'll be plenty of opportunity for new companies to play in the logistics and exploration support domain for both defense and commercial business applications. We're still probably 5 or 10 years away from that being a real thing, but I think it's going to definitely happen. And I often get, well, what's the future of propulsion after working so many years in propulsion? I've said it publicly before, and I'll say it publicly again. In my lifetime, I think nuclear thermal propulsion is the most near-term solution that I'd like to see applied to really expand humanity's ability to explore the solar system. There are, there's the Draco program from DARPA in the US that's got Lockheed and BWXT working on like a demonstration of NTP. You have a startup or two that's also trying to support that. And you have a whole bunch of R&D happening in China around NTP, just because of the performance level. I think the one thing holding the West back, and specifically the U.S., is just the regulatory environment around nuclear and launching fission reactors continues to be really challenging. But other countries don't feel as challenged in their ability to launch and test with those things. So I think it's going to be really interesting to see that area expand as we go forward. Climate solutions, I think, you know, I'm not going to get on my soapbox here, but I'll just say I am not going to sit back and wait for a miracle on the climate side. And I don't think the world is in a position where it's going to work together to solve this anytime soon, which means most likely we have to be prepared to develop technology to help solve some of these serious problems, because we've just flat out waited too long to take any meaningful action. And I think space and space technology, I'd like to see get in a driver's seat of providing more space-based solutions for climate issues that we have. And if you look a little bit farther out and pushing humanity into the solar system, I think then, you know, there's a few different companies and people that for a long time have been playing around at small dollar levels with how to resource mine and extract from asteroids and other places. And there's been a lot of NASA work, you know, to follow the water in the solar system, which I think you'll see that happening in the next decade too. But I kind of ordered these in what I saw as near term to longer term, but just, you know, for what it's worth, maybe my opinion, and it's fine if there's probably a lot of differing opinions on that, but I thought I'd share mine. And in closing, before some questions, you know, I thought I'd just say to kind of wrap up that I'd say in the second half of my career, my goals have really been heavily influenced by my time with Paul Allen. And the thing that really made my time with him different than any other career opportunity I had was his focus on technology benefiting humanity. And it was just really cool to see him work across not just space, but all these different areas through his various ventures and companies in Seattle. You know, he really, really was a humanitarian, and he really wanted to see this technology in space particularly, you know, always be on a path to having a justification and benefiting humanity as a whole. And that's kind of influenced me ever since. So I tend to work on projects that provide, you know, a future affordability and high performance that is going to be additive to the human experience. High impact engineering projects is what I've been tending to focus on, both in companies I support and work that I do. And then working with teams and programs that have a synergistic vision. I mean, people can say what they will about various entities, but there's companies out there like SpaceX and others that have such a focused vision of where they're wanting to take the business and the work. It permeates the entire culture. And I've seen that in the military when I was in the Air Force. You know, everybody's rowing the boat together. And the space companies that I've worked with where they also have that mindset, they're the ones that can move the fastest with the highest efficiency and really get their products to market as fast as possible and the benefit to the humanity approach. So that's kind of the overview I wanted to share. I think we have about, you know, 8 or 10 minutes left in the time, and I'd be happy to take any questions that anybody had.
Hi, Jeff. What an amazing presentation and talk. I'm sure we have a lot of questions, so if you want to ask a question, please come to the back so we can speak directly in the computer for the best sound. And if you allow me, I'll start with the first of my questions, because I can't help but listening to your presentation, I can't stop thinking to myself, but what did Jeff not work on? The Draco, the Strato launch, the J2, it's absolutely amazing. So this leads me to the question, what is a rocketry program you didn't get to work on, but that with hindsight, you would have wanted to be a part of, and why?
That's a good question. I don't know. Well, I do know. I mean, I went and worked on the things I really wanted to work on and were excited about. And it was one of those things, like my wife says all the time, is where preparation met opportunity. I mean, I think the one area, the one business area I never really supported, I worked for Amazon Kuiper, but I haven't worked on any of the Blue Origin programs. I think some of that stuff's pretty cool. I think, you know, the size and what New Glenn could carry is interesting, but I didn't really chase that very hard because I went through all that pain of developing a reusable rocket on Falcon 9, and I didn't really want to do it a second time, so I wanted to kind of focus on some in-space stuff. But I think the one program, I think my brain thought of it while I was jabbering there, was when I was really young and just starting out in the Air Force and I was working all this technology stuff, I really had a strong interest in working on the space shuttle program. And it just, that opportunity wasn't there. I went from IPD and technology development into more of this new space commercial stuff. I guess instead of doing space shuttle, I did, the Ares rocket and J2X related things. And so I just missed that opportunity. And it was weird because I was standing on the roof of Hawthorne, the SpaceX facility in Hawthorne, and we watched the 747 bring the space shuttle in to LAX before it went to the California Science Center. And so, I don't know, I missed that program. I think it would have been a really cool program to work. I've got to go inside the shuttles and be exposed to that, but never got to work that one. I think that would have been a cool one to be a part of.
That's a very fair answer. So we have a question here.
Hi, I'm Alex Madison from Queen's University. First, thank you for the great talk. So I wanted to ask, you briefly mentioned the space industry affecting climate solutions. I'm wondering if there are any kind of new ideas or new startups that you've seen relating to the space industry and climate solutions that you're really excited about for the future.
Unfortunately, no. I haven't seen. I've talked to some people that have some interesting ideas, but I haven't really seen anything, maturing very quickly. I mean, I think you see a lot of stuff in the news now with companies looking at how they might work with the government to seed the atmosphere with chemicals, to kind of block the solar radiation. I don't know that I'm a big fan of that one personally, because that it doesn't have the feel good, like we know what we're doing part to it to me. But I have some thoughts on what I would like to see happen in terms of the space domain. And so, if we have a perpetual human presence in LEO and above, it allows us to look at, other solutions potentially to chemicals in the atmosphere blocking solar radiation. I think there's some other things in space we could look at doing that would be equally as effective potentially. But I still think that's a really new area, but I think it's ripe for development. So I mentioned it today because I know there's a lot of bright young folks in the audience that would probably have equal and better ideas than I would, but I think that's going to be necessary in the coming decade.
Great answer, thank you. So we have time for one more question from the audience. Okay, on my left right here.
Hi, my name is Kalen. I got a Falcon 9 question for you. So on most crewed missions, they normally they normally do ocean drone ship landings, and on a recent Falcon 9, it was originally meant to be an ocean landing. Instead, they're now doing, like on Axiom 2 and Crew 7 now, they're doing RTLSs. How much do you believe Falcon 9 can continue to gain more performance? Like how much do you believe it'll be able to increase its capacity?
Well, I think this is just my opinion. I'm not in the middle of that program right now, but I think there's some things operationally that can be done, right? I think in terms of how much additional upmass you're trying to carry with the astronauts and stuff, give you some opportunities to play with the overall payload numbers and make a choice on whether you're going to go drone ship or RTLS. I think the thing that I would point to is we have a Falcon 9 vehicle and a Falcon Heavy vehicle that have stable designs in manufacturing that are working well with high reliability. So I wouldn't expect you to see a lot more performance changes in Falcon 9 and Falcon Heavy. I think there may be some incremental changes to performance with Merlin and Merlin Vacuum, but I think you're going to see that be very deliberate and a little slower pace than what we were doing, say, 10 years ago when we're trying to get the product performing well. So I don't know if that's the best answer to your question, but I do think I think they're playing probably more with operational performance characteristics and making major changes. And I think the changes you're likely to see are going to be maybe a little bit performance, but more on the reusability front, you know, as they keep pushing beyond 15 reuses of the booster and going to 20 or wherever they're headed. So that's my take anyway.
Thank you for your answer, and this is all the time we had, but thank you for this amazing talk, and we're really looking forward to having you again at Launch Canada, talking to our students and sharing your story.
My pleasure. Everybody have a great time. Good luck. And I look forward to seeing you in person in the future, and thank you for the opportunity to be here.
Absolutely. Thank you. All right. It is now 4:30, which brings us to our keynote speaker for the day. I'm going to run to the stage. So we have been very lucky this year, and you might see it a little bit everywhere on our pamphlets, on our little cards, on our merch, on everything. You'll see their logo, and it's for a very good reason. We want to thank MDA once again for being such an amazing, consistent, and present sponsor for not only us, but most opportunities in Canada for students like me and others that involve themselves in rocketry and other space applications. So first of all,
thank you for being here. Thank you for enabling this opportunity for not only us, but the rest of Canada to also develop these technologies and benefit off of them. Thank you. And so this brings me to introduce Dave Mann. Dave is a talent acquisition professional with over 2 decades of experience helping some of Canada's fastest growing tech companies achieve their growth objectives. Leading hiring teams at companies such as Staples, BlackBerry, RBC, LPRs, and now MDA. Dave has helped facilitate the hiring of nearly 20,000 new hires over his career, maybe 20,100 after this event. Mostly in the tech sector. As the director of talent acquisition for MDA, Dave is managing one of the largest ramp-ups of talent in Canadian space history, with over 2,200 hires over the past 2.5 years, and another similar amount to go over the next year and a half. So please, everyone, welcome Dave Mann.
Perfect. Thanks, Cheryl. All right, so I'm cognizant of the fact that I alone stand between
food, dinner, and so I'll make this as painless as possible. But before I sort of jump into things, who's having a great time at this event? Right? All right, as the last speaker here, we got to have some energy, right? So I'll be engaging with you guys as much as possible here. All right. Yeah, you got it? We may have a problem. There we go. All right, just going to start with a quick little video, and I may need you to hit play on that. Could you hit play? I recognize some faces in the audience. Some of you have seen this before, but thought it'd be interesting to play it again. We don't have audio. Always tech challenges at the end of the day.
Room full of engineers, it is the best place to have technical difficulties.
today when we were setting up our booth, I don't know how many of you saw the HoloCube, but the HoloCube wouldn't start up. So, you know, we got some engineers out to help us, and we were banging it and kicking it, and sure enough, the kick fix worked. Maybe that's what we need here.
The kick, WD-40, and duct tape, and that's rocketry.
And did you turn it off and back on?
Exactly, the reset.
Well, listen, we'll. I don't want to spend too much time on this. If you can maybe. So, welcome. What I want to talk today a little bit about is the space industry in Canada today. So, there's never been a more exciting time to be part of the space industry as it is right now. There's so much happening, and I would argue that MDA is at the forefront of a lot of the stuff that's happening. Canada has over 400 companies that are active in the space sector, over 11,000 space employees, $2.2 billion in the company's GDP. And we're considered world leaders, not just Canadian leaders, but world leaders in satellite telecommunications, robotics, and remote sensing technologies. Guess what? MDA leads and plays in all three of those spaces. So before we talk a little bit about that, I just want to talk a little bit about legacy. And those of you who heard me speak last year, we talked a little bit about legacy last year, but I want to get into a little bit more in depth. So before I do that, just give you a little bit of a background on who MDA is. We were founded in 1969. We were founded by two professors from UBC, Detweiler and McDonald, and they started MDA because they were tired of seeing Canadian talent graduate and move to the US. So they started up MDA. We've gone through many iterations, a lot of mergers and acquisitions. In 2017, we were purchased by Maxar in the US. And then in 2020, a group of Canadian investors wanted to see that Canadian technology gem repatriated to Canada. So they purchased it in 2020. And then in 2021, April of 2021, we went public on the Canadian Stock Exchange, on the Toronto Stock Exchange. We're headquartered in Brampton. We've got 3 lines of business. Robotics and space operations. You all know robotics and space operations. You can see on the back of the $5 bill, you can see our key product there, which is Canadarm2. We've developed Canadarm1, which was on the shuttle program. Canadarm2 is currently in operation on the International Space Station, and we're currently working on Canadarm3. We're going to talk a little bit more about that. We also have in our geointelligence business, we take vast amounts of data coming off-stream from satellites, whether it be our own satellites or customer satellites, and we turn that into meaningful data. We do things like we have our dark vessel detection program where we will use synthetic aperture radar and we'll find ships in an area of ocean, and we'll correspond that to transponder data. And where there's a ship without transponder data, we know that that ship is operating dark. It's a dark vessel. And what does that mean? It means that they're probably doing something illegal, illegal fishing, maybe human trafficking, maybe drug smuggling, but it's something not good. So we'll engage the law enforcement to come in and see what's going on there. On the satellite systems business, we're fundamentally changing the way the world communicates. It used to be that satellites were launched in what's called a geosynchronous orbit, so 40,000 kilometers above the Earth's surface, and it would be spinning at the same rate that the Earth's spinning. So it's always looking down on the same swatch of Earth that as the world spins. That's great. You have 4, 5, 6 satellites, and it's covering the entire Earth. But it's 40,000 kilometers away. So there's a latency, there's a time lag for the signals to get back and forth. There's a higher amount of power that's needed to get a signal back and forth. Now we're moving into low Earth orbit, LEO satellites. And LEO satellites, they're moving past us because they've got to be moving past us so it doesn't come crashing to Earth. But because they're 400 kilometers and not 40,000 kilometers, it means that it can operate with a much smaller power consumption. And the power needed to get a signal up there is much smaller. So now you can use your cell phone to get a signal to a LEO satellite. The trade-off is one satellite isn't going to be looking down on the same spot of Earth. It's moving past us. So just like when you're driving down the highway with your cell phone's being handed off from one tower to the next, right? Your cell phone call. Same thing's happening with LEO satellites. One satellite passes you, and then the signal gets passed to the next one, and the next one, and the next one, right? So the trade-off is you need more satellites, but the latency is much lower. The power needed is much lower, so it's a much more efficient system. And as Jeff said in the last conversation, these LEO constellations, I think the term he used was, they're the best business case in space today, and they really are. So we're doing that in our satellite systems business. And of course, we have offices from coast to coast in Canada, Richmond, BC, we're in Brampton, we're in Ottawa, we're in Montreal, we're in Halifax. In the US, we have an office in Houston, we have an office in the UK as well. So, I want to get a little bit more in depth from the conversation we had last time. So, Telesat Lightspeed. We announced it this month. This is the most advanced LEO satellite network ever conceived of. It's the next generation, and it's going to, like I said, fundamentally change the way we communicate. MDA is the prime contractor. What does that mean? It means that we're responsible for everything. We might subcontract parts of it out, but we're ultimately the prime contractor. 198 satellites, and really that's going to become 298 by the time it's all said and done. And the first satellites are going to be launched in 2026. So we're talking 3 years for these to be designed, built, tested, integrated into launch vehicles, and ultimately launched into space. Got a, where's our guy in the back? Yeah. Got a quick video here to share with you. And this one sounds not as important. I'll just hum along to it. Just a little bit about the Telesat network and how incredible it is. So we're going a little bit higher. We're considered be 1,000 to 1,300 kilometers up. And the satellites are all connected to an optical communication system. The other advancement since the last time we talked was the Artemis program, and specifically our contribution to that is Canadarm3. So since we last talked, Artemis 1 has launched. That happened in December of last year. It was a successful mission. It was an uncrewed mission. It flew around the moon and successfully came back and landed on Earth. Also, Artemis 2 crew has been announced. And as we knew would be the case, a Canadian astronaut, Jeremy Hansen, is one of the 4 astronauts that is going to be participating in that mission. That mission is scheduled to go in 2024, next year, and they're going to orbit the moon and then come back. They're not going to land. But the reason that we have a Canadian on board that mission is because of MDA's contribution. And then MDA's contribution is Canadarm3. And we'll talk a little bit about Canadarm3. But first, a lot of people ask, why do we go to the moon anyways? What purpose? We've been to the moon. We went to the moon in the 60s and 70s. Why should we go back to the moon? So let's kind of hear what NASA has to say.
If you want to play the video.
Yeah, no worries. Have we figured out the audio yet? This one kind of needs the audio. You should just be able to click in the middle. You're going in the wrong direction.
We are going. We are going. The history of this agency is marked with broken barriers, once viewed as impossible, with science fiction turned reality, with innovations that have spun industries for all.
In the skies of our just outside of gravity, and we touch points all across the solar system.
Our generation and the generations to follow.
The tens of thousands of jobs associated with propelling us to the...
I can't seem to do it with the clicker. Yeah. Yeah, okay. So in a nutshell, what that video talked about was all the reasons why we're going back to the moon. We're going back to the moon because the technology that we developed by going to the moon benefits mankind. You know, if you look at the Apollo program, much of the technology that we rely on today originated from the Apollo program, and the advancements in health, in communications, in virtually every aspect of our lives will benefit from the technology advances that we're going to develop in order to live and really thrive on the moon. This time when we go back to the moon, by the way, we're not going back for 3-day missions or 2-day missions. We're going back for 12 or 30-day missions and even longer. This is a picture of the gateway, and you can see up at the top of the lunar gateway, you can see the Canadarm, and the Canadarm3 is going to actually be a combination of two robotic arms, a small arm and a larger arm. And the small arm is going to be an arm that will conduct maintenance on the larger arm. This kind of talks about some of the components of the Gateway program that we're developing. So we're developing ground segment. And the ground segment, by the way, will be in our brand new state-of-the-art facility in Brampton, Ontario. We're going to have a mission control center in that facility that's going to operate the Canadarm. The robotics, the flight segments, and we're going to be using that for inspection and repair, vehicle handling, maintenance, assembly, EVA support. So as astronauts go out and do stuff outside of the space station, they'll be supported by the arm. And of course, it'll be useful in science experiments as well. This is just talking a little bit about the ground segment, stuff that needs to be done in the ground segment. You can see a little picture down the bottom corner there, and that's a picture of our Mission Control Center in Brampton. And this is really the timeline. So December 2022, Artemis 1 launched. 2024, we're going to see Artemis. So Artemis 2 is showing 2023. That's actually been pushed to 2024. Artemis 3 is going to be 2025. And Artemis 4, so the robotic arm, or GERS as we call it, is going to happen either in Artemis 4 or Artemis 5. So this is real stuff. This is happening. The missions are underway. The exciting one that I think we're all waiting to see is Artemis 3, and that's going to be the first mission to the surface. And by the way, that mission is going to include the first female on the surface of the moon and the first person of color on the surface of the moon. This slide here really excites me. This talks a little bit about, so what happens when we get to the surface of the moon, right? These are some of the technologies and some of the advancements that are currently being worked on to enable us to live and thrive on the surface of the moon. So you can see things like, surface power, habitation systems, autonomous robotic systems, contingency crew transportation. And then it's all the way over to, Mars missions. So, we can't forget that all of this is in preparation to ultimately go to Mars for human flights to Mars. So that's a little bit about some of the key programs we're working on. Of course, MDA is working on, numerous other things. You're going to hear in the next month, you're going to start to hear talk about the OSIRIS-REx mission. That's a mission that MDA had a big part on. OSIRIS-REx was a really exciting mission where we sent a spacecraft out, caught up to an asteroid called Bennu. We circled Bennu, and keep in mind Bennu's moving at tens of thousands of kilometers an hour. We circled it, we mapped it using LiDAR, and the LiDAR was MDA's contribution to it. And then after getting a real good model of what Bennu was, that spacecraft snuggled right up beside Bennu, reached out and grabbed a hold of a soil sample or a sample of that asteroid. And now, for the last 2 years, OSIRIS-REx has been returning to Earth so that we could actually, analyze that sample. The reason you're going to start hearing more about it is because that OSIRIS-REx is scheduled to land next month. So I think it's going to be a lot of news. So when you start seeing talk about OSIRIS-REx and Bennu in the news next month, remember that we were talking about it here and that MDA had a part of that. So that's a little bit of MDA. Stuff that we're working on is really changing the world. There's an opportunity to come and work for us. These programs are driving a lot of hiring. We're going to be hiring probably, in the next 12 months, in the next 18 months, let's say, we're going to be hiring probably 1,500 people. A lot of that being engineers. Hopefully a lot of that being you people in the room.
So our team has been working really hard in the back, and they have the videos working. So if you think it's okay, we can play them right now.
Yeah, awesome. With some sound. Sorry to make the lights so difficult back there. Eventually powered by light speed. They're just messing with this thing.
We are going. The history of this agency is marked with broken barriers, once viewed as impossible, with science fiction turned reality, with innovations that have spun industries all their own, and with demonstrations of peace for all humankind.
We soar in the skies of our home planet. We maintain a human presence just outside of gravity, and we touch points all across the solar system and beyond. We're going back to the moon, and this is why.
The moon is a treasure trove of science. It holds opportunities for us to make discoveries about our home planet, about our sun, and about our solar system.
The wealth of knowledge to be gleaned from the moon will inspire a new generation of thought and action.
Without fail, every major program and mission NASA has invested in has led to technologies and capabilities that have shaped our culture.
The breakthroughs of the Artemis era will define our generation and the generations to follow.
The tens of thousands of jobs associated with propelling us to the moon today are just the beginning of a lunar economy that will see hundreds of thousands of new jobs develop around the world.
This is not an ambition of one entity or one country. The exploration of the moon is a shared effort.
Woven together by a desire for the greater good.
Why the moon? Because the missions of tomorrow will be sparked by the accomplishments of the Artemis generation today.
Because the ambition to go has already begun.
And because Mars is calling. We need to learn what it takes to establish a community on another cosmic shore. So let's camp close before pushing out.
And so, we go to the moon now, not as a series of isolated missions, but to build a community on and around the moon capable of proving how to live on other worlds.
We'll use the lessons from more than 50 years of peaceful exploration to send a new generation to the lunar surface to stay.
We will anchor our efforts on the lunar South Pole to establish the Artemis Base Camp, positioning us for long-term science and exploration of the lunar surface.
We will prove what it takes to assemble a complex ship in deep space.
We will perfect ascending down to and returning from a distant surface.
We will learn how humans can survive and thrive in a partial gravity environment.
With improved spacesuit designs, mobile habitats, and with reconnaissance robots pre-positioning and relocating supplies.
We will learn how to utilize the resources we find on these other worlds, starting with finding water ice and purifying it to drinkable water,
and refining that into hydrogen for fuel and oxygen to breathe.
We will establish fission power plants on the surface of the moon capable of supporting a growing community of efforts.
And we will expand the logistics supply chain to enable commercial and international partners
to resupply and refuel deep space outposts.
None of this is simple or easy, but nothing in our history ever has been.
The Eagle has landed. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
This kind of continuous lunar presence is a natural extension of all that we've learned in low Earth orbit. And what we will accomplish there will ensure the monumental missions to Mars are within reach. As we ready the launch of the first Artemis mission, and as commercial companies ready their lunar landers for the first private payload deliveries, we have already begun to take the next step.
So who's excited to be part of something like that?
I think a lot of us here recognize that sound. That's Scott Manley, a rocketry YouTuber. Do we have the video on the second slide? No? Okay. Well,
okay. All right.
Thank you for your presentation, and it's very thrilling and gives a lot of shivers. So thank you very much for being here and presenting.
All right, my pleasure.
So we do have time for a few questions if you want to come up stage and ask questions to MDA and how you can involve yourself in what we just saw. And in the meantime, maybe start with the first question. So, looking at all these amazing programs and the future of space, not only for Canada but internationally, how do you recommend for people present today interested to join your company? How would they approach the task of joining MDA starting to work in such a company?
Yeah, so, and I tell people, I get asked a lot, I'm interested in working, not just with the MDA, but with any company. How do I go about doing that, right? And there's a few things I tell people. Resumes alone, don't really sell people. So, networks are something that you should be looking at leveraging. So, in this room, in this event, there's probably a dozen people that work at MDA. Looking at teams, I see a few faces over here. So expand your network, get to know these people. Reach out to. There's this wonderful tool called LinkedIn. Anybody know about LinkedIn? Yeah. So reach out to LinkedIn, see who you know, connect with them. Yes, apply. Yes, go through all the proper channels, but also explore your networks. Those networks are going to help you far more than the resumes. Whether it's MBA, whatever company you're looking to join. The other thing is go beyond your academics. Look at how you can get involved in extracurricular stuff. Everyone in this room has to step up on, I would say 90% of people that are out there looking for jobs because you're involved in some really exciting things. You're exploring your passions, and employers are going to be looking for stuff like that.
Thank you. Thank you. You have a question?
First off, I thought this was a really great presentation. I'm really excited about it, the things that I was seeing. But I had just one question about the future of it, because I saw that you guys were sending a lot of things out to low Earth orbit and out to the moon and beyond. But I have concerns. I was wondering if you guys have any protocols in place to help to make sure that you can take down or remove all the debris and the old satellites that you're leaving.
You're serving up some softballs here. A couple answers to that. So we're partnering with some companies that instead of looking down on the Earth are looking up in the sky, right? And we're doing that so that we can map all the, all the devices that are up in, low and medium and geo orbits, right? So we're doing that so that we can predict if there's going to be any collisions, and we can do some sort of traffic control up there. But then the other thing that we're doing is we're building robotic spacecraft that will go up and, if there's a satellite that has been end-of-life, but it's still in orbit, it's probably, the orbit is eventually going to decay and it's going to come down. But the problem is you don't know when it's going to come down, you don't know where it's going to come down, right? Yeah, exactly. So we will either, using our robotic spacecraft, we'll do one of three things. We'll go up and maybe refuel it, right? We have that capability. Or we can push it down to accelerate the return to Earth, or we can push it into a higher, uncongested orbit farther out. So we have that technology. We're working on missions for to do just that right now. Yeah.
To build on that craft sounds very interesting. But what springs to my mind is the economics of it. Would you be pairing that with other existing missions where a craft goes up to serve a function, deposit a satellite into an orbit that you want, and then goes on to retrieve and do the refuel mission? Or is when you send a craft up to specifically target a satellite for either deorbiting or refueling, is a single craft mission where you're only targeting one satellite? Or will they build multi-rendezvous? How do you make it efficient and effective?
Yeah, so I don't have all the answers to that, but what I can tell you is that the idea is that we have a spacecraft in a certain orbit that will be able to do multiple tasks. So it wouldn't be a single-use mission. We just announced a project, I think it's in Europe, where we're doing just this. And that's a smaller scale, but the idea is we'll have a spacecraft in orbit to do other missions of that sort.
Amazing, thank you.
Do you have a follow-up? You're going to put me on the spot here.
Well, so that
I'm the HR guy, so I don't necessarily have all the technical answers.
So that further leads into the stewardship of the orbit plane that you're taking in general. How do you plan on handling micro debris scale? Because a fleck of paint traveling at kilometers per second will mess up any satellite. So are you interested in further cleaning and maintenance of it, or are you only looking at the macro scale of the satellites you're putting up, or how are you handling the small stuff?
Yeah, so I don't know what the resolution of that outlooking program is. I don't know how small we can get, but my understanding is it can get quite small. I don't know if it can get to like a paint, but I know it can get quite small. And in those cases, we're not going up to deorbit that little tiny piece of space junk, but we're advising, other satellite operators that they may need to, shift their orbit to avoid a collision.
Thank you for your answer. You can see the sustainability classes coming out of the life cycle analysis. Okay, directly there. Hi guys. I met a few of you today already. I work at the NDA, and so I just wanted to clarify with Dave. If you have more technical questions, I'm not going to spend 30 minutes to answer all of them right now. But come see me after if you want to chat about some specifics, space sustainability, MMODs, and all those things. I'll hang around and I'll be happy to answer your question. So keep the soft ones for Dave, and you can give me the tricky questions after. Well, then allow me maybe a more HR-geared question. So a lot of students in this room are maybe applying for their first internship, first experience at work. How should they prepare to interview and show the capacity that they've developed through the rocket team to a company like NDA?
Yeah, excellent question. And I get asked that a fair bit. And what I tell people is don't limit yourself. You know, we have some co-op students, interns that have done amazing things. Not because they were asked to, right? Because they put up their hand and said, hey, can I be a part of it? So years ago, when the Hubble Space Telescope had some problems, they launched a shuttle mission to go and fix it. What they had to do was they had to take Canadarm1 at that point and extend it straight up. And then they had an astronaut standing off the tip, so the Canadarm was sticking straight up. They had an astronaut, like his feet were bolted to the end of it, and he's standing off the tip of it, right? And then they maneuvered him up to the Hubble and fixed the Hubble. That mission was planned by co-op students, right? So don't limit yourself. You get the opportunity, go in there, and you know the most of the limitations that you'll encounter are self-imposed. So don't impose those limitations on yourself, right? Ask if you can do things. The worst that they can say is no, right? So get in there, get excited about what you're doing, roll up your sleeves, ask to get involved. 9 times out of 10, they're going to let you get involved.
Perfectly within the theme of sustainability, and still today Hubble is working, they're still in service.
There you go.
So, thank you very much. And if I may conclude by just asking, I'm putting you all on the spot, but who here had the occasion to intern at MDA? If you can raise your hand in your life, in your experience, so that other students in the room knows who you are and can come talk to you and ask about your experience, and then eventually drop off the resume at the MDA stand. So.
Okay, just one last question. Of those who haven't, who want to. All right, good.
Alright, so this concludes the first day of the Launch Canada 2023 conference.
There is one more thing that is coming up. So it is 5:15-ish. At 5:30, if you want, I would welcome you to the baseball field right in this direction, next to the Sportsplex, where we'll be launching 10 to 12 small rockets that students today have been building and painting and customizing. So around 5:30, if you want to come and see some of the first rockets of this edition of Launch Canada Take to the Skies. So once again, thank you for being here and congratulations for a first day of competition.
It takes a second.
Ready to go for launch? Steering off, go for launch. It is with great pleasure. We are going to press the button. Countdown in 5, 4, 3, 2, 1. Ignition. Congratulations on what appears to be a very successful flight. Well done, everyone.
Just how much work you guys put into this. How long have you been building this exact rocket?
You have to clear airspace, make sure the waterways are clear downstream and stuff. And then the other part, of course, is just supporting what these students are doing.
Well, so the objective of the flight was to successfully stage the rocket. Staging is a huge point of potential failure for a rocket.
Pressing on it, pressing on the nozzle. There, look at that. It's flush. How'd you like that? 5, 4, 3, 2, 1.
What does it take to launch a rocket? It takes vision, countless hours of planning, design, and testing. But most of all, it takes people like us. Engineers, designers, machinists, business people, and inventors. We are University of Ottawa Rocketry. Though we might look like a bunch of nerds, our competitive spirit is tenacious. In 2018, we started competing in the Spaceport America Cup. launching and recovering a 9-pound payload to an altitude of 10,000 feet. Our rocket, Jackalope, placed top 10 out of more than 122 teams internationally. But apart from our shiny medals, our mantra has always been to innovate, to learn and to pursue the interesting. From the development of a hybrid engine, to new parachute concepts, to custom avionics, and so much more, our capacity to create is through the roof. With a vibrant team of students, we foster a culture of hard work and ingenuity. This year, we set our sights for the 2023 Launch Canada competition, to reach an altitude of 23,000 feet with a solid rocket while building experience and laying the groundwork for a future hybrid engine. Our team has grown and transformed in so many ways. With more interest and collaboration than ever before, we are confident that we can lift ourselves up to new heights. We are grateful for the support and guidance of our mentors, faculty advisors, and university for taking a leap and putting their faith in the engineers of tomorrow. So, what does it take to launch a rocket? Well, it takes a team like UO Rocketry.
Hello, my name is Mohammed. We are the McGill Rocket Team.
Safety first! 3, 2, 1.
And this is Project Porthos.